catastrophe strikes in the heart of Minnesota.
It lifted my car up, I heard a loud boom, and I thought, that's it, that's it.
A detonation disaster in downtown Dallas.
Are you serious? What the heck is going on here?
In Denmark, a rail tragedy on a cutting-edge crossing.
One of the most fatal and tragic accidents in Danish train history. It was horrific.
And in Iowa, a devastating dam failure threatens an entire community.
You don't have a minute. You need to get out now.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Bridge engineers are in a constant fight with gravity. Every joint, angle, and dimension has to be perfect. Even a small miscalculation can cause a major disaster. Like this bridge failure in Minnesota, a fatal collapse on one of the state's busiest crossings.
Seeing it crumbled in the river was nothing like I'd ever seen before.
This rush hour disaster revealed a deadly design flaw.
I thought I was gonna die, and you just waited for that wave of concrete to gobble you up and to take you away.
The tragedy left everyone asking, why did it fail so catastrophically? Minneapolis, the name means waterfall city, and it thrived thanks to America's most iconic river. Stacy Bengs is a local journalist.
Minneapolis was built around the Mississippi River. There's so much life and color in the city. It's a source of recreation, but more importantly, the city is built around the power of the Mississippi River.
All that power carved a gorge through the land, and as the city grew, so did the need to cross the river.
Minneapolis now has more than 20 bridges crossing the Mississippi. Without them, the city would grind to a halt.
The St. Anthony Falls Bridge is one of the busiest. It carries I-35 over the Mississippi, a crucial connection on an interstate running from Minnesota to the Mexican border. In 1964, construction started on the original 8-lane crossing, the I-35 Mississippi River Bridge. Engineer Dr. Matt Rouse is a bridge research specialist.
So the I-35 bridge in Minneapolis was designed and built in the 1960s. The style of bridge, this deck truss, the basic structure of the bridge has two of these large trusses which are parallel to each other, and they support the deck that the traffic moves on.
Each 325-meter truss was a lattice of horizontal, vertical, and diagonal steel members, all connected by multiple gusset plates.
This gusset plate is a steel plate that connects several of these truss members that all meet at a certain point. So for example, there's a gusset plate right here, right, which is bolted or riveted to all of the individual truss members. And that gusset plate holds those members together. And if the stress gets too high on that gusset plate, it can rip or tear.
Gusset plates are found in all kinds of steel structures, not just bridges, but stadiums, television masts, even the Eiffel Tower. They're like the glue that hold these huge objects together.
The 35W bridge opened in 1967, and for 4 decades carried more than 100,000 vehicles a day over the Mississippi.
The 35W bridge connects people, it connects life. It's part of the heartbeat of Minneapolis.
On August 1st, 2007, construction workers and cement tankers were on site, waiting to resurface the bridge. 4 of the 8 lanes were closed. Andy Gannon was driving across town.
That day I was heading to a wake of a coworker of mine whose father had passed away. And when I got on the bridge, got on a little bit, and the first thing I heard was a loud boom, and the bridge moved lateral. And I thought, well, that was weird. I thought maybe that was a barge that hit one of the beams in the water.
But this was no barge. At 6:05 p.m., motion sensors triggered a surveillance camera. The 40-year-old bridge failed without warning.
So you watch the bridge buckle up and lifting cars up, and some of the cars falling down over the sides. It lifted my car up. I remember being up above everybody, heard a loud boom. That was the bridge coming back down.
Almost 140 meters of the central span dropped into the river.
We all free-falled and just rode it down, and my life flashed before me, and definitely thought that was going to be it.
More than 100 cars went down with the bridge.
For about 3 to 5 seconds, it was the most eerie quiet, the most eerie silent. And at that moment, I actually thought I had died.
Deputy Fire Chief Don Leadham was on duty when the call came in.
35W bridge is right off to our left. And normally it looks like that. But on that particular day, the cement kind of had a horizon line, and you couldn't see the part that actually went over the river because it didn't exist anymore. It was like, nah, that can't really be it.
As Don and the fire crew arrived, the scale of the disaster hit home.
It became evident that they were going to be going into a very fluid situation. The bridge had just collapsed. It by no means seemed like it was stable at the time. We still had cars up on top that were letting loose and sliding down and falling off the ledge.
Journalist Stacey Bengs also witnessed the devastation firsthand.
I only lived about 3 or 4 blocks away, and I heard and felt something. Somebody even asked, "Did you guys feel that?" And I looked out my balcony and I saw the fracture sticking up in the smoke. I was in complete shock, and my gut instinct was just to get my cameras and go there.
Nearly 200 people had been on the bridge when it fell. It was a race against time to rescue them.
It was shocking, and it was unbelievable to see.
I was calling my wife to say goodbye. I thought for sure I was going to die. If I could get her on the phone for even 2 seconds to say I love you, that would be good enough for me.
Not everyone was as lucky as Andy. 145 people were injured. Tragically, 13 died. The nation was left asking just what had gone wrong.
It's haunting to this day when I think about what people on the bridge went through when that went down. I think we were all just kind of in a collective shock.
In the wake of the disaster, an investigation was launched to discover why the bridge had collapsed and why so suddenly.
One question was whether the combination of construction equipment and heavy rush hour traffic was to blame. These added more than 600 tons of weight to the center span. But that in itself shouldn't have triggered the collapse.
Detailed inspection of the CCTV delivered a crucial clue.
By analyzing the footage, investigators were able to pinpoint exactly where the fail started. And they discovered it was a specific set of gusset plates, the very things that held the bridge together.
The first part of the bridge to fail was identified on the south side of the central span, with gusset plates known as the U10 node. The steel plates were found to have buckled and fractured completely. As the bridge dropped, the exact same plates on the north side cracked, and the center span was doomed. Bridge specialist Dr. Matt Rouse explains.
This type of bridge is very non-redundant. So if there is a localized failure which causes one of the trusses to fail, the whole bridge comes down.
So why did these critical plates fail? Investigators uncovered a tiny but crucial design flaw in the original plans.
This gusset plate that we're talking about that failed is about 10 feet wide and 6 feet high. It's a huge piece of steel. And this one in particular that failed was about a ½ inch thick. And according to the code and the design standards, it should have probably been closer to an inch in thickness. It did not meet the standards of the day, and it certainly didn't meet the standards of today.
That small miscalculation ultimately proved catastrophic. And yet the bridge had stood firm for 40 years with the flaw hiding in plain sight.
City historian Laurie Williamson explains.
This is an infamous gusset plate from the 35W bridge over the Mississippi River that collapsed in 2007. I think it was a combination of design flaw from the get-go, of it not being thick enough, but I also think that there was a lot of wear and tear on it that weakened it to a point where it ultimately failed.
Decades of pounding by traffic and the weight of construction equipment proved to be a lethal cocktail.
It was a perfect storm of all the right combinations. It couldn't take it and the whole bridge came down.
The city was in mourning, but the I-35 was a vital link and had to be replaced. On September 18, 2008, just over a year after the tragedy, the new 10-lane St. Anthony Falls Bridge opened to traffic. This time, engineers weren't taking any chances.
Bridge engineering had come a long way in 40 years. Instead of a fracture-critical steel truss, which risked collapse if one plate failed, the new bridge uses multiple concrete girders, meaning it's a much more robust, safer crossing.
So for example, instead of 2 major structural elements of 2 parallel trusses, we might have several parallel beams, each which supports a smaller portion of the deck. And the idea there is that with more redundancy, the consequences of a local failure are much smaller.
Minneapolis was on the move once more. But lessons from the failure continued to reverberate through the engineering community.
This bridge collapsed. Departments of transportation all around the country suddenly scrambled to increase their inspection programs, especially bridges of similar design, to make sure that they didn't have a similar situation on their hands that had gone undetected.
It was a reminder of the risks in older infrastructure. In Minnesota, inspectors now assess fracture-critical bridges at least every 2 years.
What I've taken from this situation is really a broader look on life and my own life and what really truly matters, what really doesn't matter, because when you come close to dying, at that moment I remember going, I don't want to die because I'm not done.
Every engineer knows that careful planning is the key to success. But sometimes even the best laid plans go disastrously wrong. Like this calamity in Texas, where a routine detonation turned to disaster.
When you're using well over 100 kilos of dynamite, you really hope you've got things right.
An explosion that made headlines for all the wrong reasons.
Are you serious? What the heck is going on here?
And a building that just wouldn't go away.
Safe to say, this demolition didn't go to plan.
Dallas, Texas is a big city with a southern can-do attitude. Journalist Sean O'Neill explains.
The symbol of Dallas is a Pegasus. It's an ordinary creature that becomes extraordinary. It's a workhorse that sprouts wings and flies up above everybody else. And that's Dallas in some ways.
Dallas might have a reputation for its oil and its cowboys, but there's a lot more to this city than meets the eye.
Dallas made its bones in oil, but oil is just one of the many things. It's just got its hand to just about everything. It's always out there every day just selling itself.
One of Dallas's boldest marketing ideas grew out of the long, baking hot summers.
In the 1920s in Dallas, you had this place called the Southland Ice Company, and they were just selling ice out of their storefront. One of the employees, this guy named John Jefferson Green, He realized that, he could sell milk and eggs and bread and that sort of stuff out of their storefront. It was a convenience for people.
The idea quickly caught on, and by 1946 was spread across Texas, renamed 7-Eleven.
They decided after World War II to change their name to reflect the hours that they were open. By the 1960s, 7-Elevens were everywhere.
In the 1970s, this fast-growing company needed a brand new headquarters. Built around 3 kilometers north of downtown, in typical Dallas style, it would be bold and strong at heart. Thomas Taylor was the principal design engineer.
These are the original plans. They were completed in 1971. I had this idea as a young engineer to make something more out of it than just a standard routine building. So we came up with the concept to actually use the facade, the expression of the building, actually use that as structural.
Standing around 48 meters tall, the outside of the 11-story tower would be built from precast concrete panels and steel. But its real strength would come from within, supported by a solid cast-in-place concrete core that would both stabilize and provide structural rigidity.
The whole purpose of the concrete core was to tie all the precast and steel floors with steel beams to the concrete core so they won't fall over. If this were a tree, that would be the tree trunk.
These days, precast panels can be made strong enough to play a structural role. But back in 1971, they were mainly cosmetic. So this building's solid concrete core was essential.
The primary purpose is to keep it from blowing over. It's a 11-story building with plus a basement, so the wind pressures are pretty high. So obviously a core is extremely important because it's the whole lateral stability of the building.
By the 80s, 7-Eleven had moved on, and in 2020 the tower was scheduled for demolition to make way for a $2.5 billion redevelopment.
Built in the 70s, so that's 50 years ago, so that it had a good long life.
Sunday, February the 16th, 2020, Demolition Day.
There's two ways to demolish a building. One is just knocking it down with heavy balls or something, but then the other is to implode it.
More than 100 kilograms of dynamite were primed and ready to go.
When that first implosion hit, it took down everything else. It took down the steel bars, the windows, all the kind of frippery, if you will, and it just left this solid concrete core.
Built to withstand hurricane-force winds, the core had just stood up to more than 100 kilos of explosives, shaken but still standing.
The core only dropped around 10 meters and was left with a tilt of 15 degrees. That's more than the Leaning Tower of Pisa.
Local street artist Gerald Sestiter knew that this was too good an opportunity to miss.
My brother called me and he said, hey, did you hear about the Leaning Tower? I said, yeah, I know the Leaning Tower. Everybody. He goes, no, the one in Dallas. I said, what? So I came out here, and the spectacle was something that I just had to capture. I hadn't seen anything like that.
As Gerald memorialized the catastrophe on canvas, the core quickly became known as the Leaning Tower of Dallas.
It became a real tourist attraction. People started going to it specifically to take photos like you would in Italy with the Leaning Tower of Pisa, pretending to hold it up or kick it over or whatever.
The Dallasites kind of were fond of it. This is our Leaning Tower. It was a fun time.
One of them started a petition asking for it to be made a UNESCO World Heritage Site. There were calls to make it a permanent tourist attraction. Obviously, there's a lot of safety concerns with that sort of thing.
But how had a supposedly routine demolition gone so spectacularly wrong?
Engineers build structures to last, not fall over. So when you're planning to use explosives to bring one down, it's crucial to know exactly what you're blowing up.
That's kind of how we built it back then. We didn't build them to make them easy to demolish.
It seems the core might have been stronger and more stable than expected. This wasn't news to the tower's principal engineer.
I wasn't surprised that the core was hard to come down. If they didn't have a proper number of charges, or if the timing was bad, or maybe a charge didn't go off at the exact time it was supposed to go off. Maybe they undersized their charges, I don't know.
One explanation was that the dynamite would blast the precast concrete and steel floors while cutting the core off at its base, toppling it to the ground like that tree. But one thing they might not have bargained on was the basement.
If you look at it closely, it looks like it fell in the basement. So it actually did fall down. And I think maybe the rubble of all of this other stuff that was in there was surrounding the core. And so when it tried to fall over laterally, the rubble around it is probably what contained it and prevented it from being able to fall over.
The core was wedged in and leaning at around 15 degrees. So, on February the 24th, 8 days after the blast, it was time for Plan B, the wrecking ball.
If they needed 135 kilos of dynamite to blow it up, you'd think they would need a giant wrecking ball too. But think again.
To take down the 11-story concrete core was a 2,500 kilogram wrecking ball, just over 1 meter high.
There was a silence in the crowd, and then there was a great exhale of, what the heck is going on here? Are you serious? Is that what they brought?
What Dallasites were witnessing wasn't blowing them away.
I don't know how big a wrecking ball you can actually get, but you know, especially from a distance, it just looks like this little cannonball just taking pot shots at this building.
Literally, it looks like my paintbrush coming up to the side of the building here, and then
the ball would just bounce off of it and just bounce off of it.
And eventually the local news set up like a live stream. You could watch it 24 hours a day.
all day long.
That wrecking ball might have looked underwhelming, but at least it got the job done, eventually.
On the afternoon of March the 2nd, 15 days after the blast, the Leaning Tower of Dallas finally leaned no more.
It was over. It was done. Everybody stood around, everybody that was there. All that was left was just a pile of rock.
With the land now leveled, and despite the calamity, the Leaning Tower left a lasting impression on the city.
It brought the community together and it allowed us to focus on something that was outside of ourselves.
And one thing is for certain, the core was definitely up to the job.
It does kind of prove that it was strong enough to resist the wind, because that was what it was intended to do. Everybody in Dallas knows and loves the Leaning Tower of Dallas.
The tower is gone, but it's not forgotten.
Engineers are on a constant quest for simple solutions to complicated problems. But it only takes one oversight to turn a fix into failure. Like this railroad disaster in Denmark, on one of Europe's most iconic bridges.
This was a ticking time bomb. No one had any idea there was a problem until it was too late.
A hidden design flaw with tragic consequences.
One of the most fatal and tragic accidents in Danish train history.
A deadly discovery that sent shockwaves across Europe.
We warned the other investigation boards in Europe. This could be safety critical.
Denmark. For centuries, the capital Copenhagen, on the nation's biggest island, could only be reached by boat. Stefan Jorgensen is a local journalist.
Denmark is a small country separated by many islands. If you had to travel from the western part of Denmark to the capital of Copenhagen, you had to take ferries. It took hours. But then in 1998, the Great Belt Bridge was constructed and everything changed.
With a main span of just over 1.5 kilometers, the Great Belt Fixed Link is the third longest suspension bridge in the world. Standing tall, this mammoth crossing revolutionized Denmark's transportation network.
The Great Belt Bridge totally redefined the infrastructure of this country. So what took an hour before crossing by ferry now takes not more than 10 minutes.
This crucial link helped connect northern Scandinavia with the rest of Europe to the south by both road and rail, and sometimes a clever combination of both, known as piggybacking.
For about 40 years, Europe has used rail network to carry road freight semi-trailers, piggybacking on specialist rail cars called pocket wagons. Instead of being towed by a truck, the trailer sits in the wagon like being in a pocket.
The only fixed connection is where the trailer's kingpin slots into the rail car's saddle, with teeth that grip it in place, all secured by a locking arm. This tried and tested method was transporting freight safely across the Great Belt Bridge and into Europe for decades. January the 2nd, 2019, a 110-kilometer-an-hour storm was battering the coast of Denmark. The Great Belt Bridge was right in its firing line and closed to road traffic, but open to rail. Local journalist Stefan Jorgensen was on the train to work.
I was crossing the Great Belt Bridge, and approximately about 7:30, the train stopped in the middle of the bridge. And in the speakers, they announced that we had to stop because a cargo train had dropped some kind of tarp on the tracks, and that we couldn't proceed.
Chief accident investigator Bo Hanning was on duty at the time.
We got a phone call from the Danish State Railways, DSB, who told us there's been some incident on the Great Belt. Maybe some passengers had got wounded a bit.
It was far worse. At 7:29 a.m., a commuter train heading to Copenhagen collided with a semi-trailer hanging from a freight train.
We pretty quickly found out that it wasn't just a tarp on the tracks. It was a lot bigger than that. It was very serious.
Moments before the incident, CCTV captured this grainy footage. The empty trailer had fallen sideways from the freight train and was being dragged into the path of the oncoming commuter train. Both were traveling at around 120 kilometers an hour. By the time the passenger train saw the trailer, it was too late.
In a very few seconds, there was huge damages along both the passenger train and the freight train.
131 passengers were on board when the front carriage hit the trailer. 18 people were injured. Sadly, 8 lost their lives.
What started out for me, and I guess many other journalists, as a quite normal day, quickly turned out to be an extraordinary day with one of the most fatal and tragic accidents in Danish train history.
This accident was on one of Denmark's busiest bridges, between 2 regular rail services. So Bo knew they had to uncover the cause of the disaster.
It was important for us to find out as fast as possible what happened. Not only what happened, but why. For me, I can describe this as a big puzzle, and we have to find all the parts to put together.
The accident spread wreckage along hundreds of meters of track.
The collision actually was just after where the bridge started, and then the passenger train broke and stopped a few hundred meters after. And the freight train continued here on the line and actually stopped around here with the locomotive just over there and with the wagons up here.
The semi-trailer had been dragged sideways by the pocket wagon until it was knocked completely clear by the passenger train. Bo and his team faced a massive challenge finding evidence.
It was a train with empty beer bottles in boxes. So there was glass bottles all over. So we was trying to locate which parts on the track was actually a part of the accident and was train parts from the freight train or from the passenger train.
The big question for Bo and his team was why the semi-trailer had fallen from the pocket wagon. So investigators focused on the only connection between trailer and rail car, the kingpin and saddle.
We had three main scenarios. One of them was that the semi-trailer was correct loaded but not locked. One of them was actually that it was wrong loaded. And the last scenario was that it was correct loaded, but the wind was strong enough to draw it out.
Just 6 days after the crash, with the investigation still underway, the Danish authorities banned all pocket wagons from the rail network.
Suddenly, goods going from Germany, for example, to Sweden couldn't cross in Denmark with these kind of wagons. These kind of pocket wagons were banned until the companies could reassure the Danish authorities that it was safe.
To find out how the 7-ton semi-trailer had been blown from the pocket wagon, the team brought in Professors Jens Sorensen and Robert Mikkelsen, wind experts from the Technical University of Denmark.
We used a model train, which is identical to the real train, and put that into a wind tunnel to measure and test, visualize, and investigate how the wind was blown around the bridge and the train.
By simulating the exact conditions on the bridge that morning, Jens and Robert discovered that strong winds, combined with the speed of the train, were enough to blow the empty trailer off the pocket wagon, on one condition.
We found out that a wind speed in the order of 22 meters per second was sufficient to crash this down here, provided that the king rod was not attached.
The theory was tested at full scale, with an empty trailer in equivalent winds, proving that if unlocked, the kingpin could be blown from the saddle. But according to reports, the kingpin had been properly locked in place.
If it was locked correct and you lift in the semi-trailer, it is so heavy, the lock, that you could lift the wagon, the whole wagon. And you don't have wind powers enough to derail both the wagon and the semi-trailer in a train.
On closer investigation, they discovered a previously unknown flaw in the pocket wagon system. The locking teeth on the saddle weren't always locking.
The problem was really very simple. Although the operating lever looked to be locked, the teeth in the saddle weren't always fully closing around the kingpin, meaning it wasn't locked at all.
And this flaw was made worse by maintenance access issues.
We could see that actually the maintenance of these locks was not done for several years. To be sure that the lock could work, you have to open and to lubricate the beneath of the lock to be sure all the parts inside could work, and it hasn't been done.
While it's clear proper lubrication was safety critical, it wasn't mentioned in the guidelines.
This is one of those problems that goes unnoticed until a disaster brings it into the light. Pocket wagons had been hurtling around Europe unsecured for years.
The combination of the trailer being empty and exposed to high winds on the bridge revealed the problem very dramatically.
With the cause of the accident identified, new maintenance guidelines for locking mechanisms were implemented throughout Europe.
So this was one of the consequences, to be sure that other hitches of this type wouldn't have risked the same failure in the future.
In the wake of this accident, the rules were changed, requiring these crucial connections to be serviced regularly. So hopefully nothing like this can ever happen again.
Engineers say Mother Nature always bats last. And when it comes to big construction, her strike rate can be devastating. Like this dam collapse in Iowa, on a collision course with an entire town.
We could be wiped out. It was scary. This is my town. What's going to happen if it's wiped away?
Hundreds evacuated in a catastrophe of epic proportions.
You don't have a minute. You need to get out now.
An engineering mistake exposed by Mother Nature.
The power of water, a single rainfall event, almost without warning, can result in the failure of a dam that's been in existence for roughly 100 years.
Iowa, in the heart of America, is home to hundreds of rural communities like Hopkinton, a small town that grew up on the banks of the Maquoketa River. Kathy Harris is former mayor.
Hopkins has always been my home. It has grown. I mean, we're a population of 628 now. I enjoy the small town life. When somebody's sick, somebody needs something, we're there for them. And that's just the way Hopkins is. So that's why it's so special to me.
Around 15 kilometers upriver lies Lake Delhi. Now a hotspot for fishing and recreation, its dam was once a source of power for Hopkinton.
Delhi Dam was built in the 1920s as a hydroelectric power station and generated electricity for about 40 years until the turbines were switched off in 1973.
Engineer Randy Rattenberg is president of the dam's operating company.
These are the original inlets where the turbines were. This is where the water would flow into to spin the turbines. Right now we're in the turbine room. These are original from the construction of the dam. So the purpose of these turbines was to generate the hydroelectric power, which is the reason the dam was built to begin with.
Completed in 1929, the dam beside the powerhouse had a 26-meter wide spillway designed to release water during periods of high flow.
The old dam had 3 gates. We're actually standing over the top of them right now. This area is part of the original structure built in the 20s.
Holding back the rest of Lake Delhi was a 150-meter long earthen embankment, around 18 meters high, with a reinforced concrete wall at its core to anchor the dam in place. Professor of Engineering Larry Weber is a hydraulics expert.
In many cases, there will be a portion of the dam that's concrete. That's where the structure of the dam is. And then there's a larger earthen embankment, just to hold the water back.
For more than 100 years, the dam controlled the flow of water to the river below, while Lake Delhi itself became one of the county's most sought-after suburbs. On July 22, 2010, a heavy storm began to fall on the Maquoketa River. At one point, 25 centimeters fell in just 12 hours.
And so there was a warning that went to communities downstream of a potential dam failure at Lake Delhi.
If the dam burst, the small town of Hopkinton would be the first in its path. In the early hours of the morning, Mayor Kathy Harris received a knock at her door.
It was about 6 o'clock on July 24th. I looked out my bedroom window and I see the fire chief. I said, "What's going on, Craig?" And he said, "They think the dam is going to break. We are evacuating this area."
Delhi Dam engineer Randy Rattenberg had a bird's-eye view of the impending disaster.
Me and another guy were up in a plane and we were taking pictures. I'm watching and I'm just like, wow, this is really bad. This is not going to go away anytime soon.
Randy was right. At 12:49, the roadway across the dam dropped into the deluge. 11 minutes later, the entire embankment failed.
All the water that was being held back from upstream went downstream. It was pretty dramatic.
Around 2 million litres of water per second were now flooding down river, rocks and roads straight towards Hopkinton.
There's houses that are just gone now because the ground that they were sitting on doesn't exist anymore. It's gone.
As the torrent continued, the outskirts of Hopkinton were engulfed in a wall of water.
When it came with such a force. When you looked at it, it looked like a big ocean down here. It came over the road here and back through here. That is the highest I have ever seen the water. It's scary.
When the flood subsided, questions were being asked. Why had this historic dam failed? Was it an act of God or an engineering catastrophe?
Town could have been gone. It was scary. Something that I'd never want to live through again.
In the aftermath of the disaster, an investigation was launched to find out exactly what had gone wrong. The dam's 3 spillway gates, designed to prevent an overflow, were the first port of call.
A year before the dam burst, it was clear that one of the spillway gates needed repair. But by the time the dam broke, the works didn't appear to have been completed.
They had 2 of the 3 gates opening. The third one was open partially, but was not able to be opened completely.
The investigation concluded that even a fully functioning third gate wouldn't have saved the dam.
At its peak, more than 2 million liters of water were pushing against the dam every second. Even with all 3 gates fully open, the spillways could only cope with half that amount.
And so that caused the lake level to rise more and a little faster until ultimately the lake level rose to a point where it overtopped the dam.
Evidence in the rubble explained why the overtopping had caused such destruction in the embankment. The height of the concrete core.
The concrete core in the dam was at a certain design height. The lake level rose to a point higher than that. That caused seepage to happen. And that water seepage caused some erosion to the interior core of the dam.
The reinforced concrete wall was around 1.8 meters lower than the top of the embankment. As flooding made its way over the top, water eroded the earth in a process known as piping. And the whole thing started to collapse.
Piping happens when fast-flowing water gets into a dam or embankment, eroding soil and creating a long cavity, or pipe. In some cases, it can cause a catastrophic failure of the structure.
As it overtopped, the force of the water was simply too much for the 80-year-old structure to bear.
This event tested that dam to a level it had never seen before. A single storm in the Maquoketa River. It was a single watershed, but in that watershed, it was devastating.
In the wake of the collapse, the dam was redesigned, reinforced, and reopened in 2016. This time with an award-winning spillway, the first of its kind in Iowa, the aptly named Labyrinth.
The labyrinth is kind of a zigzag shape, and this labyrinth controls the pool. And it also allows for the river just to maintain its normal flow as if this dam was never here.
The shape effectively makes the spillway about 3 times longer than a straight design in the same space, meaning the labyrinth can pass huge amounts of water compared to the old spillway.
It's a night and day comparison. There is no comparison. With this design, it's going to make it safer for the downstream people as far as not having a major catastrophic flooding event happen again.
The rebirth of the dam and the lake has reinvigorated the community and the local economy. And for this area at least, will hopefully make the catastrophe of 2010 a very distant memory.
Hopkins could have been wiped off the map, and it wasn't. So we were very, very lucky. We just pray and hope that it never happens again.
In Kentucky, American icons buried in the dirt.
Made national and international news. It brought reporters from all across the country.
In Australia, tragedy strikes an epic Melbourne bridge.
You could see the bridge actually snapping in the center. You could see bolts coming off.
Big engineering shocks an Oklahoma town.
I just had visions of the entire downtown being leveled. Just feared the worst.
And in Canada, a near miss on a crucial river crossing.
I bounced, I hit the roof. I saw the bridge was collapsed.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. One basic rule of engineering is to build on solid foundations. But sometimes what lies beneath bites back. Like this catastrophic collapse in Kentucky.
I was in shock. I was in disbelief. It's stranger than fiction.
As 8 historic cars were swallowed whole.
This happened to be inside a building with millions of dollars worth of cars sitting on top.
It's a miracle the damage wasn't so much worse. America, known for its enduring love affair with the automobile, of all shapes and sizes. One of the greatest is the legendary Corvette. Owner and enthusiast Sean Preston explains.
What's special about a Corvette? Well, it's America's first sports car, and it's designed for the open road.
Named after a small, fast warship, the Corvette was inspired by Europe's small, fast sports cars.
Driving a Corvette, it's freedom. It feels like I own this part of the road, and me and the car are one. And I feel like I'm driving an iconic piece of American history.
In 1994, a museum celebrating this icon was built beside the Corvette factory in Bowling Green, Kentucky. Like the car, it boasted a distinctive look, thanks to the trademark Sky Dome.
You know, the Sky Dome is unique to the National Corvette Museum. You don't see this yellow structure and the red spire going through the middle of any building that we could think of, right? And it was done so that we could have a cathedral, if you will, to all things Corvette. Many of our unique pieces are kept in the Sky Dome. From each of the generations to one-of-a-kind prototypes, the Sky Dome acts as the shrine. It's an iconic structure with an iconic brand.
The unique Sky Dome towered strong and proud over the museum and its precious contents for the next 20 years. On February the 12th, 2014, just before 5:39 a.m., a burglar alarm was triggered inside the dome. Police rushed to the scene. Geotechnical engineer Mike Marassa was called soon after.
When the police arrived, they saw a great deal of dust in the air that they thought was smoke originally, so initiated a call to the fire department, who responded to what they thought was going to be a fire.
The CCTV revealed something much more shocking.
They neither had a thief nor a fire, but a massive hole in the middle of their iconic sky dome with 8 of their collector cars at the bottom.
The 10-meter deep sinkhole had swallowed millions of dollars of invaluable icons, and it continued to grow.
So when I arrived on the scene, the feeling in this room was surreal. The cars were almost like litter on the ground, this massive chasm of a sinkhole in the middle of the structure. The questions just kept mounting. How stable is the structure? How big is the problem that we're dealing with? There were way more unknowns than there were knowns.
Most concerning, the landmark red spire was in imminent danger.
It was hanging over the edge of the sinkhole, so the potential for any of this portion of the floor to collapse was pretty high. Had we lost the spire, it likely would have collapsed the entire structure.
The spire was only held in place by the steel connections in the roof of the dome. But the dome wasn't designed to support the spire. Who knew how long it would hold?
Mike and the team were in a race against time.
One of the riskiest and most immediate needs was to stabilize the spire structure. It involved supporting the structure with a steel element called a micropile.
These micropiles are steel cylinders about 1.5 meters long and 25 centimeters wide, which would be screwed together and drilled down through the cave into solid rock below.
The installation of 2 of the 5 micropiles that helped stabilize this structure were being installed immediately adjacent to the 35-foot drop-off. It was a risky operation.
Mike and the team worked tirelessly, and within a couple of weeks, the spire and dome were safe. Meanwhile, news of the collapse quickly spread.
Made national and international news. It brought reporters from all across the country. It brought geologists and cave experts.
And it was quite a circus of people that were walking around in amazement of this disaster that was at their feet.
The question was why, after nearly 20 stable years, had the floor collapsed? Kentucky's famous geology was an obvious suspect. Professor of Geoscience, Dr. Jason Polk, examined the wreckage.
One of the most cave-rich places that you have in the United States. We have over 5,000 known and mapped caves here. You can see extensively inside the caves. They can be literally 50, 60, 70 feet wide, 30, 40 feet tall, and they can go for miles and miles and miles.
This is Crump's Cave. It sits in the same rock as the museum and the nearby Mammoth Caves, the longest cave system in the world. All the result of soluble limestone.
Basically, the water is able to dissolve the rock as it picks up carbon dioxide in the soil and from the atmosphere, and it creates a really mild acid that over thousands of years dissolves the rock very slowly. And that, in turn, creates these large cave systems, which then become underground rivers, and it gets bigger and bigger and bigger until eventually it gets too close to the surface and you can have a sinkhole collapse occur.
Caves take forever to form, but the roof can collapse in the blink of an eye. You never even knew there was a cave there. And that's what happened with the Corvette Museum.
Looking at the Corvette Museum, you can see pretty clearly that this is the same type of environment where you had a large, massive chamber. Eventually, it's just its time, because it's the nature of the landscape for this rock to dissolve and for the rock to become too thin and for collapses.
Jason mapped the cave beneath the museum and discovered the sky dome was positioned almost perfectly above it. So how had engineers not noticed this before building the structure?
Generally, a typical geotechnical investigation would involve drilling through the soil and stopping once you hit bedrock, once you hit something hard.
In the 90s, engineers hit solid rock 9 meters down, and construction went ahead. So although it seemed like a mistake to build here, they had no reason to drill deeper. and the cave lay undiscovered another 12 meters below.
So it's not anything that can be identified as negligence. Structural roof collapse of a cave is extremely rare. This structural collapse of the roof of a cave also happened to be inside a building with millions of dollars worth of cars sitting on top.
Now it was clear what they were dealing with. The team had another challenge on their hands: how to get the Sky Dome back in operation above an active cave.
The design team and the construction team sat down and went through a number of options. Everything from relocating this structure, trying to fill the volume of the cave with an incompressible material to stabilize the cave. And ultimately what was decided was to isolate the structure from the cave below.
First, horizontal sheet piles sealed the cave, topped with 4,000 tons of crushed rock. Next, just like the spire, micropiles were driven through everything, deep into the bedrock.
These hugely long micropiles act like a grid of solid stilts for the new Sky Dome floor to sit on. So the cave could grow, collapse, whatever, the floor would stay put.
Supported by foundations more than 30 meters below, the new Sky Dome floor was on solid ground.
So if the entire area were to collapse, the structure would stay intact because it is isolated from all of the geologic hazards that lie beneath our feet.
With the Sky Dome safe, the museum had turned catastrophe into triumph.
The red line denotes the actual sinkhole. So now I am standing on the part of the Sky Dome that fell 30 feet below me, bringing with it 8 of our beloved Corvettes. 5 of these Corvettes could not be restored. They're in their original condition, so we can honor them and also tell the story about what happened on that fateful day. And in fact, we've kept part of the sinkhole alive and well.
The new exhibit opened exactly 2 years after the disaster, and visitor numbers have gone through the roof.
The museum really embraced the tragedy and used it to their advantage, and to see it in existence, standing strong, it feels good. And I'm sure it'll last for a long time to come.
With massive engineering, how you build is just as important as what you're building. And when the technique goes wrong, results can be devastating. Like this disaster in Australia, where miscalculations led to catastrophic failure.
I heard the biggest crack I've ever heard of my life. It was just like a bomb going off.
A bridge tragedy that rocked an entire city.
The whole of Melbourne was in shock. In the blink of an eye, it's come down. She just could not believe it had happened.
And left a nation asking questions.
I was just horrified. What happened? How did this happen?
Melbourne, with a population of around 5 million, is Australia's fastest growing city. The River Yarra, which splits the city, has played a pivotal role in its success. Ken McInnes is a local historian and engineer.
Melbourne is one of the most cosmopolitan cities in the world. It has a huge diversity, a huge entertainment culture, arts culture, sports centre of the world. Without the Yarra River, there'd be no Melbourne. It provides water from the upper catchments, and then the lower reaches, where it's south of Delta, it provides support for Melbourne.
In 1978, this epic Yarra crossing opened to traffic. The West Gate Bridge. When built, the 336-metre central span was the longest cable-stayed span in the world.
Construction of the West Gate Bridge started in 1968. As a young civil engineer, I was very excited that this major structure was being built in Melbourne because it was the beginning of the mega structures, the large bridges at the bleeding edge of design.
As a budding engineer in 1970, Ken even visited the construction site and documented his trip.
That's span 10 and 11, and you can see the stage of the concrete construction on the temporary forward being lifted into place on the last two spans here, the central core of the bridge on the western side. There's a shot of spans from Pier 14 to Pier 15. So you can see the sort of construction. The workers' sheds are on the top of the bridge, and you can see how the derrick is then lifting the pieces into place.
Key to this mammoth bridge's strength was a tried and true technique dating from the 1850s, which would allow traffic to drive along hollow steel sections known as box girders.
A box girder bridge is a box. It simply is just a box which is continuous, and the box itself then spans from the pier to the pier, and it forms a tube which is strong.
The simplest way to build a bridge like this is to make individual boxes on the ground, then lift them into place, using temporary structures to support the load. Then repeat the process until the bridge meets in the middle. But this wasn't just any bridge.
With this bridge, because of the size and the weight of the boxes, the decision that was made was to build half of the boxes, assemble them on the ground, then jack them to the top of the piers, then roll them across into the structure, and then hope that the two longitudinal sections would join together.
Box girder bridges are always built in sections, and normally it's only the ends that have to meet. But here, because each span was split lengthways too, there was a lot more lining up to do.
Construction took place simultaneously on both sides of the river. Each half, weighing around 600 tons, would be hoisted into place, then bolted together using steel plates or flanges. Tommy Watson was a 22-year-old steel rigger when he landed a job working on the massive project.
It was the biggest job going in I think the whole of Australia when it first started. There was at least 3,000 people working on the job, and it was a good job for camaraderie and people working together. I was pretty proud to be working on the West Coast.
On October the 15th, 1970, 2 years into construction, Tommy and the team were working on the western side of the bridge, between piers 10 and 11.
That day was a Thursday, which in them days was payday, and everybody was excited. And we were transporting steel across, and I was working down the bottom, getting ready for lunch.
Up on deck, workers were preparing to attach the two half boxes that would form the span.
It was 10 to 12. Some people were on the toilet, some people were washing their hands, some people were in the lunchroom. I just turned around and I heard the biggest crack I've ever heard in my life, and I looked up and the whole lot just came down 100 metres from me.
With workers still on top, the entire 111-metre span between piers 10 and 11 collapsed.
You could see the bridge actually snapping in the centre. You could see bolts coming off. The concrete piling was cracking.
Around 2,000 tons of metal and concrete crashed to the ground and into the water.
I've probably seen 5 of my workmates either fall or jump off the bridge on the way down, and then an almighty thud just hit the ground.
They had shelters for the workers under the bridge. Some of those were squashed. People were thrown off the bridge, and the disaster happened.
The impact shook buildings hundreds of metres from the disaster, and the noise was heard around 20 kilometres away.
I just ran towards the bridge and it was just chaos. You realise that your workmates, the people who are friends of yours, were in that structure somewhere. I've never been in a war zone, but it's probably the closest I've ever been.
The catastrophe sent shockwaves across Melbourne. Local resident and construction worker Danny Gardner soon heard the devastating news.
You could not believe it. It was an absolute disaster. A lot of the people lived around here. You know, we knew who they were. And when you see that sort of tragedy happening, it was absolutely, can't put it to words.
This was the worst construction disaster in Australia's history. 18 workers were injured, and tragically, 35 lost their lives.
Oh, it was terrible. It was just something that came out of the blue, and it happened so quickly. And those sort of things, they just never leave you. You think about them all the time.
The tragedy left the nation in mourning. A royal commission was set up to investigate just what had gone wrong, and in August 1971 released its report. No blame was attributed to any one party, but the reasons behind the tragedy ranged from mistakes to miscalculations, errors of judgment, and failures of communication. Ken visited the site 2 months before the collapse.
I asked the engineer who was giving me a tour whether I could go up on the steel section, and he said, no, we've got some problems. So already I was a little bit horrified. To me, to build a box girder in 2 longitudinal halves and hope that the flanges would join at the top, you just wonder what people were thinking.
When the 2 halves of the span were rolled into position, ready to be joined, workers discovered that they were out of line by more than 11 centimeters.
Part of the problem was to try and get them to join. So they needed to tweak the boxes to try and get them to join together.
When you're talking about huge steel spans that are well over 100 meters long, 11.5 centimeters might not sound like much, but in engineering terms, it's huge. These girders had to line up.
To realign the girders, the decision was made to weigh them down with 7 8-ton concrete blocks. But the extra weight caused the steel to buckle.
The steel just wouldn't go back to the position it was. And the concrete blocks really, they didn't work, so we pulled them all down and sent them away on trucks.
One of the solutions that was made was to tweak a couple of bolts to get a little bit of flexure in the boxes themselves.
To try to straighten the buckle, 30 bolts that held the girders in place were loosened and removed.
They took the bolts out and the bridge bent and collapsed, and having started to fall, the end of the bridge over the river then knocked down the pier as well.
Because the steel was under so much tension, it just snapped. I found out later that the steel had turned blue. They lost the holes. They're trying to put the bolts back in the holes.
In 1972, construction resumed, with many of the surviving workers returning to finish the job, Tommy included.
I started the job, I wanted to finish it. My mates got killed on a project that wasn't completed, and I wanted to complete the job for them too. The job had to be completed for the memory of the 35.
The steelwork was strengthened, temporary piers put in place, and based on calculations, this time no more than 2 bolts would be removed at any one time. Danny Gardner joined the rebuild as a rigger.
I am absolutely proud of working on the Westgate Bridge. I'm proud to be part of an iconic structure in Australia. A lot of our construction men who were killed in it were friends of ours. And that was a sense of finishing a job that unfortunately some of our friends' fathers couldn't finish.
More than 40 years later, the West Gate still stands proud as a vital crossing for the city and a memorial to the workers who tragically lost their lives.
When I go over the bridge, I think about them all the time, and you end up in a traffic jam and the traffic stopped, and you sit on the actual section that's collapsed. And that's the time I really think about the people's names.
My view of looking at the Westgate Bridge even today, standing here, I treat it as a monument of the men who were killed that fateful day. And if you look at it, it's a monument to them.
When engineering leads to catastrophe, the problem can be easy for all to see. But sometimes the most obvious suspect might not be to blame. Like this disaster in Oklahoma that literally made the earth move.
It seemed like it shook for at least 2 minutes.
As shocking swarms rocked the ground.
It's hard to believe that human activity caused this chaos.
Big engineering was in the firing line.
I just had visions of the entire downtown being leveled. Just feared the worst.
In the Green Country region of northeast Oklahoma sits the rural town of Pawnee. Brad Sewell is former mayor.
Pawnee is a small agricultural town. There's a lot of ranchers in the area. And really there's a lot of character and a lot of history in this town that's worth preserving and celebrating.
One important part of Pawnee history dates back to the time of the dinosaurs.
Millions of years ago, this area was underwater. Organisms die and eventually, over time, create products like oil and coal and so forth.
Oil was first discovered here in 1859 and quickly became big business.
People rely on oil for the economy and also oil-based products, cars and different things like that.
For decades, Oklahoma was one of the nation's leading oil producers. But by the 90s, reserves were becoming harder to tap.
In the good old days, prospectors would strike oil and out it would gush. But there's a lot more oil and gas underground that's trapped by complicated geology in so-called shale rock.
Engineers worked out decades ago that they could extract hard-to-reach oil and gas by fracturing the rock with high-pressure fluids. It's what we know as fracking.
Fracking starts like conventional extraction, drilling a deep vertical well, but that's where the similarities end. When drilling reaches shale, most wells turn horizontal and can extend for more than a kilometre. Next, special fracking fluid is pumped in under high pressure, fracturing the rock, releasing oil and gas, which flows back to the surface. From the late 90s, fracking operations opened up across Oklahoma, and state oil and gas production was back in business. September 3rd, 2016 started out as a regular day in Pawnee. Local rancher Mike Haslip was heading home when he got a surprise.
I had stopped to get a cup of coffee and a bite to eat, and that's when I felt the earthquake, and it seemed like it shook for at least 2 minutes. Of course, I had no idea where it was occurring. And I get in my truck and start heading back, and about 5 minutes later I get a call from my then wife that told me that the earthquake had badly damaged our house. She said, "Wait, I've got to go. It looks like the barn's on fire." And by the time I got here, the fire department was here. There were fire trucks putting water on the fire. I have gasoline and a diesel tank, and they were trying to keep that from blowing up.
Mike wasn't alone. The quake had wreaked havoc across Pawnee and beyond.
It was frightening at the time because, I'd never experienced anything like that. And during the quake, I was wondering, is the house going to fall down on us? It was just really unexpected. I came right down this street, and this was the first building that I saw. And it was the most heavily damaged downtown building. And this facade right here on the south side had all fallen down.
Pawnee had been hit by the most powerful earthquake in Oklahoma history, measuring 5.8 on the Richter scale.
5.8 is a proper earthquake. Experts would classify it as moderate to strong. That's seriously shocking when you're nowhere near a major fault line.
In the wake of the devastation, the people of Pawnee were looking for answers. The most obvious suspect was fracking.
Well, the process of fracking, that has the effect of lubricating fault lines. And so areas which were formerly relatively stable suddenly they don't have the resistance, and so you have the likelihood of earthquakes happening.
With no fault lines near Pawnee, there had to be another explanation. And there was. The problem wasn't extraction, but the cleanup process. Geoscientist Xiaowei Chen studied the quakes.
This earthquake is related to wastewater disposal, and the wastewater is a byproduct of oil and gas exploration in this kind of area.
Fracking uses millions of liters of fluid to fracture the rock. It also helps flush the oil and gas back to the surface. The problem is, all that fluid, called wastewater, is now contaminated. It has to be disposed of somehow.
For 1 barrel of oil, they will produce about 5 to 7 barrels of water, and those wastewater need to be disposed or get rid of. The most economic way to get rid of wastewater is to inject back into a deeper subsurface formation.
Wastewater wells go far below the shale, so deep that the water will be forever locked out of harm's way. Or that's the theory. The problem was, around Pawnee, the wastewater was much saltier than normal.
The salty wastewater was up to 15% denser than the existing groundwater, meaning that it could penetrate deeper into the earth, creating greater pressure on the surrounding rock.
The wastewater is being injected back into a deeper formation, and the formation here is about 1 kilometer deep. And this deeper formation is very close to what we call a crystalline basement that is brittle and can host earthquakes. So the problem here is that the injected water is close to the basement rock.
The so-called crystalline basement rock is hard and brittle. If you pump in unusually dense wastewater, the ground shifts.
It's ironic that the fracking process itself was relatively safe, but the leftover water wreaked such havoc.
The 2016 Pawnee earthquake might have been the biggest, but it was just one in a swarm of hundreds of quakes that started back in 2008. This wasn't a one-off.
Following the quake, residents demanded action, and state regulators ordered a reduction in wastewater disposal.
Hopefully, a combination of increased knowledge, monitoring, and regulation will bring a more stable future for the residents of Oklahoma.
This is a community where people have lived their whole lives, and it continues to charm visitors and residents alike. And I think it's worth preserving, and I'm glad that it survived the earthquake.
With big bridges, engineers strive for standout design. But when they get the materials wrong, the results can be catastrophic. Like this close call in Ontario, on a vital freeway bridge.
Late afternoon, transports were going north and south. All of a sudden, there was a loud crack.
A decades-old design flaw that nearly led to tragedy.
It was obvious we had to report this there. It was major catastrophe.
This fail was far too close for comfort. Latchford, deep in the interior of Ontario, is proud to be one of the smallest towns in the province. George Lefebvre is former mayor.
It's a great place to live, and it's a beautiful location. We're nestled here along the banks of the Montreal River and Bay Lake. We're surrounded on 3 sides by water, which is quite unique.
The only way south out of town is over this 110-meter bridge.
It's extremely important because it's a landmark for our community. It's a monument to Sergeant Aubrey Cousins, one of Canada's 16 Victoria Cross winners in the Second World War, who was born here in Latchford. It certainly is a big deal in the town.
It's not just a big deal for Latchford. This bridge carries one of Canada's most important highways over the Montreal River.
This bridge allows Canada to be connected. Basically, it's a northern route of the Trans-Canada Highway, and it's absolutely vital to keep this connecting link to the north. Those magnificent arches are unique along number 11 highway.
Latchford's iconic crossing is what's known as a tide arch bridge. Although much bigger, Toronto's Burlington Skyway works the same way. Civil engineering professor Lydell Weeb explains.
Just like the Cousins Memorial Bridge, this is an arch-type structure. And the job of the arch, this curved part going over the top, that's really what's doing the work of carrying the load. The deck that holds the bridge, it's hanging from these hangers. They carry the load up to the arch, and then the arch carries it down to the piers on the two sides. The hangers are critical to this bridge because the deck can't carry the load by itself.
Bridge hangers do exactly what the name says. They might be steel bars, cables, or box girders, but whatever the design, the bridge deck literally hangs from them.
Latchford's bridge originally had 12 hangers on each side, suspending the deck from the twin arches. The hangers were connected top and bottom with giant bolts called pins. These connections allow the deck to sway with the movement of traffic.
Steel is super strong for supporting structures. But if you keep bending it and working it, the metal can start to fatigue. So lots of bridges have flexible connections built in. They are crucial to durability and safety.
Aubrey Cousins spanned the Montreal River from 1960. But after more than 40 years of loyal service, it faced a serious challenge. On January the 14th, 2003, during a ferocious cold snap, Jocelyn Roy was doing what he loves best, driving his rig cross-country.
Truck always been a part of my world. It's in my blood, this kind of truck here. Right now we're heading north. That's the direction I was heading to Oshawa.
Temperatures were 30 below zero, but Jocelyn was on a roll.
So just as I pulled on the highway, another big truck was following me. It was a logger. Like we were coming on a good pace there. And right about here, it was right as we entered the bridge there. I heard a big boom. I thought I had a flat tire, so by the time I looked in my mirror, a bunch of snow fell, and when I looked ahead, my eyes kind of went down with the snow, and I saw the bridge that was collapsed.
The deck had dropped 2 meters towards the freezing Montreal River.
I bounced, I hit the roof, but then by the time I stopped, it was almost like 1,000 feet past the bridge. It was obvious we had to report this there, and it was major catastrophe.
Well, the deck of the bridge had dropped down. Basically, if you have a situation such as that, and if the traffic isn't stopped, death could occur. Much greater damage could occur to equipment, to vehicles. Anything going over the north end would have dropped into a gap, and anything coming from the south end would eventually have reached that point. The big concern was to ensure that nothing was coming north. Got it stopped, reported everything to the police. So it was a lot of reaction by a very few people to ensuring that safe passage was assured and that no vehicles got onto the bridge and caused further damage.
The bridge had failed. Luckily for Jocelyn, it didn't fully collapse.
The key is the word, because the way the collapse happened there, it kind of went in a V there, like maybe 4 feet on one side and 6, 7 feet on the other side. So it was just a slope, a big slope. And I was lucky. It could have been a straight fall right into the concrete pier.
But with the bridge down, motorists faced a mammoth 3-hour detour.
This might have been a relatively small bridge in a very small town, but the impact of the collapse was enormous.
People had to detour. They had to go down through Quebec or go over to Highway 144. Of course, for commercial transportation, they need special licensing to go through Quebec. So it was a real problem. All of a sudden, we'd lost our connecting link between northern Ontario and southern Ontario, between western Canada and eastern Canada. This is the Trans-Canada Highway. Well, it was a bad day for the whole northeast.
Frustrated commuters wanted to know what had caused the sudden collapse. At just over 40 years old, the bridge should have safely carried traffic for decades to come. Engineering professor Lydell Weeb explains.
When you build a bridge, for sure you intend for it to last. It's very rare to have this kind of failure. When I go over a bridge, I'm not worried that it's going to collapse underneath me.
The reason for the failure was blindingly obvious. 3 broken steel hangers.
So the hangers are what are carrying the load for the bridge, and those hangers, over a number of years, they fractured. There were a few kind of stages to it. The first hanger is the one that seems to have gone first, and it seems like it fractured first and wasn't noticed for years.
Once one hanger failed, it was just a matter of time before a second, then a third. It might have taken years, but that bridge was only going in one direction, down.
The big question was what had caused them to fracture in the first place. On the day of the fail, temperatures had plummeted 30 degrees below freezing.
Temperature has a big impact on the performance of steel. Basically, when warm, it can be flexible. It can deform without losing its strength. It's called being ductile. But below a certain temperature, it loses that ductility and becomes brittle. Instead of flexing, it can crack.
But this area is no stranger to extreme cold, so investigators knew there must be more at play. Then they found something unexpected inside the arch span.
At the top of the hanger rods, where they were kind of hidden inside of the arch, there's a threaded portion, just like at the end of this bolt, and there are nuts on top of there to hold it in there. What the investigation showed was that for some reason, someone had filed down some of the threading in there. The reasons for that aren't totally clear. It could be to get rid of some defect that they saw, or it could be that that created a defect. But whatever the cause, that was where the fracture started, in the critical hanger rod.
Having located the source of the fractures, investigators realized why the damage hadn't been detected earlier.
When the bridge was built, the top of the hangers were enclosed inside the steel arch spans, so they couldn't be inspected, and the damage was never spotted.
Further investigation revealed yet another factor. The pins that should have allowed the hanger rods to sway were corroded solid.
What had actually happened is that the pins had seized, and so we start getting this kind of response in there. And you can see that when we do that, there's a lot more stress on the hanger.
With seized pins, the steel hanger rods were forced to flex rather than sway. It didn't take long for metal fatigue to set in.
Steel fatigues when it is repeatedly stressed or strained. If it happens over and over at the same point, the metal starts to degrade or fatigue, and ultimately it will crack.
What happens in that case is something like what happens with a paper clip. If I take a paper clip and I start bending it back and forth, I'm not strong enough to break this on my own in one go. But if I go back and forth several times, eventually this paper clip will break.
Damaged hanger rods subjected to decades of fatigue combined with the extreme cold finally pushed the bridge to breaking point.
So over a number of years, for all of these different reasons that we've talked about, we had one hanger that failed, and then that lasted a few years with no one noticing, and then another one failed, and again no one noticed. And then when the third one went, that was really what led to the failure.
The 43-year-old bridge was beyond repair. But with 5 decades of new engineering knowledge to draw on, and lessons learned from the failure, the replacement is built to last.
With the new bridge, the solid steel hangers were each replaced with 4 steel cables. So not only are they more flexible, but if one should break, the bridge will continue to function safely until it can be repaired.
Today, the Aubrey-Cousins Memorial Bridge is once again carrying Canada's cross-country traffic in safety. And Jocelyn Roy is still trucking.
Yeah, I was lucky. We were all lucky. Actually, nobody got hurt on this one.
The people who drove over that bridge at that time are very, very fortunate and extremely lucky that they are alive today.
It's crucial that engineers learn from the past so they can build a safer future.
Devastation rocks a small town in the heart of North Dakota.
A massive ball of smoke and flames. I have never seen anything like this ever.
Tragedy in Taiwan on an iconic bridge.
The cables began to snap. It was like fireworks going off.
In Kansas City, catastrophic collapse at a state-of-the-art stadium.
The bolts of the hangars breaking, fracturing, cascaded down.
And in Canada, a bridge crashes down onto a major highway.
People were very lucky that they weren't underneath the bridge, as it would have been catastrophic.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Some engineering errors lie undetected for years, a ticking time bomb waiting to go off. Only when they fail do we realize that we were in danger all along. Like this remote railroad disaster in North Dakota, which rocked an entire community.
The force of the explosions, it was unbelievable.
The huge fireballs threatened a small town.
You could be a quarter-mile away and feel that heat coming off of it.
And revealed a potentially fatal flaw lurking in the nation's rail cars. North Dakota, a vast flat state that boasts some of the richest soil in the world.
You're fine.
Photographer and farmer Dawn Ford has been working the land around the town of Castleton for nearly 40 years.
Agriculture has always been the most important part of North Dakota. It keeps the businesses rolling. Agriculture has been king.
Around 90% of North Dakota is farmland. That's equivalent to 30 million football fields, or 4 times the size of Switzerland. It's one of the top grain producers in the country.
In 2000, grain was rivaled by newly discovered oil in the so-called Barken boom. Named after Henry Barken, on whose farm the first exploratory wells were drilled, the oil is extracted by a process known as hydraulic fracturing, or fracking.
The Bakken boom was huge. We had people coming in from all over the country. We had a housing shortage out west.
The high-quality crude became known as North Dakota Sweet.
It is that pure that we were told that you could probably put it in your diesel pickups and be able to operate them on pure Bakken oil.
Oil production was soon second only to Texas. Thanks to years of grain transportation, the infrastructure was already in place to get the valuable cargo where it needed to go.
The railroad goes straight through the middle of town. All you saw was the oil tankers going past. The United States was built around train tracks when you think about it.
Key to a railway's success is the ability to carry massive loads long distances. The most vital component is the wheel set. Each set has 2 steel wheels connected by a solid steel axle. At each end, roller bearings hold the axle in place on the truck, allowing the wheels to rotate freely. But these trains carry massive loads, and the stresses on the axles and bearings are enormous. The forces might be huge, but the setup is simple. John Hale is a local rail expert.
The axle just carries the weight of the train. That's really all that holds that together. It's just gravity. And so all it's meant to do is lessen the friction as the train rolls down the track.
By 2013, North Dakota was rolling out millions of barrels of oil a week.
In 2009, there was something like 9,500 rail shipments of crude oil in the United States. And in 2013, it was somewhere in the neighborhood of 400,000.
With both grain and oil now rumbling across the plains, up to 50 trains were passing through Castleton daily, some loaded with more than 13 million litres of crude. On December 30th, 2013, at 2:10 p.m., a grain train hauling 112 cars was heading west, more than 1.5 kilometers out of town, with the onboard camera recording.
A trackside engineer saw damage that suggested something was being dragged along the rails, and he immediately radioed the crew.
Without warning, the emergency brake on the grain train kicked in. Meanwhile, a 104-car train, loaded with bark and crude, was heading in the opposite direction.
The grain train crew sent an emergency warning, but the oil train's radio was on a different channel, and they heard nothing.
What neither crew knew was that 13 cars in the middle of the grain train had derailed, blocking the track ahead. By the time the oil train driver saw the wreck and hit the brake, it was too late. Both locomotives, a buffer car, and 20 tankers loaded with crude oil derailed. Volunteer firefighter Paul Fort was expecting the worst.
When you first hear a call like that, your heart drops just a little bit because it's like, oh, how bad is this? And then you start to just pick yourself up and say, I got a job to do and we need to go do it.
Paul's sister-in-law, local photographer Dawn, was heading into town at the time.
A few miles out, we saw the first explosion. And we drove to approximately 3/4 of a mile from the actual derailment, and I started taking photos.
What Dawn captured was the stuff of disaster movies.
Huge columns of smoke and flames and heat coming back at us. Big black smoke billowing out of it.
The derailed tankers had ruptured, and more than 1.5 million litres of crude were gushing onto the tracks. Paul and the team knew they had a major disaster on their hands.
You start seeing that much fire, it's how bad and how big is this going to get, and what are we going to do to control this?
More than 80 cars full of highly explosive crude were still attached to the train, just feet away from the inferno.
We had people looking at disconnecting the fuel, taking the train away.
One of our friends was with the train engineer, basically belly crawling up to the cars as far as they could so they can unhook, and then the other locomotive pulled them back out of the way to stop all of the chain explosions.
These heroic actions helped slow the spread, yet the wreckage still burned throughout the night. The only thing preventing human tragedy was the fact the accident occurred more than 1 kilometer outside town.
We were all so fortunate that the derailment happened where it did, in an empty field, versus the city of Castleton.
In the immediate aftermath, an investigation was launched to discover exactly what had gone wrong.
There's no doubt what caused the inferno. The force of the derailment ruptured the tankers, and once the oil caught fire, there was no stopping it.
But that didn't solve why the grain train derailed in the first place.
At first, investigators didn't know whether track or train was at fault. Then, in the devastation where the derailment began, they discovered a broken axle.
When you see the scale of the explosions, a broken axle doesn't sound like a big deal. But this one had an unusual hole in the middle. It was smaller than a golf ball, but it was the best clue that the investigators had.
Investigators traced the void back to 2002, 10 years earlier, and a defect from the original casting process. When made, it had been tested for flaws, but back then there was no requirement to look deep inside. And yet, further analysis revealed this small hole had triggered the entire catastrophe. With a solid axle, stress forces are distributed equally. But this central void, although small, had a jagged shape, which created uneven stresses, causing metal fatigue, until finally, a decade later, the axle failed.
This axle was a ticking bomb. It had been trundling across the rail networks for years, getting weaker with every stress and strain from heavy loads. It's just so lucky that when it finally failed, it was a mile outside Castleton.
In the wake of the disaster, there were multiple recommendations for safety improvements.
At the time of the accident, new axles were routinely being examined with ultrasound. But the rules were changed so that second-hand axles would have to be inspected too, which would have revealed a flaw like this.
And to prevent rupturing in the event of another derailment, tanker cars are being made more robust, with thermal protection and pressure relief valves.
Railcar design changed. They wanted railcars to be built thicker, and they wanted more safety parameters put on their valving, just making them safer to haul product.
With safer rail cars and more thorough inspections, disasters like this should be a thing of the past.
There's multiple things that were learned at this incident. Nobody got hurt. As firefighters, we can go out there and look at this and say, you know what, I think we can handle it. And that's why there's so much more training going on for incidents like this. And I think that's great.
It's definitely a once-in-a-lifetime experience, and one that I hope I never witness again.
As they battle with Mother Nature, engineers are constantly striving for ever more unique designs. Get it wrong, and innovation can lead to catastrophe. Like this disaster in Taiwan that ripped through the heart of a community.
The cables began to snap. It was like fireworks going off.
A state-of-the-art bridge destroyed in seconds.
This triggered a major rescue operation involving the Coast Guard and the military.
The tragedy revealed a hidden design flaw.
Hundreds of tons of steel and concrete came crashing down. The destruction was devastating.
The island of Taiwan, on the western edge of the Pacific Ocean, boasts Asia's top-performing economy and is one of the most technologically advanced places on Earth.
Taiwan is well known as the world's leader in computer chip technology, but it also has one of the world's largest fishing industries.
Nestling in the shadow of the central mountain range lies the port of Nanfangao, home to one of Taiwan's biggest fishing fleets. Chun Sen-chan is the executive secretary of the Fishermen Association.
是东部最大的渔港，也是全省3大渔港之一。我们本会的会员总共有16200多个会员。我们的渔船船只大概有800多艘的一个渔船的船只。
In 1996, construction began on this 140-meter harbour bridge to allow larger vessels in and out, as journalist Philippe Charlier explains.
The old bridge was too low, so only small boats could get in and out of the harbour. And the one that was built at Nanfangao Harbour was unique.
The new bridge would be the first bifurcated single-arch bridge in all of Asia, and only one of 2 in the world.
Bifurcated simply means split into 2 branches, much like a fork in the road. What made this bridge stand out is that the arch itself was split into 2, a bit like a wishbone, creating 2 legs on either end.
It was designed to be strong in terms of being able to withstand earthquakes and typhoons, but also to be aesthetically pleasing. because this is a very popular tourist area.
Professor Chung-Chae Chu from the National Taiwan University is an expert in bridge and earthquake engineering.
Nanfang Ao Bridge is a beautiful and a simple structure. A single span steel tied arch bridge because we don't want to have the current in the water to block the fishing boat passing through the harbor. Therefore, we use the two bifurcated legs. This is very important, especially for resisting the earthquake load or the wind load.
To keep the harbour entrance clear, this unique bridge supported the deck from the single arch above with 13 steel cables or hangers, anchored to bucket-shaped steel troughs between the roadways.
The bridge deck is supported by the cable, which transfers the bridge weight and the traffic load into the arch.
Completed in 1998, for the next 20 years, traffic flowed smoothly both under and over it. On Monday 30th of September 2019, Typhoon Mitag hit the coast of Taiwan, with winds of up to 140 kilometers an hour.
There was a typhoon that swept past the northeast coast, and it created considerable sway on the bridge.
But Mother Nature wasn't done yet.
In the early hours of the morning, there was an earthquake of 3.8 magnitude.
By dawn, life was returning to normal, but all that changed at 9:30 a.m. $320 tons of bridge and a tanker truck fell suddenly and without warning around 18 meters into the water below.
That one truck set off a chain reaction, causing the bridge to go down in seconds.
There were 3 fishing boats moored under the bridge with crew aboard.
There was no warning and no chance to escape. A massive rescue operation was launched, led by the Taiwanese military.
It involved the Coast Guard, the National Airborne Service Corps, and Navy and Army divers.
With members of his fishing community in trouble, Executive Secretary Chun Sen-Chan went to work.
第二个，我们成立了一个由推广课成立一个前进指挥所，整个地方上的一个重要的位置的一个，再来就是清查断桥之后，桥下有3艘渔船。
More than 200 people spent 3 days searching the wreckage. Incredibly, the driver of the tanker truck was rescued, and although injured, survived the disaster, along with 12 others. But not everyone was so lucky. Tragically, 6 people on board the boats died.
全部把他找到，虽然不幸的罹难，但是我们也非常尊重他的大体，把他做了很大的一个处理。
An investigation was launched to find out why the bridge had failed so catastrophically. Taiwan's leaders wanted answers, and no stone would be left unturned.
2 days after the collapse, Premier Su Zhen-Chang ordered an investigation and ordered inspections of all the bridges in Taiwan, which number over 20,000, to prevent this happening again.
The first question, had the typhoon or earthquake caused the collapse? Not so, says Professor Chung-Chae Chu, who was on the team.
No. The bridge was standing there for almost 20 years. Then the bridge failed, so that means there's a system-level damage. So probably due to the environment effect, not due to the single event effect.
The bridge had withstood years of typhoons and quakes. The next suspect was less dramatic, the harbor's salty environment.
Investigators wondered whether the collapse could have been caused by the very thing the bridge was designed to cross, the sea.
If we look at this damage part, it's damage due to corrosion of the tendon. So with a salty environment, so tendon rupture may be the major issue.
Engineers discovered that water was leaking through the unique bridge into the steel pockets that anchored the tendons.
You can see the tendon needs to be anchored on the girder. So the engineer built a steel bucket in order to hold the tendon. But after many years, this steel bucket becomes a good place for the water to store up.
As salt water collected in the anchor points, the waterproof seals on the metal pockets gradually hardened and cracked, as did the tubes covering the steel cables. This allowed rainwater to leak into the anchoring mechanism, weakening the entire structure.
Further investigation revealed there were no drain holes.
The tendon is hanging there, and we don't see the drainage for the steel bucket. So that's become the worst design for this case.
The salty water was trapped and slowly corroded the steel tendons. As this investigation test shows, they simply didn't have the strength to hold on any longer.
Once the first cable gave way, the next, which was also badly corroded, failed, and so on in a domino effect along the bridge, which brought the whole structure down in seconds.
The investigation found other factors had contributed to the collapse, from construction techniques to routine maintenance regulations, which hadn't required examination of the anchor points inside the bridge deck. This meant the problem went undetected for nearly 20 years.
Inspections were carried out between 1998 and 2016. However, the anchor supports for the cable were concealed in the deck of a bridge. And unless you had special engineering training, you probably wouldn't know that you needed to look inside to check for corrosion.
After the collapse, all bridges with cable supports were checked, and from now on, bridges with a unique design, like the one at Nanfangao, will only be inspected by specially trained engineers.
The bridge in Nanfangao was crucial to the community, and just over a year after the collapse, construction began on its replacement.
The groundbreaking ceremony for the new bridge occurred on October 5, 2020, and it's due to be completed in August of 2022.
When finished, the new bridge will be a more conventional concrete structure with no arch.
This incident should have been prevented. We just need to remember this lesson and really do the examination to make sure the problem of the tendon corrosion can be prevented.
Hopefully, once again, Taiwan will be blazing a trail with cutting-edge and eye-catching engineering. In the mission to create ever more spectacular builds, engineers are constantly thinking outside the box. But occasionally, pushing boundaries can come with dramatic consequences. Like this stadium disaster in Missouri that literally brought the house down.
Tons of steel hit the floor in seconds.
A pioneering structure that did battle with Mother Nature.
A huge storm blew through, and that was when the roof collapsed. That was crazy.
And revealed a hidden design flaw.
The bolts of the hangers breaking, fracturing, cascaded down.
Kansas City, Missouri was founded in 1850, where the Kansas and Missouri rivers meet, and swiftly grew into a major commercial center. Elizabeth Rosen is a local preservationist.
Kansas City is the heart of America. It sounds really cliche, but it's a place that's easy to live, it's easy to love. There's a great community spirit here.
The city owes its success to the cattle industry.
Kansas City was historically known as a cow town. This is where the cattle came in at the end of the cattle drives coming from Texas and the grazing lands.
In the 1920s, Kansas City stockyards were handling around 2.5 million head of cattle. That's enough to make more than 2 billion burgers.
By the 1970s, agriculture gave way to architecture, and Kansas City went from cowtown to city slicker with an ambitious building boom.
There was a desire to have buildings that were both unique and at the same time that were cost-effective to both build and maintain and manage. And this resulted in some really unique designs.
One building stood out more than the rest. On the site of the former Kansas City stockyards, the 17,600-seat Kemper Arena. Engineering project manager Greg Litterick explains.
Kemper Arena is very iconic and well known for its exterior skeleton and really pushing some of the boundaries of design at the time that it was put up.
This revolutionary design, covering more than 12,000 square meters, gave fans what they'd always wanted, an uninterrupted view of the action.
The uniqueness about this structure, because of the exoskeleton, is that there's no columns right now in this space. If you look around, there's nothing to get in the way of people being able to see the events that's going on.
The space-age exoskeleton is aptly known as a space frame. When originally built, it looked a little different, but its purpose was the same, to support the roof from above. 3 giant steel space frames rise 24 meters up, then extend around 115 meters over the building, supporting 42 hangars connected to a lattice of joists and trusses, with high-density foam roof panels sitting above.
This system makes it so that the roof basically floats over the top of the bowl and is not reliant on the bowl for its support, nor is the bowl reliant on the support of the roof to hold itself up. They have hangers that come down and actually support the roof beams from above. And so now we don't have deep trusses inside the event center, and we don't have any columns.
The roof didn't just offer uninterrupted views. On top, it acted like a giant reservoir to catch rain from summer storms, releasing it slowly to avoid overloading the city's sewers.
The idea was that the roof would catch rain until it reached a depth of around 2 inches or 5 centimeters. Then the water would be slowly released through 8 intentionally undersized drains. Think of it like a large bath with 8 small plug holes.
The arena opened in 1974 and was a huge success. Groundbreaking at the time, it even won an award from the American Institute of Architects for its innovative design.
It was a really unique design. We talk about thinking outside the box, and this whole building is outside the box.
The Kemper Arena was home to ice hockey, NBA basketball, even the King Elvis Presley played here, twice.
Pretty much anybody who grew up in Kansas City from the mid-1970s through the 1990s has a memory of Kemper Arena, of a concert they saw, of a show they attended, and it means something to them.
Growing up in the area, I came to see several concerts. I came to see several rodeos. So this place personally holds a lot of very good memories for myself and my family.
On June 3, 1979, the arena was hosting the American Institute of Architects' annual convention. The following day, a storm rolled into Kansas City.
A big classic Kansas City spring storm blew through the area. There's a lot of heavy rain in a very short period of time. We sometimes get tornadoes. They can cause a lot of damage.
The storm intensified with torrential rain and gusting winds of around 110 kilometers an hour.
Around 6:30 in the evening, one person in the arena started to hear strange noises. As he got closer into this space, he started to hear what he called explosions and ran out.
This was no explosion. At 6:45 p.m., as the employee fled from the arena, a 60-meter section of the roof dramatically collapsed. Tons of twisted steel and roofing fell more than 20 meters to the arena floor below.
The amount of steel and the amount of water, it was this center section, approximately 1 acre of the roof came down.
The collapsed section was so big and the roof came down with such force that the air pressure blew some of the walls apart.
Fortunately, the arena wasn't in use at the time. If the collapse had happened just 24 hours earlier, ironically, thousands of architects would have been inside.
That was crazy. The timing, the coincidence was incredible.
Luckily, no one was hurt in the disaster. But when the dust settled, big questions were being asked. In a building designed to withstand Kansas City's stormy weather, how had this disaster happened?
It had survived much bigger storms, so the obvious question was why, on this particular night, did it fail so catastrophically?
Professor of Engineering Norb Delat explains.
One thing you might wonder is if the roof is designed to hold water, why didn't it hold the water? That's what it was made for.
Some experts initially believed the answer could lie in a phenomenon known as ponding.
The problem is if the roof is too flexible, what happens is that as it sags, it collects more water. That causes additional sag, it collects more water, and then at some point there's so much load on it that it collapses.
Water wasn't the only problem. In Kansas City's stormy weather, the design may have underestimated the effect of the wind.
In a windstorm, which is what we had at Kemper Arena, is the water's getting pushed around all over the place, and it may find a low spot and it may find a weak spot.
The problem was storm winds were swirling the water around, and instead of draining, it started to pond unevenly around the roof, causing localized stress.
The roof weighed about 1,200 tons, and at the time of collapse is holding about 1,200 tons of water.
Further investigation found that it wasn't just the weather that was responsible for the collapse.
The heavy rain and swirling winds caused the roof to swing back and forth, highlighting a structural flaw within the hangars that had been there for 5 years. The type of bolts.
These were high-strength bolts. And when you use a high-strength material, typically you sacrifice something to get high strength. And what you sacrifice is the ductility, the ability to stretch, the ability to absorb energy.
Each of the 42 hangars was held in place by 4 high-strength bolts, designed to work on rigid structures. But every time the roof moved, the lack of flexibility in the bolts caused the metal to weaken, until it's estimated they lost almost 2/3 of their strength.
What happened was over the time, as the water moved around, as the wind moved the water, those bolts went through cycles of fatigue, and so they were slowly stretched and unstretched, slowly stretched and unstretched. And what happened because of this type of steel is eventually it weakens the structure and can break. But it was just the phenomenon of that slow stress repeated several thousand times that broke the bolts.
The failure of just one bolt weakened the hangar, causing the other 3 to fail. This in turn overloaded the adjacent hangars, creating a domino effect, until the whole 60-meter section of the roof came crashing down.
As one broke, the next one would get overloaded and then continue to break. Sounds like an explosion, but it's really pieces of steel breaking apart.
It turned out that the bolts, although strong, simply weren't flexible enough to take the strain any longer.
Failures generally occur because you have a set of circumstances plus a trigger. The circumstances in this case were the bolts that had been weakened by fatigue over many, many years, and the trigger in this case was a particular overload of rain on this particular day.
The Kemper Arena was rebuilt and reopened on February the 20th, 1980, this time with more flexible bolts, a pitched roof, and instead of 8 drains, there were now 22.
They've changed the profile of the roof so that it doesn't store as much water anymore. It effectively is now pushing all the water off of the roof and down into the drainage system.
In 1994, the stadium grew, with more seating and an enlarged roof truss over a new glass atrium.
As part of that, they also expanded that central truss. Now the central truss steps back a little bit. It's a little bit larger and a little bit taller as it goes over the top.
In 2017, the stadium was transformed yet again with a $42 million makeover, this time into a sports facility for the whole community. Greg Litterick was project manager.
Personally, I was very excited to be part of this project to bring this arena that had been such a prominent role in my life growing up to now being able to revitalize the arena and make it again a place for the community to gather. I am very proud that this arena is still here and that we've given it a new lease on its life.
It's an iconic part of the community, and it's really embedded in the community's soul.
The arena came back better and crucially stronger than ever. Once again, rock legends could raise the roof without bringing it down.
And maybe this time, proud Kansas Cityans can create a few stars of their own in this very special part of town. With every project, engineers have to strike a compromise between safety and strength. If the balance is off, the consequences can be dramatic. Like this sudden collapse in Ontario, a renovation project gone badly wrong.
This was a major freeway and it was still open.
Miscalculations brought a bridge crashing to earth.
People were very lucky that they weren't underneath the bridge, as it would have been catastrophic.
Sudbury, Ontario, sits on the edge of a giant hole in the earth. Its origins are literally out of this world. Julie Moskalik, director at the Dynamic Earth Science Center, explains.
About 1.85 billion years ago, there was a meteor that struck this region. So we are standing in the world's second largest and second oldest meteor impact structure.
The impact forced precious metals from deep in the Earth's crust up into the crater rim.
So we're on the south rim of a basin that is about 80 kilometers by 30 kilometers. And all along the rim of the basin are these very rich nickel-copper mines. For nickel, it is one of the richest areas in the world.
Nickel is hugely important to the modern world, and it's used in everything from cell phones to armor plating. But it's best known for making money.
In the 1960s, Sudbury's epic nickel mining industry was celebrated on a massive scale.
This is probably the most iconic structure that you'll find in Sudbury, the very famous Big Nickel, made of almost pure nickel and symbolic of the famous nickel mining history that you find in Sudbury. I bet you that the majority of the Canadian nickels that you hold in your hand, that metal, came from this region.
This is the world's largest coin, and from day one became a draw for locals and travellers on the nearby Trans-Canada Highway. Most of them arriving via the Big Nickel Mine Road Bridge, a single-span concrete beam design.
A beam bridge is basically what it sounds like, as simple as a fallen tree crossing a stream. In the modern world, it's normally a concrete girder resting on two supports or abutments. It's one of the most basic types of bridge.
The bridge was constructed at the same time as the giant coin, but after decades of wear and tear, the aging concrete was in need of some TLC. In March 2006, the bridge to the Big Nickel was closed for renovations.
The main structure itself was in decent condition, but the ends of the deck and the abutments needed repair. It was also a bit low for modern traffic, so this was an opportunity to not only renovate the bridge, but raise it too.
The plan was to lift the bridge vertically clear of the work site. Steel girders bolted to the abutments would support it while the sides were raised and the bridge ends repaired. The bridge would then be lowered back into its new elevated position.
Using temporary structures to support a bridge is common practice. Because they'll be removed once the bridge is complete, they're known as false works.
False works might be temporary, but they're vitally important. Professor of Engineering Lydell Weeb explains.
You're repairing a bridge and you're starting to change the way that the forces flow through that bridge. You're relying on the false work to carry the load while you're doing those repairs. And so it's critical then that the false work is able to carry the load.
But like every project, engineers had to balance strength with safety.
There's a saying that an engineer is someone who can do for $1 what any fool could do for $3. You're repairing a bridge, so you're always trying to balance something that is strong enough that it's not going to collapse, but not so over-designed that you're wasting materials.
The road below Municipal Road 55 is a key artery in and out of Sudbury, so the plan was to renovate the bridge without closing the freeway.
The renovation would take time, but closing the freeway would be massively disruptive, so doing it all in situ was the best solution.
Repairs went ahead and traffic continued to flow freely. On the morning of May the 7th, 2004, Sudbury resident Grant Garber was working nearby.
Well, that day, and I happened to hear a noise come from the bridge. I happened to glance over, and the southern end of the bridge collapsed.
The Big Nickel Bridge was down.
Vehicles that were about to go underneath the bridge were stepping on their brakes, avoiding debris. There's ambulance, fire trucks, police cars show up at the scene there. It was chaos.
Imagine driving down a freeway and the bridge in front suddenly collapsing. It must have been terrifying for motorists.
So you don't see that every day. You don't see something that's supposed to be structurally sound while under construction. You don't see it just collapse out of the blue like that.
Despite the freeway being open to traffic, incredibly nobody was hurt or killed.
If it would have happened an hour earlier, there would have been school buses going through with children in there, people going back and forth to work. People were very lucky that they weren't underneath the bridge at the moment of collapse, because it would have been catastrophic.
The disaster severed a busy road and people demanded answers. The first suspect was the very thing that made Sudbury great: mining.
Tens of thousands of tons of nickel slag were being shifted at a nearby mine, and some said the rock movement could be to blame.
But inspection of the wreckage seemed to tell a different story. Engineers found that the false work had been subjected to forces beyond its load-bearing capacity.
An official report listed multiple problems in the support structure, from the layout to the materials, and although it stood firm for 16 days, ultimately the false work wasn't strong enough to do its job.
The false work can't fail underneath a bridge, especially if it's over top of an operating roadway. If the false work isn't able to do that job, then if the bridge isn't able to either, there's nothing that can carry the loads.
According to the report, factors contributing to the weakness included key bracing that had been made from wood, not steel, welds being used in place of bolts, and multiple changes in procedure.
If you're building any load-bearing structure, temporary or not, sticking to the design specification is crucial. A small deviation can be the difference between success and failure.
Following the accident, the bridge had to be completely rebuilt. But more than 15 years later, traffic continues to flow safely, while tourists still flock to Sudbury's big money monument, the Big Nickel.
This collapse just shows no matter how simple a job may seem, there are always lots of pitfalls along the way, and any change in the plan could be catastrophic.
I just hope to God never see that again in my life. I remember it was like it was yesterday.
Tragedy strikes a bustling Canadian shopping mall.
There was water flowing, bells were ringing. I knew it was serious.
In Missouri, a massive mountaintop dam fails in record time.
When we arrived, it just looked like a different planet.
In Australia, disaster as a towering inferno takes hold in downtown Melbourne.
This spread in less than 6 minutes to 23 floors. Unprecedented, unheard of.
And in Arkansas, an oil spill threatens an entire community.
We want to protect it at all costs.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to big construction, engineers always have to consider the elements. Fail to do so, and the results can be disastrous. Like this shopping mall in Canada that was hiding a deadly design flaw.
Once the leaking started, it never stopped. It continued until the mall actually collapsed.
An engineering disaster that left many questioning whether this could have been avoided.
They knew about it. This didn't have to happen.
And a tragedy that left a community reeling.
It was very hard to take it all in. It was pretty overwhelming.
In the wilderness of Ontario lies the remote city of Elliott Lake. Until 1955, it was relatively undeveloped.
In the 1950s, geologists discovered huge deposits of uranium, attracting mine workers from all over the globe. Elliott Lake sprung up around the mines and became known as the uranium capital of the world.
For nearly 40 years, it was a bustling mining town. But when the last mine closed in 1996, the boom times were over, and Elliott Lake had to reinvent itself to survive. Kevin McSheffrey is a local journalist.
We've gone from the uranium capital of the world to the seniors capital of Canada. 60% of Elliott Lake is over the age of 50. There's 1,000 lakes of 50-mile radius. I wouldn't want to live anywhere else. Too many people down south, and if I moved down there, it'd make it worse.
A key attraction for the aging population was its shopping mall. But this isn't the first plaza on the block. Opening in August 1980, the Algo shopping mall became the lifeblood of Elliott Lake.
Everybody met here. The food court, if you weren't here by 10 a.m., there was no room in it. It was the heart and soul of the community. There's no two ways about it.
The mall was constructed with steel beams and columns, supporting hundreds of concrete slabs, with 3 floors and a 4-story hotel incorporated into the footprint. To maximize space, the Algo Mall had a very distinct design feature. The entire roof was a parking lot.
An open rooftop parking lot isn't unheard of, but this part of Canada has brutal cold winters. Ice and snow come with the territory, so waterproofing was crucial.
Structural engineer Hassan Safarini explains.
So these are the original design drawings of 1979. It shows you the parking lot at the roof of the mall. And the most significant thing about this was the waterproofing of the concrete. When they built it, there was a new and modern approach, and that is just to seal the concrete.
The concrete panels were around 9 meters long, but only 1.2 meters wide, which meant lots of joints to waterproof.
The solution was simple. Almost 8 centimeters of concrete was poured over the entire roof, acting as a single waterproofing layer.
This concrete coating had been used, but only on much bigger slabs known as double T's, which can be 10 times the size, meaning a lot fewer joints. With the Algo's smaller slabs, this was definitely uncharted territory.
For residents, it was clear right from the start that something was wrong.
It was leaking before the mall opened. Never stopped and just got worse.
Buckets and tarps almost became part of the mall's architecture. The leaking got so bad that some local residents even dubbed it the Algo Falls.
For over 3 decades, the parking lot continued to leak directly into the shopping mall below.
This should not happen at all. But for this to persist for 30 years is totally unacceptable.
On Saturday afternoon, June the 23rd, 2012, it was business as usual at the Algo shopping mall. But all that changed in a heartbeat. At precisely 2:18 p.m., disaster struck.
This failure was so sudden, there was no warning. The car park just dropped.
Journalist Kevin McSheffrey was in the hotel theatre critiquing a play.
There was panic there because nobody knew what was going on. At first, some people thought it was part of the play. Well, nobody has sound effects that good.
They soon discovered the truth was much more shocking.
It started with the parking lot level, dropped into the second, and dropped onto the first, right there.
Elliott Lake Fire Chief John Thomas got the call.
There was water flowing, bells were ringing, parking lot was full of people, and then I looked in the window and I saw daylight, and that's when I knew it was serious.
Even for a hardened veteran with nearly 20 years under his belt, the devastating scene that confronted John was hard to take.
And we don't know how many people are actually inside. There was asphalt, concrete. Some of these pieces of slab were as long as our truck. What really struck me was to see a vehicle inside the mall.
For 2 days, firefighters worked around the clock, searching the wreckage. 19 people were injured in the collapse, but despite rescuers' heroic efforts, tragically 2 died.
It was not a good day. Anyway, yeah, it was difficult.
In the wake of the tragedy, the Premier of Ontario ordered an immediate investigation into the disaster. As the nation mourned, everyone was asking, why had it collapsed? It was soon clear that there was one main culprit: rust. Hassan Safarini was one of the investigating engineers.
The corrosion in the mall was so severe that the closest that we could compare it to was the marine environment in terms of ships. The entire section was lost that you could see through the beam because it completely corroded.
The cause was painfully obvious. Massive corrosion of a weld on one of the supporting steel beams led to the fatal collapse.
The steel had become so corroded that it only had 13% of its original load capacity left. That one car going over it was the straw that broke the camel's back.
Well, everything was corroding, but it was the thinnest member that was likely to fail, and it did.
Now, the question on officials' minds wasn't what had happened, but why.
Why was there that loss of connection between one beam and the column that led to the collapse of the roof?
The investigation found that failed waterproofing combined with extreme Canadian winters had been slowly eating the steel away for more than 30 years.
Anywhere that has freezing winters, roads are regularly gritted and salted to melt the ice. But salt and water create a corrosive cocktail, and it's very bad news if it gets into a steel structure.
The 7.5 centimeter concrete coating was simply insufficient to prevent the salt and water from running through the many joints of the narrow slabs directly onto the steel below.
Once the leaking started in the mall, it never stopped. It continued until the mall actually collapsed.
After more than 30 years of corrosion, the heart and soul of Elliott Lake came crashing down, taking more than just the mall.
After that, people started moving out of town. There was no place to shop. You couldn't buy socks or underwear in Elliott Lake.
The government report found that financial considerations played a part in the tragic failure, in what it called a toxic combination of circumstances.
Certainly it was about bad decisions that eventually led to the loss of material and then loss of section and eventually loss of life.
The Algo Mall was demolished and a new mall opened across town 4 years later, this time without a rooftop parking lot.
The simple answer to how to protect the building and to protect the steel is to prevent water from going in. And to do that, we need a waterproofing membrane. It's the membrane that protects the structure.
The original variant of the concrete waterproofing system was never used again on any project, while the empty site serves as a reminder of what happened.
It hurt the community quite a bit. And it's funny, we always talk about fire calls. Do you remember this call when? And stuff like this. This was the one call we never talk about.
With the new mall to bring people together, the residents of Elliott Lake were able to move on from the tragedy and rebuild their lives and town.
It was a tragic story. 2 women died. Hopefully nothing like that will ever happen here again.
When engineers harness the energy of hydraulics, what may look like peaceful water can become immensely powerful. The smallest mistake can have catastrophic consequences. Like this epic fail in Missouri, where a unique mountaintop reservoir left a trail of destruction.
1.5 billion gallons of water in a few minutes went running down this hill.
Engineering oversights combined to wreak havoc.
This thing was draining twice as fast as Niagara Falls.
And left everyone asking just what had gone wrong.
When we arrived, it almost just looked like a different planet.
The rugged Ozarks in the wilds of southeast Missouri are carved up by rivers, like here at Johnson's Shut-ins. Greg Coombs is the state park's regional director.
Here in the Ozark Mountains, shut-in is a term being the river is shut in. The East Fork of the Black River runs through Johnson Shut-ins. And the rhyolite boulders that you see behind me form the shut-in that is a very popular recreating area here at the park.
During the summer, these rock-lined waters are a huge draw for tourists. But in the 1960s, engineers saw potential for something very different in the towering slopes. This mighty reservoir on Prophet Mountain is the power behind the Tom Sock hydroelectric plant. Warren Witt is Director of Hydro Operations for Ameren, Missouri.
So this plant was built in 1963 when it went into service. It actually was the largest pump storage hydroelectric power plant in the world when it was built. But it's about 100 feet deep, estimated about 1.5 billion gallons of water. Unique thing, obviously, with this reservoir is you don't see many reservoirs that are on top of a mountain.
Building on a mountaintop is always going to be hard, but there's a good reason for perching it up here. The reservoir is all about dumping water from as high as possible to generate electricity.
When built, this hydroelectric plant had a higher vertical drop than any other facility in the country, creating enough electricity to power thousands of homes.
The problem with electricity is that everyone wants it during the day and not so much at night. Conventional power stations produce electricity 24/7, but storing it for when it's really needed can be tricky.
Tom Sock can both store energy and convert it to electricity at the flip of a switch. During the day, water is dropped more than 240 meters through the turbines, providing an instant boost to the electricity grid. At night, there's less demand and plenty of power available to refill the reservoir, like recharging a battery. This is known as pump storage.
We fluctuate this lake about every day. We drop it about 75 feet in elevation. It goes down, generates to the lower reservoir, and then at nighttime we pump it back full.
In 1964, this pioneering project was honored for its outstanding civil engineering, and for 40 years it pumped power into Missouri's electricity grid. But this isn't the first reservoir on this site. What came before it met an untimely end. On December 14, 2005, Greg Coombs from Missouri State Parks was woken unusually early.
I got a call a little after 5 a.m. on the morning of December 14th that we couldn't reach our park superintendent, and there was word that there was a problem with the upper reservoir at Tom Sock Mountain.
Initial reports were right. A vast section of wall had failed, catastrophically, and all 6.8 billion liters of water had gushed out.
When the reservoir broke and the water rushed down the west slope of the Prophet Mountain, it came into the developed zone of Johnson Shut-In State Park.
The superintendent and his family were all asleep in their home within the park boundaries when the deluge washed it away. Incredibly, they all survived.
We are extremely lucky that this event happened in December and didn't happen during one of the warmer season months when the campground would have been full.
Hydrologist Paul Rydland came to assess the damage just hours after the flood.
When we arrived, there was no identifiable trail. It was all very barren. It almost just looked like a different planet. There wasn't any trees or timber or any kind of cover like that because everything, of course, was so fresh.
This massive scar on the landscape proves just how much energy is stored in the water on top of the mountain. It was like dumping 2,000 Olympic swimming pools over the side.
289,000 cubic feet a second was the peak. Essentially, it took just over 5 minutes for that flood wave or that peak to be able to come down to the very base of this, where its junction is with the East Fork Black River.
Channeled through the turbines, that's a phenomenal amount of energy. But let loose on the mountainside, it was hugely destructive.
As we took a look at the magnitude of this water, it was actually pretty phenomenal. I was very surprised to see the force of water, and I've been 28 years in my career of dealing with hydrology and hydraulics. I've not seen anything this significant. This was a little off the charts.
An investigation was launched to understand exactly what had gone wrong. The wall had been built to survive an event like this, so why had it failed?
The old reservoir, the rock-filled dike, all the analysis said that you could overflow that top of that reservoir for more than 12 hours and it would not fail. That's why there was no overflow relief structure. We had only overflowed like 10 or 15 minutes and the thing completely collapsed.
When investigators examined the damage, the reason was clear to see.
And that's where we found the rock was not compacted like most rock-filled dams are.
Not only was the dike wall weaker than expected, so were the foundations.
Where the piled rock set on solid foundation rock, the spec called for nowhere to be more than 2 inches of soil, and we found as much as 12 to 18 inches of soil in some places.
Once the water started spilling over, it quickly eroded the soft foundations, and the dike was doomed to fail. But what investigators needed to understand was why it had overflowed in the first place.
Conventional dams can be hit by unexpected water surges from a storm or an upstream dam failing, but the only water coming into this one was pumped up on purpose. Clearly something had gone very wrong.
Over the decades, the reservoir wall had settled, causing cracks in the waterproofing. To fix the problem in 2004, a new liner was installed, along with new water level sensors. known as high trip switches, to prevent the reservoir from overflowing. But no one had realized the settled wall was no longer level and the switch's calibration was off.
People that put the high trip switch didn't recognize the low point of the reservoir, and they actually ended up having it set above the low point of the wall. So it was actually overflowing the reservoir before the high trip switch could even see it.
With some cut-off switches now set higher than parts of the wall they were meant to monitor, water could spill over the low point without ever tripping the alarms.
These automated safety switches were basically redundant. The pumps kept pumping, the water just kept coming. No one knew the reservoir was overtopping.
The failure of the emergency shut-off system, combined with the weakness in the wall and its foundations, was more than the structure could handle, and collapse was inevitable. Yet the Tomsock pump storage plant was vital to the state's energy system, and in 2007 rebuilding efforts began with lessons learned from the investigation.
Once we decided, yeah, we are going to rebuild, then there became a huge focus on how are you going to guarantee this never happens again.
One key requirement was a stronger retaining wall that wouldn't settle or fail.
It was a very impressive sight to see when it was being built. I tell people it was like an ant farm. There were just hundreds of people everywhere. We had about a half a dozen concrete plants on site here, and we'd make concrete, put it right back in the same place now as a concrete dam.
The outer skin would be watertight concrete, much like the older wall. But inside, for maximum stability and strength, engineers used roller compacted concrete in place of rock fill.
One of the reasons for roller compacted concrete is you can build massive amounts in a short period of time. This gets poured about 18 inches thick, and then you roll it. And as you rolled it, it compacted down to about a foot thick, and then you just keep pouring. The roller is good for the mass and the strength and the weight to hold it in place.
In addition to the impenetrable wall, engineers developed new safety precautions.
So in this room is our emergency high-level trips that back up the normal control system. This whole building was built with the new reservoir to provide a whole nother level of protection, utilizing 6 probes in here and 2 out on the overflow relief to shut down the units in an emergency. This is now the most sophisticated level instrumentation system probably of any hydro plant in the world.
Now the Tomsock Reservoir is stronger than ever and continues to be key to a cleaner, greener energy future.
We are putting some wind farms in service right now. We've got some solar farms in service, but you need a way to store that renewable, clean energy for when we really need it. And pump storage is the biggest and best way to do that.
This is a perfect example of engineers learning from mistakes of the past. And this unique reservoir looks to be here to stay.
When it comes to creating standout structures, form and function often go hand in hand. But if one outweighs the other, it can be a recipe for disaster. Like this catastrophe in Australia, in an apartment building in the middle of the night.
It looked like a towering inferno. The whole side of the building was on fire.
The fire took hold in seconds and forced a mass evacuation.
I see a big fire. Scary, very scary.
This disaster revealed a deadly defect.
This problem was massive, not just in Australia, but all over the world.
Melbourne, Australia, is a cosmopolitan city with a rich history. Local writer Mark Murdoch explains.
The growth of Melbourne really started in the 1850s with the gold rush and really set it up for the future. At one point, it was actually the second richest city in the British Empire behind London.
As its population blossomed, so too did its architecture.
Melbourne has an incredibly diverse and eclectic mix of buildings. We have Victorian buildings dating back to the 1800s and early 1900s, and then these days to the ultra-modern skyscrapers.
In the 1990s, Melbourne embarked on a 30-year project to redevelop its once derelict docklands.
This was one of Australia's largest urban renewal projects. Everything from roads to offices and more than 10,000 apartments.
In 2011, work began on the 23-story La Crosse Tower. To stand out from the crowd, it had a very distinct design feature, an aluminium covering. Fire safety engineer Stephen Kipp explains.
Modern buildings want to use very innovative, unique, fancy-looking materials to give a really crisp, sharp edge. Aluminium has the ability to have very straight edges and have a very clean finish for a long time.
Standing around 58 meters tall, the entire building was finished in aluminium composite material, or ACM. Just over 4 millimeters thick, this cosmetic skin had a layer of polyethylene sandwiched between two sheets of aluminium.
The core material, which is usually a plastic polyethylene, was added to avoid what's called oil canning, to avoid that sort of ripple effect that metals get when they heat up in strong sunlight.
You might not have heard of it, but polyethylene is the most common plastic in use today. It's found in everything from plastic bags to plastic bottles. It's even on the outside of buildings.
The La Crosse Tower, with its distinctive skin, opened in 2012, and its 240 apartments were soon home to more than 400 residents. Monday, November the 24th, 2014. For one La Crosse resident, Shashi Kumar Shaw, it was just like any other day.
Monday, went to work, came back, cooked my food, went to sleep. Very, very normal day. And then the alarm started to ring.
At 2:25 on Tuesday morning, a single smoke alarm was activated on the 8th floor. Other alarms in the building quickly followed.
The alarm kept on ringing. The alarm never went off.
The fire officer on duty that night was Deputy Commissioner Ken Brown.
We originally got a call from the resident inside the building. It rang alarm bells knowing it was a residential property, but a high occupancy rate, and 2:30 in the morning, people would be generally asleep.
Shashi woke his friends and they quickly began to evacuate.
We came out from this side, and the moment I reached there and turned right, there is the whole fire. Crazy.
The building's sprinkler system kicked in. Firefighters were on the scene in less than 5 minutes.
The whole side of the building was on fire and it was spreading up to the roof.
The front of the building was ablaze and rising rapidly.
This spread in less than 6 minutes to 23 floors. Unprecedented, unheard of before.
Within maybe a minute, a minute or two, the fire quickly went up. Fire was massive, massive.
With a towering inferno on their hands, Ken and the rest of the Fire Rescue Victoria team went to work.
At the height of the blaze, we had 22 fire trucks. We had 4 specialist appliances. We had ladder platforms and support vehicles as well.
Within 30 minutes, amazingly, firefighters had this 16-story blaze under control, and more importantly, had the residents out.
There was more than 500 people in the building at the time of the fire. Fortunately, they were all evacuated, and there was only 3 minor injuries, so it was a good outcome.
Thanks to internal sprinklers and the fast-acting fire service, tragedy was avoided.
After seeing that fire and coming to know that there was nobody killed, I thought that we were very lucky.
When the flames died down, questions were being asked. How had this building fire spread so high, so quickly? In the aftermath of the blaze, Fire Rescue Victoria sent investigators in to determine the cause of the catastrophe. Deputy Commissioner for Fire Safety, Michelle Young, explains.
There's many avenues for the fire investigators to gather information, and unless you know what you're looking for, it just looks like all that stuff.
Analysing the damage, the team discovered that the fire started on an 8th floor balcony. with a cigarette butt discarded in a plastic yogurt pot.
That cigarette caused the yogurt container to catch alight, which in turn caught the table alight, and those embers got into the air conditioning unit, which then in turn caught the cladding, and then it just shot up from there.
That cigarette might have been the initial trigger, but the speed at which the blaze spread up the cladding gave fire chiefs real cause for concern.
What is this material? Why did it spread so quickly on the external? What's out here that's different?
The covering was sent to the CSIRO, one of Australia's leading scientific research institutions. Fire engineer Alex Webb analysed the samples.
The fire brigade actually asked us to do some testing on the cladding that was on there, and one specific test they asked us to do, which was the AS 1530 Part 1 test, which is about its combustibility.
The standard temperature for the test is 750 degrees Celsius.
The aluminium cladding samples that we received is something similar to this. It's not the actual one, so it has two skins of aluminium with the polymer core in the middle. So to make it for a sample we're going to be able to test, we need to cut it into discs, because we have to make a sample. It's actually this shape, about the size of a fist. In the pictures, we can see the sample here, sitting on top of the furnace, which is kept at 750 degrees C, really stable temperature. If there's any flaming, or if the temperature of the furnace goes over a certain criteria, then we know that the material is actually combustible.
What Alex and the CSIRO team discovered was shocking.
In the photos here, we can see the flames actually coming out of the furnace. This is a photo when the material was extracted and is still flaming.
The conclusion was that this material miserably failed industry standards. Fire safety engineer Stephen Kipp explains.
The cladding included a highly combustible polyethylene core. In fact, the CSIRO found that a test that should have lasted 20 minutes failed after 93 seconds.
So why was a highly flammable material wrapped around an entire apartment building? It turns out that this covering was not actually approved on the building permit.
The cladding that was planned for the lacrosse tower had a mineral fiber core, which is fire retardant, but the polyethylene core was not. The difference in combustibility is massive.
Polyethylene has a very high calorific content, so it's very energy laden. So once it's ignited, it can burn by itself. Now, fires like to burn upwards. If you can imagine, if you lit a match, if you turned the match upside down, it would burn very quickly. So any situation where combustible plastic is in a vertical situation means that the fuel is ahead of the flame and the fire will spread rapidly.
The apartment building was a potential ticking time bomb, and the single cigarette butt was the fuse.
With combustible cladding, it's like wrapping a building in flammable liquid, virtually, and the spread of fire is so quick, and with the melting aluminium, it drops down and creates fires on lower levels, which is something we don't see very often.
It's like the difference between putting bricks on the outside and putting cardboard paper on the outside. You know, we know which one's going to burn more readily and we know which one's safer.
Further investigation revealed that this highly flammable material, although non-compliant throughout Australia, had been used on buildings across the country for years.
In this case, it was the cheaper, easier to build product that is actually quite combustible that was used, I think, in error by the people who constructed the building.
While narrowly avoiding tragedy, the disaster prompted an overhaul of the state's building safety regulations.
That opened up an audit of about 170 other buildings in Victoria, and we've since had a Victorian cladding task force where nearly 1,700 non-compliant buildings have been discovered. So this is an ongoing long-term issue.
That's one of the benefits that have come out of this, that we've identified these buildings and they are now registered and we can work with them to help reduce this material and help make Victoria a safer place.
In 2019, nearly 5 years after the fire, the non-compliant covering on the lacrosse tower was finally replaced.
Ultimately, people have to feel safe in their own homes, and hopefully now action will be taken to prevent this and related tragedies from ever happening again.
When massive feats of engineering fail, many come crashing down from above. But sometimes the real danger lies in what lurks beneath. Like this catastrophe in Arkansas.
It was surreal, to say the least. I would not have expected that then or now.
A river of oil engulfing a town.
Incredible, and that is oil.
In its path, one of the best fishing lakes in the entire state.
The oil came into the upper end of Dawson's Cove. We want to protect it at all costs.
The town of Mayflower, Arkansas, sits on the banks of Lake Conway. In a state that prides itself on natural beauty, this nearly 13-kilometer man-made waterway is a huge draw for both tourists and residents alike. County Judge Alan Dodson has lived here all his life.
Well, Lake Conway has always been special to anyone who lives around here. It's the largest state-owned game and fish lake in America. It's a natural reserve for wildlife. It's just beautiful, and we are proud of it.
Lake Conway was created for one main reason: fishing. Not only is it a world-class destination for anglers, migratory birds stop to fish here too.
Developed back in the late 40s, this man-made haven was a major attraction to the Mayflower community. But less than a decade ago, an engineering blunder almost destroyed it. On March 29, 2013, Mayflower resident Drew Barnes was driving his daughter home.
The closer we got to the neighborhood, there was something that was very wrong. I saw a stream, and I assumed it was water gushing down the opposite side of the road.
Drew started filming.
It took me probably 30 seconds to figure out that that wasn't water. There was obviously something else there.
That something else was heavy-duty crude oil.
To get into the neighborhood and find an oil spill was very shocking and very sobering. It was disbelief, I think, but given all the other sensory input with smell and eyes burning and all of those things, you know, it was surreal, to say the least.
Thick, heavy, and toxic. Nearly 400,000 liters of it was spewing onto the streets.
Incredible, and that is oil.
The equivalent of thousands of barrels of crude was moving fast, flowing into storm drains and heading towards Lake Conway. Judge Alan Dodson and the community swung into action.
So we're on Arkansas Highway 89, so the oil has to get under this highway to get to the open water of the lake.
With time running out, Alan and the team knew they had to block the pipes to protect the lake.
We're not industry experts, but we're the first on scene, and we have our own skill sets. We knew that we could create a mechanical block here and that no water and oil could get from the cove into the greater part of the lake.
If they could create a makeshift dam, the lake's wildlife could potentially be saved.
We had dozens of people working on covering these culverts with gravel. We covered the end of the pipe up with multiple sheets of plywood. The barricade was successful, but nothing could get through them.
Amazingly, the community's rapid response saved Lake Conway from a massive ecological disaster.
I think in the heat of the moment, you really don't have time to stop and think about, small victories like that. But, knowing we got that block, that was a huge relief.
Although Lake Conway was in the clear, much of the surrounding area was contaminated. More than 1,000 meters of containment booms were deployed to trap the oil. In the town, 22 homes had to be evacuated. The shocked Mayflower community wanted to know what had caused this catastrophe. The answers lay buried beneath the ground.
There are around 300,000 kilometers of pipeline crisscrossing the U.S., carrying oil and gas 24/7 from drill sites to refineries and onto all kinds of industrial facilities. And one of them runs straight beneath Mayflower.
It's part of the mighty Pegasus pipeline.
The Pegasus pipeline carries 90,000 barrels of crude oil a day, almost 1,400 kilometers from Illinois to the refineries of Texas. Some of it runs on the surface, but miles of pipeline are buried underground.
Never had any concern about the pipeline or any pipeline, you just know there's something there, and of course you hope nothing ever happens to it.
Nothing until that day.
The pipeline had clearly burst. It was hemorrhaging oil at an alarming rate, and Mayflower bore the brunt.
With the pipeline shut down, engineers were quick to the scene to assess the source of the rupture.
One section of a pipe had a nearly 7-meter split running lengthways along the top of the pipe. There was no other damage, so this crack was clearly the cause. The question was, why had it failed?
The investigation revealed that the problem could be in how the pipe was made about 60 years before the accident.
One of the simplest ways to make a pipe is called seam welding. You roll a sheet of steel into a cylinder and weld this seam. In this case, using electricity to melt and join the steel.
Gary Prins is an associate professor of engineering.
So they take a sheet of steel and they essentially cold work it to more of a cylindrical shape, and then they pass an electric current along the two edges of the plate just to heat them up, and then force the ends of the plates together. The fusion of the two plate edges is very important.
In this case, the particular method used was known as low-frequency electric resistance welding. Now obsolete, it was discovered to be susceptible to defects such as seam corrosion and inadequate bonding.
These pipes have a problem. The heat from welding that long seam together can create defects in the metal around it. And those defects could join up to form fatigue cracks.
What happens when we have defects in there is they cause stress concentrations. And so at the tips of these cracks, we get very, very high stresses. During repeated loading, these cracks, even though the loading is insufficient to just fully rupture the pipe, they can cause growth of the cracks over time. And these cracks can grow to a point where they become critical and unstable.
Although phased out in the 70s, these aging pipes were still part of the pipeline running directly underneath the town.
When you pump oil through a pipeline, the pressure fluctuates. When it's happening day in, day out, the stress fatigues the metal, and it's only a matter of time until it fails.
As we repeat this stress over and over, the cracks grow until they maybe merge with another crack, and then that crack gets much bigger, and then eventually they might reach a point where they reach that critical size and can cause a rupture.
After years of transporting heavy-duty crude, the seam and the welding finally gave way, pouring out oil onto an unsuspecting neighborhood, leaving a trail of destruction in its wake.
The two houses that were closest, those are completely gone. So, it carved a path essentially to the lowest elevation and down into the watershed and did some real damage. Obviously, these houses are just gone.
After the disaster, the ruptured section of the pipeline was isolated and repaired, and a massive cleanup operation began.
This was one huge and costly mess, but thanks to a swift response and an epic cleanup, Mayflower and Lake Conway was safe again.
At the time, you wouldn't consider that being risky in any sense of the word. There's pipelines buried all across the United States, and it's stranger than fiction.
With a new electric welding process now common practice, creating higher quality welds, hopefully disasters like this are a thing of the past.
Well, I'm thankful that it's back to its natural state. Of course, we're proud of our wildlife, we're proud of our nature, we're proud of our clean air, we're proud of of where we live. We want to protect it at all costs for future generations.
In Texas, explosions rip through a refinery.
You had the black smoke rising up, but you could also just see flame, 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 flame.
A catastrophic collapse in Iowa.
It was something I will never ever forget. It was almost apocalyptic.
In Australia, a cracking miscalculation.
It became one of those things that people talk about, wondering what could have possibly gone so wrong.
And in Denmark, a bridge disaster that very nearly turned to tragedy.
There were people working on the bridge. There were people passing under the bridge. You want to know, how could this happen?
With big bills, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Sometimes engineers strive for style, sometimes for substance, but always for safety. Because even a small mistake can trigger a major catastrophe. Like this shocking disaster in Texas at a major oil refinery.
It looked like a scene from a disaster movie. The explosion was so strong, so massive.
Devastation on a terrifying scale.
Heavy-duty steel, just bent, missing, gone, destroyed. There was not a structure in sight.
An engineering tragedy that left a city reeling.
It was like a bomb blew off. Never saw nothing like that in my life.
Across the planet, every major economy relies on oil. And in the US, one state accounts for more than 40% of all production, Texas. Journalist T.J. Olds knows the story well.
In Texas, oil is bigger than big. It is where oil was first taken from the ground and turned into refined product. You hear a lot of times oil referred to as black gold or Texas tea. It is what makes the heart beat in the state of Texas.
To say oil is huge in Texas is a massive understatement. In a good year, it's worth more than $220 billion. That's more than the entire economy of New Zealand.
All that black gold starts life deep underground in a seething cocktail of crude oil. Before it can turn the wheels of the modern world, it has to be refined. At mammoth facilities like this 6-kilometer-wide complex in Texas City on the Gulf Coast. During the late 90s, it was owned and operated by BP.
The refinery in Texas City was the third largest in the U.S., capable of refining more than 450,000 barrels of crude a day.
Mass producing millions of liters of highly explosive compounds is incredibly dangerous. Mark Holtzapfel is a professor of chemical engineering.
One way of thinking about an oil refinery is it's a bomb. Typically, the chemicals are volatile and flammable and explosive. Everybody that works there knows this, and so safety is an extremely important part of the culture.
The volatile chemicals can be turned into more than 2,000 products, and one of the most in demand is gasoline, produced in the so-called ISOM unit.
The isomerization, or ISOM unit, basically rearranges the liquid's molecular structure to create a higher grade gasoline.
The boiling heart of the ISOM unit is the 50-meter high raffinate splitter, a distillation column where oil is heated to around 135 degrees and vaporized, breaking the raw crude into different products based on their boiling points.
The volatile parts rise to the top, and the heavy parts stay at the bottom. So based on the volatility, how easy it is to vaporize, you can separate the various components.
The components are then further refined and blended to create regular gasoline, with operations running 24/7, 365 days a year. On March 24, 2005, Assistant Fire Chief Jesse Rubio was on call at Texas City Fire Station 1.
While I was laying in my bunk, I heard what sounded like someone banging on the door. The ceiling tile moved up and down, and that's when I noticed, okay, that wasn't normal.
Journalist TJ Olds was in his office.
There was this low rumble. I went outside and saw a black plume of smoke coming up.
We got into our rescue truck and we responded to the scene.
At 1:20 p.m., a huge and violent explosion from inside the Gulf Coast refinery shook the city.
It was not anything I had ever witnessed in person before. You had the black smoke rising up, but you could also just see flame here, and it just billowed and billowed. And you could see it for miles. It looked like a scene from a movie.
The pressure from the blast triggered more violent explosions, igniting fires across the plant, engulfing an area approaching 5 acres.
They were bringing in air ambulances, helicopters to land and take people out. There were employees who had run, who had jumped over the fence in many cases, and they were along the ways here and being treated and triaged right here on site, then taken away.
It was very horrific. Injuries that we've never seen before. Heavy duty steel, just bent, missing, gone, destroyed.
Refinery worker Brian Ambrose was at home preparing for his shift.
I was working a night shift, and my wife at the time said, "Your plant's on fire." I said, "My plant's on fire." Got to the TV and I looked. I couldn't believe it. It was the ISOM. It was the unit I worked.
Brian was one of the lucky ones. Hundreds of others were on site at the time.
By the time I got there, and you looked, it was like a bomb blew off. Unbelievable.
More than 40 mobile trailers used as temporary offices were damaged, 13 completely destroyed.
The explosion was so strong, so massive. Trailers that had been just destroyed and turned into sticks.
There was not a structure in sight. These were all gone.
180 workers were injured. And despite rescuers' best efforts, sadly, 15 more lost their lives.
I still feel for them people. Nobody should go through that. I'll never, ever forget what happened that day.
With more than 100 refineries across the country still working around the clock, it was crucial the cause of the blast was established.
Within 24 hours of this happening, the big question came is, how did this happen? Why did it happen? The nation, and in many ways the world, was looking at this too.
After the disaster, investigators knew that the initial explosion had come from the ISOM unit. Just before the blast, the unit was being restarted.
A restart is one of the most dangerous times because you're taking cold product and heating it up. If anything's gonna go wrong, that's when it'll go wrong.
During the restart, oil is pumped into the 50-meter tall distillation column. At its base, 2 safety gauges linked to 2 control rooms, monitoring liquid levels to prevent vapor pressure from building up.
During normal operations, there should only be around 2 meters. If the level goes even 30 centimeters too high, it activates an alarm. There's even a second gauge just above the first one to act as a failsafe.
The filling liquid did trigger the first warning, but as the level continued to rise, The top gauge, which should have acted as a failsafe, malfunctioned.
And so the crew that was starting that unit up was putting more in there thinking they had room. They didn't.
The liquid reached a height of nearly 30 meters. That's more than 15 times normal. But incredibly, the faulty gauge was telling operators that it was just over 2.5 meters and gradually falling.
The climbing liquid compressed the gases in the tower, triggering 3 emergency relief valves, which sent the hot liquid to a venting system known as the blowdown stack.
Essentially what a blowdown stack is a drum that has a pipe at the top of it. When you have an overflow of highly explosive, highly volatile product, would go into that drum and the vapors from that would be released and it would blow out from that. But when it gets overfilled, it doesn't work.
Instead of venting vapor, the blowdown stack shot nearly 30,000 liters of hot, highly flammable liquid into the air in less than 2 minutes.
And it was like a geyser. Just it came out, this explosive product coming out of the top of this blowdown stack.
The equivalent of nearly a tanker truck of gasoline fell to the ground, creating a huge flammable vapor cloud.
All this vapor needed was a spark. About 7 meters away, 2 workers were in a diesel pickup with the engine running.
Any engine runs on a mixture of air and fuel. But in this case, the air itself had fuel in it. And so when that air with the fuel got into the engine just ran faster and faster and faster. Even though they tried to turn it off, it wouldn't turn off. And they ran out of the truck knowing that something bad was going to happen.
That truck revved up just based on all that explosive vapor going into it. And that ignited what became a fireball that went down the ground, hit the unit, and then took the whole unit up with it.
Investigators now understood how the blast was triggered, but not what had caused the overflow. Attention turned to the gauge in the distillation column, which had failed to activate the alarm. For a complicated refinery, it was a remarkably simple device.
Essentially, it's the same thing in your toilet, the float that tells you what the liquid level is in your toilet. They have an industrial float, and that piece of equipment malfunctioned.
Investigators found a hole in the float, which appeared to have formed before the disaster. They concluded it had either sunk or failed to float on the surface of the liquid.
They had a false reading. They thought they had a small amount of liquid in there, and so they were basically flying blind because the instruments were not telling them the proper situation.
Following the tragedy, more detailed checklists and safety reviews were introduced, and exclusion zones were established for both unit startups and shutdowns.
The first lessons learned were getting folks away from facilities unless they really had to be there. Now, when you have a startup, everybody is told. So you know, hey, we got to clear out, let's be ultra safe on this.
All non-essential workers and temporary structures were permanently relocated away from the danger zone.
This was the largest explosion accident in American history at a refinery, so it definitely got people's attention, and we will learn from this experience.
The ISOM unit remained shut down for more than 2 years. But with lessons learned, the refinery has been operating safely for more than a decade.
It really tears me up to see when people don't go home the way they showed up to work. And I hope a day like the ISOM never happens again.
Wherever they build, engineers must always consider the elements. Underestimate Mother Nature, and the consequences can be devastating. Like this catastrophe in Iowa that brought down a vital railroad crossing.
The river forecast went from 24 feet to 28 feet, then came up onto the structure and up onto those rail cars.
A bold rescue effort that didn't pay off.
The image of the rail cars in the water, it was something I will never ever forget. It was almost apocalyptic.
and a battle with engineering that Mother Nature won.
We've learned through painful experience, forces that come to bear on structures are tremendous and frankly quite frightening.
Iowa, sprawling across the Great Plains, is the largest grower of corn in the US.
Millions of acres of Iowa farmland are dedicated to growing corn. They harvest billions of bushels a year. That's almost 20% of the national corn production.
Most of it comes here to be processed, the city of Cedar Rapids. And what better way to get it where it needs to go than by railroad? For about 100 years, the Cedar Rapids and Iowa City Railway, or CRANDIC, crossed the rapids on a bridge like this, designed for shallow, sandy rivers. Bridge engineering specialist Matt Rouse explains.
If the ground conditions are particularly favorable near the surface, which is usually a very sandy type of soil, sometimes bridge foundations are much shallower. And it so happened that the CRANDIC Bridge had relatively shallow foundations.
Built in 1903, the original nearly 250-meter-long bridge consisted of 4 steel truss spans. The bridge legs or piers stood on shallow but wide concrete foundations known as spread footings.
Many structures, and certainly bridges, use a spread footing as the foundation for the pier. And the idea is to distribute the loads from the pier to the soil, which is usually a very sandy type of soil. The slab would have a thickness similar to this block that we're standing by here. They tend to do that so that they are very rigid and can better distribute those loads to the surrounding soil.
Spread footings are great for distributing load on soft ground. They're also much simpler to build than deeper foundations, which is especially difficult in the middle of a river.
The bridge carried up to 100 trains a day without a hitch for over a century until 2008. In early June, an unprecedented flood swept through Cedar Rapids, devastating everything in its path. Susie Kettleson from the local school district was worried.
I had never seen anything like this before. Just kept coming and coming. This was a 500-year flood.
As the rains kept falling, the river kept rising. For Professor of Environmental Engineering Larry Weber, this was unparalleled.
About 1,300 blocks of the city were inundated by this event. You know, City of Cedar Rapids had to evacuate 30,000 people overnight. The damage was devastating.
With water rising to historic levels, one major concern was the CRANDIC Bridge, which was in danger of being overwhelmed.
Each day brought more rain and more bad news in the forecast. As we add rainfall, day by day by day, the river forecast went from 20 feet to 22 feet to 24 feet.
On June 10, 2008, the railroad took drastic action.
They were concerned that if the waters rose far enough that it would push the steel truss off of the large concrete piers. So they loaded several train cars with rock and put them on the bridge to try to hold the bridge down.
The river was flowing at around 4 million liters per second and rising fast.
The river forecast went from 24 feet to 28 feet, so the river then came up onto the structure and put a tremendous amount of lateral force on the bridge and the rail cars.
At 9:43 a.m. on June 12th, the CRANDIC Bridge was finally overcome by the flood. 14 loaded rail cars, 3 steel trusses, and 3 concrete piers were swept into the river.
It's unbelievable, the amount of water that basically penetrated the whole city. And then when you saw that the CRANDIC Bridge actually collapsed and the image of the rail cars in the water, it was something I will never ever forget.
In the aftermath of the disaster, the CRANDIC Railroad crossing was cut off, lying in a mass of rubble and debris.
The collapse caused major disruption. Trains were rerouted hundreds of kilometers out of their way to get into Cedar Rapids.
This was the only bridge to fail in the floods, and left many wondering why had the Crandic crossing collapsed when others had survived.
The one big difference was the use of rail cars to weigh this bridge down. Some suggested that played a part in the collapse. But while it might sound unusual, it isn't unheard of.
The Crandic Railroad has deployed that approach before, and it worked very successfully. This event simply exceeded the forecasted flows and the forecasted height and resulted in the failure.
That's a railway bridge that is regularly loaded with train cars loaded to the top. But I would not imagine that the additional load led to the collapse.
Instead, attention turned to the pier's concrete foundations, the spread footings. It turns out they were susceptible to a relatively common phenomenon known as scour.
Scour is one of the challenges of river engineering. As the river water is flowing through the channel, it's moving sediment particles along the bed of the river. When we put a structure in the middle of the river, like a bridge pier, then water that's flowing to that structure has to accelerate to get around the structure and can move more sediment particles. And so it scours a hole on the downstream side of these structures in the middle of rivers.
Maybe just as a simple demonstration of how a bridge pier might undergo erosion or scour, set up a simple bucket of sand here, and let's let this wooden stake represent our bridge pier. And normally it's very stable, but under a high flow event, you can see this scour basin immediately forming around the base.
As the flood intensified, so did the flow around the piers, increasing the scour and weakening the foundations, compromising the integrity of the bridge.
So the fast-moving water around the base of the pier scoured out or eroded the supporting soil around the base of the spread footing, which caused the piers to tip over.
Scour is one of the most common causes of bridge collapse in the U.S. Some estimates suggest that up to 16% of all bridge failures are caused by scour.
When the 100-year-old bridge came up against the 500-year-old flood, the winner was clear.
Scour is just a very unpredictable event, and a flood the magnitude that Cedar River experienced, it was just beyond the range of floods that were considered at the time that that bridge was built.
After the flooding receded, every ballast car was retrieved and restored, and a new bridge constructed. This time the foundations consisted of 90-centimeter diameter shafts drilled down into the bedrock.
They did go in and fortify the foundations below the piers. Now, instead of using spread footings, we will drive steel piling in to the river and then pour the concrete cap of the pier on top of that steel piling. So even if scour happens around the steel piling, the structure of the steel maintains the integrity of the bridge.
The new bridge opened just over a year later, on July the 6th, 2009, at a cost of around $8 million. And once again, the Crandic Railroad is rolling over the river.
I think what's important for us as engineers is that when we have failures, that becomes a matter of our understanding, and that then becomes part of future engineering design.
Urban engineering isn't just about function. With landmark projects, architects strive for unique, standout designs. But one-of-a-kind projects come with big risks. Like this catastrophe in Australia that was breaking at the seams, with a giant wheel that drew everybody's eye.
The landmark was at the heart of a bustling city. It was a very public place to fail.
A design flaw that crippled an icon for years.
It became one of those things that people talk about, wondering what could have possibly gone so wrong.
Melbourne, Australia, is the nation's second largest city. With 5 million residents and growing, it's now one of the most popular destinations on the planet. Mark Murdoch is a local tourism writer.
Melbourne's a multicultural city and a very exciting place to live. And the people here are very curious for new and interesting experiences. And it's some of these qualities that make a city that's actually at the end of the world, one of the world's most livable places.
Melbourne has everything. Great weather, sports, culture. It's a big hit with tourists, and more than 10 million people a year visit the city.
In 2008, locals and tourists alike were excited by the arrival of an iconic new attraction. A $100 million observation wheel. At around 120 meters or 40 stories high, the first wheel here was the tallest of its kind in the Southern Hemisphere.
Melbourne is known for trying to bring the best of what the world has to offer to the city. And people had been watching the success of the London Eye over in the UK and had the idea to bring some of the best of that back here for what then became the Melbourne Star Observation Wheel.
When the London Eye opened in 2000, it was the first of a new generation of super-tall, modern observation wheels.
The London Eye set the bar high for the rest of the world to follow, and massive observation wheels opened up everywhere from Las Vegas to Singapore.
Each has its own unique design, but the basic principles are the same. Structural engineer Santo Pascuzzi explains.
The observation wheel is very similar to a bicycle rim. So you've got an external rim supported by spokes, and the spokes are supported by a main hub, which spins around a spindle. And the spindle is supported by struts down to a foundation.
The ride might look effortless, but gravity exerts huge forces on the structure, which has to push back. As the wheel rotates, those forces push and pull it in every direction.
All the joints are subject to tension compression at different times on their cycle around the wheel. And when the spokes are positioned in the lower part of the wheel, it experiences the greatest amount of tension to hold up the whole rim of the wheel. When the spokes are at the top of the wheel, it's in less tension and more compression.
With most of the modern big wheels, your eye is drawn by the outer rim, and the hub and the spokes are just the mechanics. The Melbourne wheel is different. It has a central feature, the iconic star from the Australian flag. And that star isn't cosmetic. Those are the spokes.
Instead of steel cables, Melbourne's spokes were made from hollow steel trusses welded together to create a space frame in the pattern of a 7-pointed star.
The London Eye uses about 67 spokes, and they're much narrower cables rather than bigger structures. By having more cables, you are distributing the stresses around the supports of the rim and also at the hub, whereas using less spokes, such as the Melbourne Star, you're concentrating the loads at each spoke, so each spoke takes a bit more load than the London Eye.
There's a reason most bicycle wheels have lots of spokes. The rim is evenly supported all the way around, and all the stresses are spread. Fewer spokes can work perfectly too, but clearly each connection has to work much harder. And on the scale of a bicycle, that's no problem. But the Star weighs around 1,500 tons.
The giant iconic wheel first opened for business for the 2008 summer break during an unusually strong heatwave, even for Melbourne.
2008 was a scorcher in Melbourne with temperatures in the mid-40s in centigrade. That's around 110 in Fahrenheit.
A few weeks after the grand opening, a contractor working on the original wheel spotted a problem. Soon after, these pictures were leaked online.
The Melbourne Star was open for 40 days before a technician who was installing LED lighting noticed some worrying cracks in the wheel. In total, there were 14 of them, and some of them were as many as 3 meters long. And so safety authorities ultimately shut down the wheel at that point.
3 meters is about 10 feet. That is a long crack. And there were more than a dozen of them. In a structure almost 40 stories tall, clearly something was seriously wrong here.
With the wheel shut down, engineers made a closer inspection, hoping to get the ride operational as soon as possible.
This is a $100 million project, and as part of that, you're using some of the best engineers in the world in what's a very, very unique and interesting design problem. And I think the expectation is that if there is a problem, it can be resolved.
Rumours were running rampant as to the cause of the cracks, from poor welding to unstable foundations. Fingers were even pointed at the extreme weather.
Initially, they blamed a record heat wave during that period. So there were 3 days that were over 43 degrees, the hottest of which was over 46 degrees. And so initially, the operators blamed the heat, but in time it became clear that the issue was actually with the design rather than the unusual heat during that period.
2 months later, the owners conceded the cracks were due to a design flaw. The details weren't made public, but the location of the cracks suggested the design was unable to cope with the ever-changing forces of rotating.
I believe low cycle fatigue was the main cause of cracking in this Melbourne Star wheel. Low cycle fatigue is when the wheel experiences both tension and compression at the joints with a long period of time between each cycle. When the stresses exceed the yield strength of the steel, it reaches its plastic deformation with every cycle. With plastic deformation, cracks form, and with each cycle, the cracks will propagate into longer cracks.
A big clue in low cycle fatigue is the word low. That means the fatigue happens after only a few cycles or turns of the wheel. That's no good for a structure that has one job, to rotate.
Experts said the wheel was never at risk of collapse, but the cracks were too serious to fix.
It wasn't a great start to what was supposed to be a very iconic attraction in Melbourne. People are normally reasonably forgiving, but the problem was that that initial shutdown, which was expected to be resolved in a year, turned into 2 years and then turned into 5 years. So it became one of those things that people talk about at dinner parties and at the pub, wondering what could have possibly gone so wrong.
The radical solution was to take the wheel down and start over with a modified design.
As the project went on, it became clear that the issues are more fundamental than that, and unfortunately, the entire wheel had to be sold for scrap. They did retain the cabins and the support structure, but the rest of the wheel was gone.
With the old wheel on the scrap heap, it was clear that something had to be done differently the second time around.
The star was simplified. The connections from the spokes to the outer rim have been strengthened up via trusses. Compared to the previous design, it's a lot more sturdy.
This was a costly, very public fail, but thankfully no one was hurt. It's a reminder that in big engineering, trying something new always comes with risks.
In unique designs such as the Melbourne Star, there are always new aspects to engineering to consider. However, if you bring it back to basics and just focus on the fundamentals, you will have a greater chance of mitigating the chance of failure.
With the replacement in place, residents and visitors can enjoy the unique view from the new and improved Melbourne Star. When it comes to big engineering, every last detail must be checked and double-checked. Because sometimes it's the most basic oversights that lead to catastrophe. Like this disaster in Denmark, which exposed critical flaws in construction.
It was very dramatic, it was very bad. It was a very disturbing picture.
A catastrophic bridge collapse that very nearly turned to tragedy.
People have been standing in these areas and they had to grab the net not to fall down on the road.
Fundamental engineering errors that caused chaos on one of the country's most important highways.
There were people working on the bridge. There were people passing under the bridge. You want to know, how could this happen?
Denmark, a small nation with a long coastline that plays a vital role in European travel and trade. Local journalist Ulrik Andersen explains.
Denmark sits at the crossroads between mainland Europe and Scandinavia. Every transportation route goes through Denmark and to Sweden or to Norway.
In 1962, work began on a comprehensive highway system known as the Big H. At its heart was the E47, the first freeway in Denmark, running from the capital Copenhagen directly into Germany.
Everything depends on a well-functioning road network. It's a very important cog in the European transport network.
But this cog was becoming clogged. So in 2014, to ease congestion around the capital, the road was widened from 4 to 6 lanes, which involved more than just a new road surface. Professor of Engineering Christos Georgiakis explains.
The widening of the E47 was a very, very big project. It was, in a way, a kind of not just an engineering concept, but an architectural dream. There was the idea from the architects to sort of build a boulevard through Copenhagen. People wanted the widening of the road because there was enormous amounts of traffic on the E47. A lot of time spent in vehicles, getting to work, coming home in the evening. So a lot of people welcomed this, and they understood that this disruption was going to be for the benefit of all. When you widen a road like this, you have to look at what existing infrastructure you have. Older bridges, more often than not, cannot be lengthened.
In all, 7 bridges needed completely rebuilding. The freeway was a vital thoroughfare, so the road would stay open, while concrete for the bridges would be poured above, a process known as cast in situ.
When you're casting a bridge in situ, you can put temporary supports in the locations where you're going to end up putting the permanent supports, and that allows you to open up the road below.
Wooden molds, known as formwork, are built in the shape of the bridge on top of temporary steel supports. Then concrete is poured into the mold, and when hardened, the deck is lowered into place.
There's a good reason for casting the bridge in one giant mould. Having joints would create potential weaknesses. But this way, when the concrete hardens, you effectively have one solid, strong structure.
The big difficulty is that, in fact, you're having to carry almost all of the dead load of the bridge by temporary formwork. So all of this concrete that you're pouring in, that is almost all of the dead load of the bridge, and it is in liquid form. And that's the most dangerous and critical part of constructing such a bridge.
Although risky, casting the bridge in situ was the best option.
This tried and true formula was common engineering practice. It allows you to build entire bridges, but still keep that all-important traffic flowing.
On September the 27th, 2014, concrete for the Eggebækvej Bridge, 16 kilometers north of Copenhagen, was about to be poured. Erik Larsen is head of construction at the Danish Road Directorate.
It was a Saturday. The casting was started early in the morning. Normally this size of bridge, the casting will take maybe 10-15 hours.
Just before 9:30 p.m., 26 workers were on the bridge pouring the western side of the deck when the whole structure rocked sideways.
The casting process was approximately 2/3 near the end when everything went wrong.
Without warning and with workers still on top, nearly 40 meters of wooden formwork collapsed.
2/3 of the mould were already full, and the concrete would take days to fully harden. Much of it was still wet and just spilled out.
Police immediately closed the road, and our people went to site immediately also.
Erik's colleague, engineer Christian Munk-Petersen, was one of those who witnessed the aftermath.
It was only 5 kilometers from where I live. This was the site I saw when I arrived. Exactly what you see on this picture here. The traffic has stopped, the bridge has partly collapsed, but the steel structure was still standing.
Around 800 tons of wet, reinforced concrete had come crashing down in seconds. Professor Christos Georgiakis was working nearby.
I came out almost immediately to the bridge, A lot of the concrete had fallen down onto the road below. The reinforcement that was in had slipped out of the formwork. Some of the supports underneath, it was obvious that they had buckled. It was a very disturbing picture.
Despite buckling, the fact that the steelwork held firm may have prevented this catastrophe from turning to tragedy.
About 20 persons were up here when the accident happened, and they had to grab to the net not to fall down on the road. And actually, I spoke to a young man who has been sitting out here. Then he was thirsty and went in to get a Coca-Cola, and when he was in to get the Coke, it fell down and it saved his life. And also down on the road, there was traffic on the road, but no cars were hit by the debris, or everyone stopped before an accident happened.
Incredibly, no one was seriously hurt. But with a key transportation link shut down, people wanted to know how such a routine build could go so disastrously wrong.
We're not accustomed to these kind of accidents, so you immediately start to wonder what went wrong in this particular instance.
The E47 in and out of Copenhagen was closed and traffic rerouted, causing chaos on road and rail networks. But before they could thoroughly investigate, Danish authorities realized they faced a much more immediate and potentially deadly problem.
Because they didn't know at that point what had gone wrong, they had to put the work on similar kinds of construction where you pour the concrete in place under increased scrutiny.
After this collapse, we had at that moment 85 or something like that bridges in our pipeline to be casted. So we made an immediately stop for casting of bridges.
This is the way the Danes make most of their road bridges. They have to shut down all these projects immediately.
Early investigations into the Eggebæk Bridge disaster quickly discovered the root of the problem. It seems a vital step in the wooden formwork had been overlooked.
It was pretty obvious that the formwork of the bridge had failed. Normally what you would expect in the wooden formwork is to have some longitudinal bracing. So any kind of longitudinal movements which might occur due to the pouring of the concrete, they allow for the formwork to stay together and not kind of concertina or collapse on itself.
To do its job, formwork needs to both support the weight of the wet concrete and counteract any horizontal movement. That's normally done with what's known as longitudinal bracing.
That formwork, that bracing was not present. This lack of longitudinal bracing led to a collapse of the truss work and then the subsequent collapse of the bridge.
These trusses were not stabilized enough, so they tilted. But when they tilt, the concrete, 800 tons, falls and have a huge impact on the steel structure. And actually, this falling was measured like a small earthquake.
These miscalculations meant that the formwork was insufficiently supported, but the error wasn't detected until after the collapse.
This particular failure could have been prevented. If we had sufficient overview on the project, then this lack of the bracing between the wooden trusses would have been picked up.
Within weeks, work began on a replacement bridge with lessons learned from the collapse.
After the collapse of the bridge, the road directorate managed to get another company to come in and rebuild the bridge. The bridge was built in a similar way, cast in situ, but with a different support system.
Completed in 2016, once again this vital artery was up and running, and commuters safe from potential harm.
And it went without any significant problems. So today traffic just flows on the E47 as it was supposed to all along.
The lessons learned from this disaster are a powerful reminder of the importance of coordination, communication, and double checking.
Tragedy strikes in the heart of downtown New Orleans.
Oh my God.
The building's collapsing. What? The building's collapsing. It was really just jaw-dropping.
In North Carolina, a catastrophic bridge collapse on a college campus.
There were some workers on the bridge, under the bridge, around the bridge. There was a failure, and the bridge collapsed.
Devastation in Denmark as a 60-ton tower is destroyed in seconds.
It went so fast that it looks like an explosion.
And in Houston, a billion-dollar bridge goes disastrously wrong.
If there's one little flaw in the bridge, you could have just an absolutely catastrophic situation.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to big engineering, planning is key to all construction. Any deviation, no matter how slight, can result in major catastrophe. Like this construction disaster in downtown New Orleans.
I just saw a building collapse, people trying to escape and people running.
Hotel destruction on a catastrophic scale.
Something happened here that was shocking.
A tragedy that left a city demanding answers.
How could a routine build go so disastrously wrong?
New Orleans, Louisiana's biggest and boldest city, is a destination with its own distinct identity. Local journalist Autumn Cafiero-Giusti knows all about this good time town.
New Orleans is a city that's just really like no other. It's very European, very Caribbean. The culture here is different. We're not a quiet city. We like to have fun. You know, it's a place people want to come to because it's an exciting place to be. It's got its own personality.
This charismatic city is a tourist hotspot.
The city welcomes millions of visitors every year who spend billions of dollars. In the Big Easy, big tourism equals big business.
It's one of our primary economic drivers. Our hotel industry is very important to the city. We rely on that hotel traffic and those tourists to really keep the city's economy moving.
In February 2018, construction began on a new $85 million hotel. On the edge of the famous French Quarter, this 18-story structure would break with tradition.
In this part of town, strict zoning laws normally limit buildings to around 21 meters. But this hotel would stand proud at 58 meters.
Professor of Civil Engineering and native of New Orleans, Dr. Norma Jean Mattei explains.
Typically, any structure within the French Quarter is very, very zealously guarded, but that part of Canal Street had not seen as healthy and robust an economy. So the city was looking at how in the world are we going to help develop this area that ultimately became the Hard Rock Hotel.
The plan was for the first 7 floors to house everything from parking to retail, with hotel rooms and private apartments occupying the next 11 stories.
The first 7 floors were reinforced with concrete, and then above that was a frame that was structural steel. So 2 different methodologies.
On the edge of the French Quarter and the business district, this was the perfect location for a hotel to breathe new life into this once iconic part of New Orleans.
With construction well underway, in July 2019, Amaris and Jordan Herndon thought they had found the perfect spot for their new restaurant, just a block and a half from the hotel.
Tourism drives the city
10 months out of the year. There's nothing that was going to be bad about having a massive hotel there.
On October 12, 2019, Amaris was on her way to the restaurant to open up.
It was a Saturday morning. I was driving about 2.5 blocks from here. I'm sleepy, I've overslept, and was running a little late.
More than 100 people were on the hotel construction site, working the weekend shift too.
I'm rushing, and I'm like, the building's collapsing. What? The building's collapsing.
Caught on another driver's dash cam. At around 9 a.m., without warning, the side of the hotel collapsed.
Oh my God.
People, like what looked like to me like rappelling off of the building as they were trying to escape, and people running. Sorry.
The top floors of the 18-story hotel were decimated as tons of concrete and steel cascaded to the streets below. Local journalist Autumn Caffiero Giusti heard the catastrophic news.
Seeing the site for the first time, I've covered disasters before, and I've seen a lot of tragic scenes. This was like nothing else I'd seen. It was really just jaw-dropping.
2 massive cranes were left swaying over the wreckage, forcing an immediate evacuation of the surrounding area.
I was almost a little afraid because the building was so unstable. They didn't know if it was going to collapse more. It was a really sobering scene.
18 people were injured in the disaster, and sadly 3 workers lost their lives.
The collapse was absolutely horrible. The 3 lives that were lost, and if it had happened at any other day, at any other time, the loss of life would have been more significant.
The collapse hadn't just destroyed a hotel, it had destroyed lives. The city and its citizens wanted to know, how could this have happened?
From the footage, you can clearly see the top floors on the street side collapse on themselves first. Then the side topples over. The big question was why?
The initial health and safety report by OSHA suggests design flaws may have affected the structural integrity of the upper floors, including the 16th story being under-designed in what's known as load capacity. Professor of Engineering Norma Jean Mattei knows strength in any building is key.
When you're building a tall structure, every single bit of that structure, the roof all the way down to the ground, has a load. And that load has to have a path down, ultimately, to the ground.
It appears that miscalculations left the steel connections unable to carry the necessary load, on top of which the concrete floors may have been poured thinner than originally designed.
On the plans, the metal molds for the concrete were around 7.5 centimeters deep, but in reality, they were found to be just 5. That's a very significant difference.
The strength of steel and concrete weren't the only concern. Some questioned the method of construction, specifically in temporary supports or bracing known as shoring.
Shoring is typically used when you're pouring an upper floor of fresh concrete, and so the floor below it is carrying that load through these braces. And so when the floor that you just braced has gained enough strength, you can then remove the braces and use them on the next floor.
To allow the concrete to fully harden for maximum strength, the design specifications required these braces to remain in place for a minimum of 15 days. But some accounts claim that most of the posts were gone after 8 days, just before the building collapsed.
The higher the floor, the younger the concrete, which means the concrete is weaker. It'll fail, fall on the next one, it'll fail, and that caused a series of cascading failures that ultimately took down a whole side of the structure.
Whatever the underlying issues were, ultimately the structure just wasn't strong enough to support its own weight. While the exact cause of the collapse is under investigation, there's no doubt the disaster shook one of the greatest cities in America to its core.
What happened and how it happened. There's a bunch of litigation underway, but something happened here that was tragic, and people lost their lives here.
With the structure still unstable and in a busy part of town, a decision had to be made about what to do with the wreckage.
A typical implosion is where you understand the condition of the building. In this situation, you don't know its condition. You know it's damaged, you just don't know how damaged.
In time, it was decided that the only safe option was to demolish the hotel piece by piece, no matter how long it took. And finally, it's beginning to look like there's light at the end of the tunnel.
I think people want to have normalcy again and, go back to New Orleans getting to be its usual lighthearted self without having this overshadowing it.
Maybe for some, life can, at last, return to normal.
We were open 3 months before that happened. It's now been a year and a half, and I want to be cleared of that.
New Orleanians, we're resilient, but having the building cleared out and having this street open is going to be a really good day.
When it comes to designing huge structures, engineers need to know their materials inside and out. Get the calculations wrong, and it can lead to catastrophe. Like this tragedy in North Carolina, a disaster that devastated a college campus.
There were some workers on the bridge, under the bridge, around the bridge. There was a failure, and the bridge collapsed.
Not one, but 2 bridges came crashing to the ground.
Something went wrong when the first bridge went down, but to have the second collapse, it wasn't just a fluke. You don't expect an accident like this to happen.
This double engineering mistake had devastating consequences.
Raleigh, North Carolina, is known as the City of Oaks, and over the years has grown from a tiny acorn into a metropolis. Thanks in no small part to its world-class academic institutions. Local reporter and former newspaper editor Richard Stradling explains.
Raleigh has evolved from this small, sort of southern state capital into a pretty diverse and prosperous city. Education is a big part of what Raleigh is and what has made Raleigh what it is today. To attract the companies and the employers here, if it wasn't for the universities and the colleges that were here, that wouldn't have happened.
It's one of the fastest growing cities in the US, home to 10 universities and colleges, and it's also part of one of the most prestigious research parks in the US.
Raleigh's also home to the state's largest community college, Wake Tech.
The first campus opened in 1963. It had just a few dozen students. And now it's got half dozen campuses across the county, close to 70,000 students.
As Wake Tech grew in student numbers, it needed to expand in size, constructing several new buildings and a parking garage on its northern campus. To connect the garage and campus, in 2014, construction began on 2 pedestrian bridges, crossing the woods and ravine. In keeping with the college's ethos, the bridges would embrace their surroundings. Department of Labor Commissioner Scott Mabry explains.
Wake Tech had decided to build these 2 bridges in place with the laminate wood support. With the setting, you can kind of see the trees and the creek back here. So it was a good blend, I think a good look for the area.
Both bridges would be constructed using huge timber girders, crossing suspended spans over their surroundings. The walkways would be steel beams supporting a metal deck with concrete poured over the top.
During the process of designing a bridge like that, you have to take into account ability of the wood to support the desired load that you're looking for. So the bridges were initially designed to do that, using the wood product in place.
This pair of bridges shared the same construction material. Both would feature a super-strength engineered wood known as glulam. Material expert and Associate Professor of Engineering, Dr. Reze Ferron, explains.
So over here, I have a sample of glulam, and glulam stands for structurally glue-laminated timber. And its name is exactly what it sounds like. You have timbers that are bonded together with an adhesive, a glue. With respect to glulam, you can engineer the product such that pound for pound, that it could actually be stronger than steel.
But by selecting glulam, engineers faced a design challenge.
One of the disadvantages of glulam is that if you have very long spans, you're going to have to, think about how you're going to connect it.
They were shipped across country and brought to the site. So they had to be short enough to be able to ship by truck, and they were put together in pieces.
The glulam girders were notched at each end, then pinned together using a metal plate to hold them in place. For added strength where they joined, they would be supported by V-shaped steel columns anchored to the ground.
Anytime a bridge is designed, safety is the #1 factor, and then you try to put the project together in such a way that it may blend in with the surroundings, so you're going to look for the aesthetic at that point. But regardless, safety is going to be the forefront.
November the 13th, 2014, construction of both bridges was well underway.
Bridges were already in place, so they were actually pouring the concrete for the walkway on the top of the bridge.
At around 10:30 a.m., disaster struck.
Suddenly, there's a crack, and the first bridge collapsed.
The entire central span of the first bridge fell into the ravine. There was no warning and no chance to escape.
The bridge dropped around 7.5 meters, taking 5 workers with it. Department of Labour Commissioner Scott Mabry was on the team that immediately began to investigate.
When we arrived on the site, one of the bridges had already collapsed. The other one was under construction, and there was some work activity going on that bridge at the time. So our folks recommended to the contractor at that time to cease activity on the second bridge.
While work was immediately shut down, local newspaper editor Richard Stradling knew a major story was unfolding.
There were students here, so when you hear that a bridge goes down on a campus like this, we had to scramble people up here pretty quickly.
The super-strength glulam girders lay splintered on the ravine floor.
We didn't know what had happened here. We couldn't get close, we couldn't see it. We didn't necessarily understand all the engineering, but it was pretty clear that something had gone wrong.
Worse was to follow. Just hours after locking down the site, bridge number 2 collapsed.
Something went wrong when the first bridge went down, but to have the second bridge of the same design at the same stage of construction to collapse, obviously you could tell something was wrong with the bridges. It wasn't just a fluke with the first one. But the second one collapsed shortly after midnight. Nobody was here, nobody was hurt. Very fortunate.
Not everyone was so lucky. Of the 5 workers who were on the first bridge when it collapsed, 4 were seriously injured. Tragically, 1 lost his life. The devastating collapse shocked faculty and students alike. The question was, what had gone so terribly wrong? Inspectors first considered the pouring of the bridge decks.
The bridge had been put in place. The concrete was partially poured on the bridge already, and there was an additional pour that day, which started to add the additional weight, which precipitated the crack along the beam itself and ultimately caused the collapse.
While this might have been the trigger, investigators knew that this wasn't the root cause of the disaster.
For both wooden bridges to collapse within 24 hours of each other, clearly something was fundamentally wrong with either the design or the construction.
Investigators turned their attention to the split glulam girders, specifically how they were joined.
The glulam product of the bridge was notched at the end where it was on the support column when it cracked laterally down the length of the beam. And that's where the failure occurred. So you could see how the bridge essentially split apart along the laminated section of the bridge.
The notches had created a weak spot that was now subjected to unexpectedly strong forces. Associate Professor of Engineering Dr. Reze Ferron explains.
What ended up happening is that there was already shear forces being applied to the bridge during construction, and then cracks start from the shear forces, and those cracks were horizontal.
The original design for the bridge did not include creating notches at the end of each girder, and for good reason.
One of the issues with putting notches into a material is that when you put a notch into it, you're taking out some of that material. So I think intuitively we can all think, okay, that's going to make it weaker. The other reason why you don't necessarily want to put notches in is because as you put a notch in, what you're doing is creating what we call the stress intensity. So the stresses at the cracked tip of the notch is going to be amplified.
There's nothing fundamentally wrong with cutting notches in wood, it's done all the time. But these were huge pieces carrying heavy loads, so it was essential that they were properly reinforced.
There's additional ways to put threaded rods through the beam itself to hold it together, and that wasn't done, and ultimately contributed to the failure of the bridge.
The weak spots created in the notches at both ends of the girders caused horizontal cracks to form at the column. As more and more concrete was added, the cracks spread further until the weakened wood could no longer take the strain and the whole bridge came crashing down.
The notch was actually the cause of the failure of both of the bridges.
The bridges were designed to easily carry the load of the concrete and the pedestrians. But adding these notches meant that both bridges were destined to fail. It was simply a question of when.
After the disaster, the collapsed bridges were dismantled and removed. However, Wake Tech still needed a solution to keep its campus on the move.
Wake Tech went back to the drawing board and they put in a steel-supported metal suspension bridge out here, and they fit into the environment pretty well. Maybe not quite as nicely as the wood-sided bridges would have, but they do look good, and they do get quite a bit of use.
Today, the two new bridges safely carry students and their teachers across the northern campus and the ravine.
Given the foot traffic here on campus, the incident could have been much worse if it were a nice sunny day and there were 100 people on the bridge at the time. Who knows how bad it could have been.
And the Wake Tech bridge collapse continues to serve as a reminder to the engineers of the future.
One of the things I tell my students is that as engineers, we need to make sure that we understand construction practices as well as our materials, as well as our structural calculations. You can design the best building, but if no one can construct it, it's not going to matter.
From the longest bridges to the tallest towers and everything in between, engineers are in a constant battle with the forces of nature. Any weakness can be exposed without warning. Like this fail in Denmark, which span out of control.
This wind turbine was almost 20 stories high, but it came down in seconds.
The disaster exposed an industry-wide weakness.
It really shows what the wind is capable of.
Engineers were left reeling. Just how had this happened?
It went so fast that it looks like an explosion.
Wind energy. It's clean, free, and vital to our future. Once basic and inefficient, wind turbines have come of age.
Modern wind turbines are truly state-of-the-art, And although the concept is simple, the engineering behind these things is highly complex.
Sandwiched between the North and Baltic Seas, Denmark was an early pioneer in wind energy. Stefan Jorgensen is a local journalist.
Denmark is one of the leading countries in wind energy, and we have been setting up windmills since the 70s, first on the land side and in the recent years also on the sea.
Key to their success is a reliable supply of wind.
Denmark is a quite flat country, and as you can see, there's water around Denmark and everywhere, so there are quite a lot of possibilities to set up windmills in Denmark.
The Riso research station, run by the Technical University of Denmark, or DTU, has been at the heart of the wind industry for 40 years. And it's where Professor Martin Hansen battles the elements.
The wind turbines are very important for Denmark. This is where the first wind turbines were tested and certified before they were allowed to be erected.
The now familiar three-bladed layout became known as the Danish concept. But whatever the name, wind turbines work the same way.
The blades essentially take energy from the wind, turning a gearbox connected to a generator, creating electricity.
The first thing we need to do is to slow down the wind. That means a wind turbine must create a force that is opposite the direction of the wind, and that stops the wind and steals kinetic energy from the wind. We can create this by applying 3 rotor blades here that are shaped as airfoils on an airplane.
These blades aren't just shaped like aeroplane wings. They essentially are wings and fly through the air.
When the wind approaches this airfoil here, comes in with an angle here, it accelerates around this, we call it the leading edge, and that creates a suction. So this blade are actually sucked forward. So the higher is the wind speed, the more is the lift, and the more power we can create.
The faster the blades fly, the greater the forces acting on them, which is perfect for making power, but it puts massive stress on the structure.
On a day where it's not a particularly windy day, actually there is around 100 tons of air passing this area per second, meaning that to stop that, you really need very, very large forces. We have to be very careful when we build these wind turbines.
The forces involved are so strong that every turbine has multiple braking mechanisms to stop them from spinning too fast.
It's required actually that you have an aerodynamic brake on all wind turbines. If we lose the torque from the generator, then there's no torque to stop the rotor. So it spins faster and faster and faster until it reaches a free running speed that creates large loads that may lead to failure. So to prevent this, there used to be a tip brake, meaning that we can turn the blade so that it actually acts like a brake.
The wingtip brakes would deploy, increasing air resistance to control the spin until other systems could slow the rotor.
Wind turbines are everywhere now, so it's easy to forget the technology is still evolving, and it hasn't all been a smooth ride.
On February the 22nd, 2008, a 60-ton turbine in northern Denmark was rotating much faster than usual. A local resident started filming. Journalist Stefan Jorgensen was living nearby at the time.
I remember that day back in 2008, this wind turbine just got spinning out of control for quite some time, and it looked dramatic.
With the wind getting stronger, the 30-meter blades continued to accelerate, exceeding 700 kilometers an hour.
The police already had made a perimeter for about 500 meters.
The turbine span like this for more than 2 hours.
If the brakes were working, it would never have reached that speed, or spun for so long. It was clearly out of control.
At the end, exploded, or what looked like an explosion. It really shows what the wind is capable of and how big the forces in the wind is.
The shattering machine hurled debris in all directions. Luckily, no one was hurt, but the entire turbine was completely destroyed. With turbines like this spread across Denmark, the government launched an investigation.
Denmark is at the cutting edge of wind energy, and these machines are packed with safety systems. So how could something so destructive have happened?
Professor Jens Sorensen was on the investigation team.
That day, they had registered that there was a problem with the mechanical brake, which is located inside the nacelle. So a service team arrived in the morning, and they start to look at that brake. They fixed it.
Having fixed the problem, engineers restarted the turbine.
The wind was very strong, so to keep the rotor under control as it restarted, engineers deployed the air brakes at the tip of the blades.
What you do is you activate these air brakes that you have here, so you can run it up in speed without it starts to run too fast. So you can, so to say, control the speed.
But things were soon far from controlled.
They heard some noises from the gearbox, and they knew there was a problem. And suddenly this gearbox simply blocked the rotation of the wind turbine.
The gearbox failed, instantly stopping the rotor, tearing the air brakes from the blades.
The rotor simply stopped to rotate. These air brakes, because of inertial forces, so they simply broke off.
The loss of the gearbox and air brakes explains why the turbine was spinning so fast. But what caused it to self-destruct?
So it was, while running so fast, it was subject to very, very strong forces. So it starts to bend, and at a certain point, one of the blades simply more or less exploded. And then you have two blades left, and when this happens, then they start to vibrate heavily, and one of the blades went into the tower and broke off, and everything broke off. It went so fast that it looks like an explosion. But if you go pinpoint into small details, you can see exactly what happened. So it's probably the worst accident that ever happened with a wind turbine.
One obvious question was whether the service team had made a mistake. According to Jens and the investigation, that was not the case.
It's a combination of many different accidents happening at the same time, so it's very unlikely it would happen. It's a mechanical error. There's no evidence that it's a human error.
No one could have predicted the gearbox would fail, ripping the air brakes off. With such huge forces at play, the turbine was doomed.
The catastrophic failure did, however, reveal that existing brake systems were flawed.
The accident caused people to question the safety of wind turbines, but Denmark was relying on them for a greener future, so things had to change.
One thing was for sure, the movable blade tip air brakes had to go. The smart solution was to make the whole blade the brake.
Today you have a pitch motor here that can actually turn the whole blade. But also we can use them as brakes, because if you pitch the whole blade so that it's 90 degrees out of the wind, then the whole blade acts like an aerodynamic brake. And thus such a thing as happened on the Hornslet can never occur on such a wind turbine.
This catastrophe was caused by an unpredictable chain of events. But engineers also spotted a flaw in the system, and in fixing it, they helped improve the entire wind power industry.
The outlook of Danish wind power and wind turbine in general is actually very, very bright. Wind turbines and wind energy will just keep on growing.
Some epic structures go wrong after the construction teams are long gone. But others fall early in the game. Like this mammoth construction project in Texas, a vital link brought to a grinding halt.
There's one little flaw in the bridge, and you could have just an absolutely catastrophic situation.
This project barely got off the ground.
The independent reviewer said that the settlement calculations were quite a bit off.
I think what we can say about this bridge is that Houston, we have a problem.
Houston, Texas, established around sluggish bayous that drain into Galveston Bay and the Gulf of Mexico. Local transport journalist Gail DeLaughter knows what makes Bayou City tick.
Houston is America's 4th largest city in terms of population. There's parts of the city that are very urban, other parts that sort of have a rural character about them. This is also part of the city of Houston as well, the refinery activity and the industrial activity.
One waterway is crucial to the city's industrial success, the Houston Ship Channel.
Literally billions of dollars in economic activity every year comes through the Houston Ship Channel, and there's a lot of development all along the route.
About a century ago, the Ship Channel was the sluggish, swampy Buffalo Bayou. But engineers have transformed it into one of the most important waterways in the U.S.
Civil engineer Matt Yarnold is heading out to get a bird's-eye view of this essential waterway.
The Port of Houston is a big economic driver for the region. It's responsible for about $265 billion to the economy of Texas, as well as employing over 1 million people within the state. What they say about Houston, it was the town that built a port, which built a city. So the port itself is a big factor for the size of the city and the tremendous growth of the last 100 years.
As industry drove a population boom, bridges sprung up to cross the channel. One of the most important is the Sam Houston Ship Channel Bridge, which opened in 1982 to carry the city's Beltway 8 toll road over the water.
So out my window here you can see the existing Ship Channel Bridge. It's actually a segmental concrete box girder bridge built roughly 40 years ago. It's actually in excellent condition, but the bridge itself is rather narrow.
With just 2 lanes in each direction, the bridge was struggling to meet rush hour demand.
You have the usual vehicular traffic, the people who live here, but then they're on the roadway competing with a lot of trucks that are coming in and out of the port.
The city needed more capacity, and in 2018, construction began on a brand new 8-lane bridge. But it wasn't going to be cheap.
The price tag for the new bridge is about $1 billion. It's the most expensive infrastructure project that Harris County has ever undertaken.
The epic price tag would buy an epic bridge like no other, with unique curving pylons over 150 meters high, towering above the twin road decks, in a design known as a cable-stayed bridge.
Basically, there'll be large pylons or towers that are going to come out of the riverbanks, and major steel cables will come off it, which will support the deck system below. So you can see in the background here, you can see the pylon just coming out of the ground adjacent to the bridge.
The eye-catching design isn't just good to look at.
The cable stay design allows for a longer and higher main span than the old bridge, giving more clearance for the ship channel below, while the twin decks double the amount of road space.
The new bridge will actually have 4 lanes in each direction with much wider shoulders, so the traffic capacity will be greatly increased.
The project is as ambitious as it is unique.
A bridge of this scale has a number of challenges, both from the design side as well as construction. Building towers 500 feet off the ground is no small feat, in addition to a structure that's spanning well over 1,000 feet.
But the biggest hurdle engineers faced with the whole project was getting the old bridge out of the way. This billion-dollar bridge faced a million-dollar question.
The existing bridge can't be closed until the new one is built, and yet it stands exactly where half of the new bridge needs to go. The solution was pretty audacious. Essentially build it like 2 bridges.
The new bridge is being built parallel to the old bridge. The intended staging is to build the first half, switch traffic from the old bridge to the new bridge, and then demolish the old bridge and then build the remaining half of the new structure.
With construction well underway on the first half, the project hit a major setback.
They started working on the bridge in 2018, and then they did a design review about $400 million into this project, and they found about 21 different structural problems that would have to be dealt with.
With alarm bells ringing, city planners hit the brakes.
They decided to just go ahead and shut down everything on the bridge, all the construction on the new bridge, until they can figure out what to do about those design flaws.
You don't shut down work on a project like this without a good reason. Something must have gone badly wrong.
Close inspection revealed that 3 key elements of the design were flawed, starting with the foundations, which would settle more than expected.
Settlement is exactly what it sounds like. The weight of the structure causes it to sink a little.
Settlement is vertical movement of the foundation. As you impart significant loads onto the soil, in this case it is on pile foundations, which will minimize some of the settlement, but if the structure then goes downward and then of course moves the components and parts of the structure, which can induce stresses and other issues into the bridge.
Every new structure settles up to a point. But if it goes further than expected, it can have serious consequences.
In this case, the independent reviewer said that the settlement calculations were quite a bit off, which would affect the remaining stages of construction.
Settling wasn't the only problem. The review found the design didn't fully account for sideways or lateral forces.
The lateral loading is critical when designing a structure like this. The 2 primary lateral loads that we account for in bridge engineering is seismic loads and wind loads.
Houston has never suffered an earthquake, but wind loading was one of the key factors in this bridge design, especially in a hurricane hotspot like Houston.
The critical components are where the deck system attaches to the vertical element known as a pylon, so you can have excessive stresses and potentially cracking in this region, as well as those forces need to be transferred all the way through to the foundation, so you can have other points of stress and concern, and even down into the base of the structure.
As well as having soft foundations and being vulnerable to strong winds, there were also concerns about the main cables supporting the bridge deck.
The independent design reviewer questioned the slip resistance of the main cables. That's essential because if you can imagine, all the main cable system is in significant amount of tension, and if you were to release and have a slip and release that tension, that force is then transferred into the surrounding cables.
Any problem with the cables would have a domino effect throughout the entire structure.
If you can imagine live load such as this, imparting a vertical force downward on the structure, it's going to put tension into the main cables, and it's going to impart a compressive force in the deck system. All these tensile forces are then pulling on this vertical element known as a pylon, which then puts it into significant amount of compression and then forces everything into the foundation.
There are so many massive forces constantly at play on a structure of this size that every detail, from the cables right down to the foundations, has to be absolutely right.
And with more than 100,000 vehicles a day projected to cross this new bridge, even the smallest imbalance could have disastrous consequences.
With $1 billion and potentially thousands of lives on the line, engineers were left with no choice but to put the brakes on the entire project.
It is crucial to take care of these things at an early stage because just imagine if there's one little flaw in the bridge, it leads to another flaw, it leads to another flaw. You could have just an absolutely catastrophic situation.
With such fundamental problems, new designers were brought in for a fix. The new team came up with a series of retrofits that will be built onto the already completed bridge sections. Crucially, all the potential dangers have been ironed out.
It is a good thing that they found these things in advance, one for public safety as well as for the long-term performance of this particular structure. Had this not been uncovered and been uncovered after the fact, the situation could potentially be much worse and, of course, more costly.
No matter how beautiful that bridge is, if it's not built to serve its purpose, it's useless.
With the new plan in place, Houston no longer has a problem and hopes to have its trailblazing new crossing open to traffic by 2025. In Oklahoma, a deadly disaster on a major freeway.
Driving along at 70 miles an hour and the whole world opened up.
In the UK, the Royal Air Force races to save a town.
They were huge concrete slabs smashed apart by the water. The dam could have broken at any time.
Near New Orleans, a devastating explosion rocks a community.
The silos were in flames, and there were helicopters lifting men off the burning silos.
And in Australia, tragedy strikes on a runaway train.
I kind of remembered a bang. Next thing I came to lying on the window on the other side of the train.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers constantly strive to build bigger, bolder, and crucially safer structures. But sometimes catastrophe strikes when and where you least expect it. Like this deadly disaster in Oklahoma on one of the state's busiest crossings.
It just collapsed right in front of me and people were driving off into the river.
A catastrophe that took down a vital bridge.
We had no idea how many people we had in the water, how many vehicles. Nobody knew. It was quite a shock.
And a devastating tragedy that took everyone by surprise.
Nothing's indestructible. Everything has got its limits. We can break anything.
The Arkansas River is Oklahoma's largest waterway, and for small towns along its banks like Webbers Falls, it's all about enjoying the great outdoors. Norman Barton Jr. is a lifelong resident.
I grew up on this river, fishing, hunting all around it all my life. My dad used to tell stories about changing my diaper in the boat. This is home to me.
The Arkansas River is fantastic for more than just recreation and fishing. Every year, around 12 million tons of cargo are transported up and down the stretch of water.
We're in farm country. We're in coal country, steel country, all that, and it all travels up and down this river. And it's amazing if you sit out here and watch these barges. It's commerce at its finest.
And it's not just the waterway carrying cargo. Crossing the river is the I-40, a vital road link around 3 kilometers south of Webbers Falls.
The I-40 is the third longest interstate in America's highway network. It runs more than 4,000 kilometers, almost coast to coast, from California all the way to North Carolina.
The bridge was built in 1967 to keep traffic moving above and below. 4 lanes for vehicles and a nearly 100-meter wide shipping channel with the bridge towering over 18 meters above to allow larger vessels underneath. Former Fire Chief Jack Shackelford remembers it well.
Actually, I was growing up down here when they built the highway and the bridge. They had to raise the bridges for the tugboats and the barges, and they rerouted the highways. Interstate 40, it was one of the major interstates through Oklahoma at the time when they first built it.
The more than 600-meter-long bridge sits on 12 reinforced concrete piers. No easy task, as Professor of Engineering Steve Tipton knows well.
They actually run those piers all the way down to bedrock. And they'll set a cage of reinforcement bar, dump a lot of the concrete in there, get these piers set in there. They, you know, when you look at them after they're up, you feel like, wow, that's indestructible.
Early morning, May the 26th, 2002, Memorial Day weekend. Norman Barton Jr. was competing in a fishing tournament south of the I-40 bridge. As Norman passed a buoy, he just happened to look up.
The bridge just actually collapsed right in front of me. Wow.
2 barges weighing more than 1,000 tons being pushed by a tug the Robert Y. Love had rammed into one of the piers 60 meters outside the main channel. The force of the impact caused a 150-meter section of the bridge to drop onto the barges and river below.
The next thing I know was cars driving off of it. They're driving along at 70 miles an hour and the whole world opened up. The bridge was gone and people were driving off into the river.
With cars and trucks in freefall, another fisherman grabbed his flare gun.
It just shot an orange stream up over the bridge and actually hit a truck right on the windshield. Just boom, and went up in the air. Well, that trucker jackknifed his truck on the highway, and that stopped traffic.
Quick thinking combined with a 1 in a million shot ground traffic to a halt. Former captain of Muskogee Fire Department, Jack Shackelford, was just coming off the night shift when he overheard a 911 call.
I heard the dispatch inside the station that there'd been a collapse at the Interstate 40 bridge in Webbers Falls, and I couldn't believe my ears, and they were calling for all help. So I asked the assistant chief on duty if it was all right if we took the rescue squad and came down here, and he said by all means.
But as they arrived on scene, the sheer horror of what they were facing was daunting.
It was quite a shock. The ramp going up to the bridge was still intact, but when we got to the top of it, the bridge was just gone. Where the barge had actually hit it, the bridge actually fell down on it and was sitting and was resting on the barge. And we had no idea how many people we had in the water, how many vehicles we had in the water. Nobody knew. You don't know where to start.
11 vehicles had either gone down with the bridge or driven off the freeway into the river. Norman found a truck driver trapped in his cab and about to go under.
He was just sliding, just trying to get a hold of anything before he went under that 400-foot boat.
Norman knew he had to act fast.
Tried to get a hold of his belt, but the current was so bad and he was just hanging on. But I finally got in the water, got a hold of him, and told my partner to get us out of here, get us out from under this thing.
But not everyone was so lucky. Rescue divers and anglers searched desperately to pull out anyone they could find.
Friends of mine that were pulling a guy into their boat. I mean, we looked, there was nobody else that could be saved. Nobody ever came up. There was only 3 people that you could actually saved, and we got them.
For Jack and the other teams, it was clear no one else was coming out.
We had to shift from being a rescue to total victim recovery. But it took all 4 days to get all the vehicles, to get them located, get them pulled out of the water, and to get the victims extricated from them.
Of the 19 people who went off the bridge, 5 survived, but tragically 14 died.
It's been a long time since I came by here with all these thoughts in my mind. I wasn't expecting to get emotional again like this. It's kind of bringing back some not so pleasant memories, I guess.
In the aftermath of the disaster, the first question was how had the Robert Y. Love missed the 100-meter wide navigation channel by so much?
Although huge, the barges were still only about 1/3 of the width of the shipping channel. The captain himself said it was easy to navigate and he'd safely done it hundreds of times. So the question was, what happened this time?
It turned out that while maneuvering the tug and barges to pass under the bridge, the captain of the Robert Y. Love suddenly lost consciousness.
Effectively, no one was steering, and the boat kept pushing the barges west out of the main channel, straight towards one of the bridge piers.
The barge left the river channel and actually hit this pier right here, knocked it completely down.
I don't know if he blacked out or passed out or what, but when he struck it, it just collapsed like a domino effect.
But how could one tugboat with 2 barges, traveling at around 10 kilometers an hour, take down more than 150 meters of concrete and steel? Professor of Mechanical Engineering Steve Tipton explains.
Nothing's indestructible. Everything has got its limits. You know, that material is just a bunch of atoms holding hands. If you push them hard enough to break their grip, they're going to come apart. That's kind of the way it works.
The culprit was the very material that gave the bridge its strength: concrete.
Concrete's brittle. That's a problem with it. But brittle material has a benefit that it can take compressive loading really well. The road's heavy and it's carrying that weight, and then vehicles go over it a lot and it's carrying that weight, but that's not a problem for those big columns. But if you give it just even a very light impact load, it can't handle it. That's just not what concrete's for.
These piers can easily carry the weight of nearly 20,000 vehicles rolling over them every day, but they're not designed to take sideswipes from massive barges.
These are just blocks made out of concrete. I can put it like this, and I can stand on this guy, and you know, it's plenty strong enough to take that load, right? But even with just a little bit of an impact load, just not much, just tap it, you practically tap it, and it goes. That's a pretty good example of how intolerant concrete is to impact loading.
While the main piers beside the shipping channel were protected by steel and concrete islands on the upstream side, all the other concrete piers had been vulnerable to impact for decades.
Concrete's got a lot of pores in it. Pores aren't a big deal in compression. The problem with them is that if you simultaneously give them a side load, any kind of a crack or a pore or a flaw will just take off. And now it's got this huge weight on top of it too, and you're done.
With a vital road link gone, the bridge needed to be rebuilt and fast.
It was absolutely amazing how quick they rebuilt this bridge. They ran crews 24 hours a day up here and rebuilt this bridge. I mean, literally pulled it out of the river.
Just 65 days after the tragedy, on July the 29th, 2002, the bridge was reopened, but this time with protection cells in front of all 12 piers, so that any wayward vessels would hit a cell and be stopped before it could damage the bridge.
When you've got a hazard, you have a responsibility to do something about it. So the number one thing you do about it is you try to prevent it. So that's what the barriers are for. They're sort of number one line of defense.
With the bridge piers now protected from all angles, the hope is that no barge or ship can ever threaten the bridge again.
A year after the disaster, a memorial was erected dedicated to the memory of the 14 people who sadly lost their lives.
This one was tough. It was really tough. It affects you. I mean, there's no other way to put it. It affected everybody.
You know, it turned into a terrible tragedy in a split second. But I was glad to be where I was at the time. I didn't want to be, but I was. Just the right thing to do.
When it comes to big construction, engineers are constantly striving to overcome the overwhelming forces of Mother Nature. Get it wrong and the results can be catastrophic. Like this disaster in the UK, a dam on the brink of total collapse.
You've got 1.3 billion litres of water spilling through the entire town.
Mass evacuation as an ancient town's future hangs in the balance.
Time was running out, the village would be gone. The biggest disaster since wartime history.
And the Royal Air Force rides to the rescue.
Clearly, the dam could have broken at any time. It was unfathomable the amount of destruction that it potentially caused.
The Peak District in England is one of the country's most beautiful hotspots.
The Peak District is the UK's oldest national park. Thanks to the stunning countryside, it's also one of the most popular, attracting more than 13 million visitors a year.
This rugged hill landscape gets high rainfall, and dams are a regular feature. Some are used for power, others for flood control. But Toddbrook Dam above the town of Whaley Bridge was originally built to feed a canal. Les Eckersley is a local resident and amateur photographer.
The Toddbrook Dam was built to supply water to the canal system that was used to transport coal and stone from the local quarries, so it's part of the UK's history.
During the Industrial Revolution, canals were vital for moving goods all over the UK. These man-made rivers had to be regularly topped up, so reservoirs like Toddbrook sprung up all over Britain.
Originally built in 1840, Toddbrook was made up of a solid core of watertight puddle clay, surrounded on either side by a much larger embankment of compacted earth. Dr. Andy Nichols is a water engineering expert.
That compacted earth provides mass and it provides strength to hold back the weight of the water that's behind it, while the puddle clay core is the waterproof part that prevents the seepage of water through the dam and onto the other side.
In the 1960s, a new spillway was built to carefully control the release of water in the event of flooding.
The reservoir can hold more than 1 billion liters of water, the equivalent of around 450 Olympic swimming pools. So like any dam, its spillway is crucial.
Made of large concrete panels 15 centimeters thick, the roughly 75-meter-long spillway was constructed over the central part of the dam by adding concrete capping to the earth embankment.
The spillway is designed to let large volumes of water escape from the reservoir in a safe way. In designing the spillway, we need to consider what's called the maximum probable flood, and we need to make sure that we design the spillway with the capacity to be able to discharge that amount of fluid without anything going wrong.
Late July 2019, heavy storms began raining down on Whaley Bridge and the Toddbrook Reservoir. Even for locals used to the British weather like Les, this was unprecedented.
This path we're on now is actually running at the side of the River Goyt. Would be underwater now. That's how high the water was. Typically, we do get a lot of rainfall, but that was pretty extreme.
While bad weather was forecast, this was relentless, with 2 separate storms dropping more rain than this area had seen in decades.
We saw a 1 in 43-year storm closely followed a couple of days later by a 1 in 92-year storm. And that resulted in a lot of water flowing into Toddbrook Reservoir.
The reservoir was at capacity and the spillway was hard at work.
In all the time I've lived in Whaley Bridge, I've never seen the actual spillway in action. It's a spectacular sight. I had to photograph and video it.
But while it might have looked spectacular, the spillway was struggling to cope. As engineers began pumping water out to reduce the reservoir's dangerously high level, it dramatically revealed the full extent of the damage to the spillway.
I could see that quite a few panels had collapsed and there was like muddy liquid running out of the dam.
As the hole got bigger, the structural integrity of the dam was under threat. A full-scale emergency was declared and 1,500 people immediately evacuated.
I thought it was just going to get worse and worse and just basically wash away and the village would be gone. The village would have been flushed away.
If the dam failed, more than 1 billion litres of water could engulf the already flooded town. Their only chance was an emergency plug in the spillway to hold the embankment in place. It was time for drastic action. It was time for the Royal Air Force. Flight Lieutenant Matthew Smith and his helicopter crew swung into action.
We've been briefed that the Toddbrook Reservoir had been damaged. We knew we had something to move. The success of the mission would be quite critical to how quickly we get up there and provide the services. In our minds, really, it was just trying to get underway so we could offer our support as quickly as possible.
As they reached the dam, there was no time to lose. The side of the spillway was now completely undermined.
They were huge concrete slabs smashed apart by the water. And clearly, the dam could have broken at any time.
With a last-ditch plan to add structural integrity to the dam, Matthew and the crew would have to drop hundreds of one-ton bags of rubble, 6 at a time, directly into the hole. A risky and uncharted operation.
The pilot had to hover this mammoth helicopter and its load directly over the damaged section of the dam.
If they missed the hole, they might smash more slabs, risking the integrity of the entire spillway.
The feeling of dropping 6 tons from an aircraft when you've never done it before, it's really quite unique. As soon as you press that button and release, you've got about 30% worth of power back from the engines, and that's an immense amount of power from the engines that this aircraft has.
These twin-rotor helicopters can carry more than 50 troops or 10 tons of cargo, no problem. But crucially, they normally have somewhere to land. Here, hovering so low, if something went wrong, there was nowhere to go.
In total, Matthew and the team dropped 600 tons of rubble and around 1,000 sandbags, successfully plugging the hole, saving not only the 188-year-old dam, but the town of Whaley Bridge.
The amount of destruction that this dam would actually cause if it did break, with 1,500 people living below the reservoir. For the mission we were trying to achieve, it couldn't have been any better.
The precision of the flying, there isn't many people in the world that can fly helicopters like that. We had a very lucky escape that day. Very lucky escape.
As the rains died down and people returned to their homes, everyone wanted to know how this disaster could have happened.
The concrete spillway was subjected to a torrent of fast-flowing water. But that's what it's designed for. So the big question was, why had it failed so catastrophically?
The UK government ordered an immediate investigation. They discovered a crucial part of the spillway's defence was missing, known as the cut-off wall or beam.
So we have the crest slab that sits on top of the dam, and then typically there would be a cut-off beam that penetrates from that crest slab and joins it onto the puddle clay core of the dam, meaning that there's a solid barrier that prevents any seepage of water through. But in this case, the original design didn't have one of those.
The cut-off beam acts as a barrier, connecting the crest slab with the waterproof clay core. Without it, water can penetrate under the spillway, washing away the earth, holding the concrete slabs in place.
A cut-off beam is like the sealant, plugging the gap between your bath and the wall. It's a similar thing here, only this time there's a lot more water with a lot more force that can do a lot more damage.
It was actually one of the lower slabs that moved first, probably because of the water causing sufficient pressure to lift that slab. And that was really the point of no return. At that point, that's where we had substantial flow of water through that then caused the concrete slabs above to collapse in.
With this ancient design flaw, the extreme weather created the perfect storm and the dam failed.
It's estimated that the water eroded around 800 tons of embankment until there was virtually nothing left to hold the slabs in place. Thankfully, a Herculean effort saved the dam and the day.
If those efforts hadn't happened to reduce the water level and to shore up the dam, then it's quite possible the earth embankment itself could have been eroded away. And in that case, you've got 1.3 billion litres of water that are rapidly, in a case of a few seconds or minutes, spilling through the entire town of Whaley Bridge.
With the disaster averted and the water levels reduced, a new spillway will be constructed at an estimated cost of around £14 million. In addition, new proposals were put forward for the maintenance of the UK's entire ageing dam network.
Like Toddbrook, many of these dams were constructed more than a century ago. It's now recommended that engineers inspect them at least once a year.
And while the Royal Air Force frequently flies to the rescue, hopefully they'll never have to do it again, quite like this.
We train day in, day out, and 9 times out of 10 it is troops and operations, and I've flown all around the world. This is the first time I've ever done it in the UK, and seeing a difference and knowing that you're stopping that dam collapsing, potentially destroying people's homes, livelihoods, I don't think there's any other feeling like it.
With any structure, engineers walk a tightrope between function and safety, but sometimes getting the balance right proves impossible. Like this tragedy in Louisiana that ripped through the heart of a community.
The silos were in flames, and there were helicopters lifting men off the burning silos.
A massive catastrophe triggered by something seemingly harmless.
You don't ordinarily think of a loaf of bread as a bomb.
A disaster that helped force a change in the rules.
The destructive forces at work here are truly unbelievable.
New Orleans, founded by the French in 1718, owes everything to the mighty Mississippi. Journalist John Pope is a lifelong resident.
The Mississippi River is the most famous river in the United States. You've got songs written about it, you've got books written about it. Showboat, Tom Sawyer, Huck Finn, Life on the Mississippi, and that's just for starters.
But there's a lot more to the Mississippi than its cultural legacy.
The river is continually busy with maritime traffic. Everything comes down the river to New Orleans and then out to the Gulf of Mexico and the rest of the world.
One of the most valuable goods is grain.
Every week, almost 1 million tons of grain, like wheat and corn, is barged down the Mississippi. That's 60% of the nation's grain exports.
And key to moving it all are massive structures called grain elevators. This giant facility at West Wego, just upstream from downtown New Orleans, was first built in 1960, and today stores over 4 million bushels of grain. Although vast in scale, the process is simple.
Essentially, a grain elevator scoops grain from the bottom of the barge up into massive storage silos. At its heart is a constantly operating system of conveyor belts and bucket lifts.
Engineer Tim Duncan is an expert in the design and management of marine terminals.
Transport the grain to what we call a bulk scale. Bulk scale weighs the grain and deposits it onto another belt conveyor that then transports it across the levee to this head house, ultimately to belt conveyors that deposits grain into individual silos. In essence, it's barge to silo, silo to ship. There's only a little bit of process. The grain that is shipped out of these facilities essentially feeds the world.
West Wego has been home to grain elevators since the late 1800s, playing an integral part in global grain supply. But it's also the site of an event that forced this massive industry to change forever. December 22nd, 1977, West Wego grain facility operations were underway, and employees were looking forward to the holidays.
Continental Grain had a custom of giving turkeys to its employees. So a lot of people had come to the grain elevator and pick up their turkeys.
But around 9:05 a.m., the festivities were suddenly cut short as a massive blast shook the city. Journalist Bruce Nolan was at home at the time.
I heard the deep, deep concussive whomp, completely irregular, clearly something badly wrong.
The giant grain elevator at West Wego had exploded. Journalist John Pope rushed to the scene.
When we arrived, the silos were in flames, and there were helicopters lifting men off the burning silos.
First of all, I see enormous plumes of smoke. I can see the tops of the silos. They're topped with wreckage. Black smoke is pouring out the top of the elevator.
A powerful blast had completely destroyed the 25-story grain elevator.
It's a mess. It's completely wrecked. It's so badly mangled that it doesn't even compute. I've never seen a concrete structure this massive, broken, like a child's toy.
The tops had been blown off 48 of the giant silos.
People who witnessed a blast across the river, they watched debris from the blast arcing into the sky and dropping all up and down this stretch of river.
Rescue crews worked tirelessly day and night, but tragically 36 people lost their lives. Only 11 survived. This was one of the deadliest industrial disasters in American history. Yet the machinery had simply been moving and storing grain.
Many times people don't think that a grain elevator, which handles corn and wheat, can be explosively dangerous. But they can be. They are very dangerous.
Operators have long known of its highly volatile qualities, and it all comes down to tiny particles of grain dust.
Any transfer from conveyor to conveyor accomplishes a couple of things. It not only damages the grain is relatively fragile, it also produces dust.
Grain elevators are scooping and pushing and shoveling and disturbing and agitating thousands of tons of wheat, corn. The dust is billowing into the air from the operation.
More explosive than gunpowder, confining enough grain dust within one place can be deadly.
If you take a loaf of bread, you divide it into tiny motes of dust. Each one of those tiny motes can burn if subjected to ignition. When a billion motes of dust all ignite at the same instant, that's the definition of an explosion.
An explosion like this needs 4 key ingredients: fuel, that's the grain dust, oxygen, which is all around it, a confined space like a bomb casing, here that's the concrete structure, and then all you need is a spark.
Pinpointing the exact source of the spark among the devastation was impossible. But one obvious suspect was the elevator system itself.
My understanding of the explosion in West Wego is that there was a problem with the bucket elevators. And a bucket elevator is a series of buckets that are bolted to a conveyor belt with pulleys at the top and at the bottom. Perhaps there was a belt misalignment, a pulley, which caused either a spark or a hot bearing or a fire that ultimately lit the chamber and caused the explosion.
Some also questioned whether a recent change in regulations may have been a factor.
Grain dust in the atmosphere is a known health hazard. It causes multiple respiratory problems. In the 1970s, the Clean Air Act came into force, and buildings had to be made more airtight to better contain grain dust.
Vacuum systems had been installed to recycle the dust, and ventilation in the elevator and silos where dust could previously escape was closed up.
At the time, some questioned whether the new regulations had made things worse. First, there was more dust, or fuel, inside the structure than before. Secondly, and more crucially, it was more confined. When it went, it was truly like a giant bomb going off.
Following the disaster, new industry guidelines and national regulations were introduced for the containment and controlling of grain dust at elevators.
All the motors are in the right atmosphere, are explosion-proof motors. There's even lightning protection. Even your phone isn't allowed unless it's wrapped in an explosion-proof case.
More than 4 decades later, the elevator at West Wego continues to process grain. standing as a memorial to the people who lost their lives on that terrible day.
I spent a career as a newspaper reporter, and you see a lot of bad stuff. But if I think back about all of the really shocking, spectacular stuff, this Continental Grain Elevator explosion still belongs somewhere on page 1.
In big engineering, planning for every eventuality is a key consideration. But sometimes even the best laid plans can go disastrously wrong. Like this catastrophe in Australia on an out-of-control commuter train.
I kind of remembered a bang. Next thing I came to lying on the window on the other side of the train.
This tragedy revealed a flaw in a vital security system.
90 seconds after departure, it was an unguided missile. It looks as though the train ran away.
And forced a change in the safety regulations. The Royal National Park, just south of Sydney in New South Wales, is the third oldest national park in the world. In the 19th century, the small town of Waterfall sprung up on the outskirts as a camp for workers building the Illawarra rail line.
The Illawarra line was built in the mid-1800s to connect mining and farming businesses with Sydney.
Laying a rail track through the rugged landscape was a major engineering challenge. Railway operations analyst Alex Wardrop explains.
The great difficulty is that you have to cross the Illawarra Escarpment, which is very steep. And so the railway was built on severe grades with lots of tunnels.
Building a track through the carved-up terrain wasn't easy. Cuttings, tunnels, gradients, and curves pushed rail engineers to the limits.
The terrain wasn't just a headache for engineers. It's a challenge for both the train and driver.
Trains work best on straight and level tracks where they can run smoothly and the driver can see what's coming ahead. As soon as any curves and slopes are involved, things get more complicated.
The issue about driving trains is that you have to be aware of your gradients and speed limits. Trains don't have very good braking compared to road vehicles.
Despite the slopes and curves, trains safely navigated the tricky route for more than a century. January 31st, 2003, an early morning Tangara-class passenger train was heading south from Sydney to Port Kembla. Shortly after 7 in the morning, the train passed through Waterfall. Journalist Noni Walsh was heading home.
I suddenly noticed that the train was going a little bit fast and you could see people going, that's a bit odd. And I kind of remembered 2 corners and maybe a bang, but that was the last thing I remembered.
At 7:14 a.m., about 1.5 kilometres from the station, the 4-car train with 47 passengers on board derailed. South Sydney Fire Rescue Chief Superintendent Paul Bailey was on his way to the station house.
I was driving to work and over the radio heard the call about the incident at Waterfall. I was 10 minutes away, so I responded to the incident.
As Paul arrived on the scene, it was clear that a major disaster was unfolding.
We saw the back half of the train still intact and still on the rails, but as we walked closer, we saw the first couple of carriages had actually derailed and toppled over onto their side. We weren't sure at that time how many people were trapped or indeed what the situation was.
Among more than 150 tons of mangled metal, Noni was a trapped passenger and injured.
It was pretty eerie and quiet when we came to. I blacked out, and apparently that's a good thing because my friend told me later he was actually on his knees on the window watching the rails go past, terrified. And I'm so glad I didn't see that.
Paul and the other rescue crews swung into action.
It was quite traumatic for those people because not being able to get out of the train, they don't know if it's going to catch fire, they don't know what's going on. So our major concern was to ensure that those people were removed and get them away from the scene as quick as we could.
As Noni was pulled from the train, she realised the full extent of the devastation.
And it was really only then that we saw we were in something much bigger than we really knew about. It was, yeah.
Of the 47 passengers on board, 41 were injured in the wreckage. But tragically, the driver and 6 passengers died. This was a regular route with more than 50 passenger trains a day. An investigation was launched to find out what went wrong. Rail operations analyst Alex Wardrop was an expert witness.
The accident was unusual in that there was no collision or anything, and yet 90 seconds after departure from Waterfall, the train was a crumpled mess.
With no obvious track damage, investigators turned to one of Australia's leading engineering software companies. Technical director Dr. Jindong Yang and his team created an accurate simulation of the event.
We were tasked to simulate a number of scenarios to determine the most likely cause of the accident.
Running the simulation at different speeds revealed a key piece of information. Instead of slowing down, as the train approached the curve, it was gaining speed at an alarming rate.
The speed limit around this cutting was 60 kilometres an hour, but when the train took the curve, it was travelling nearly 120.
That made the train turn over and derail. The wreckage, the simulation showed very similar amount of damage on the carriages to what really occurred.
After it started to accelerate, it just continued to accelerate, and gravity did the rest. So by the time the train reached the critical left-hand curve, its speed was such that it was an unguided missile. The train rolled somewhere between 117 and 118 kilometres an hour.
But one big question remained. Why was the train going so fast in the first place? It turned out that before the crash, there had already been a tragedy on board. The driver had suffered a heart attack.
Before the accident, the driver unfortunately had died.
But trains like this have safety systems in place to trigger an emergency stop, the so-called dead man's brake floor pedal.
The dead man's brake is a safety switch that stops the train if the driver becomes incapacitated.
If he let go, the brakes would be immediately applied, and that didn't happen.
The investigation discovered that there was a flaw in the fail-safe system. As the driver slumped forward instead of releasing the dead man's pedal, his weight was still pushing down on it.
So it didn't matter if he'd slumped off, the driver safety device didn't cut in. And so it was clear then that the cause of the accident was the driver safety device did not detect that the driver was incapacitated.
And this wasn't a one-off failure. Further analysis revealed that all Tangara-class trains suffered from the same problem. After the disaster, new fail-safe switches were designed which would automatically hit the brakes if there was no response from the driver, safeguarding against any repeat of the tragedy.
That was inevitably the root cause of it. The dead man's handle didn't recognise that the driver had had a heart attack, and it allowed that train to continue to accelerate. They changed significantly the way that their dead man handle worked on the train. So I think that was a good thing.
In Texas, a suburban road collapses without warning.
Man, if it's a sinkhole, how big is it and how much bigger is it going to be?
In the UK, a cutting-edge build goes back to square one.
the ground underneath it had actually started to move. We were absolutely shocked.
One of America's most deadly disasters strikes in Missouri.
And that put my eyes right on the second floor walkway as it began to break apart.
And in Iowa, work on a crucial safety project grinds to a halt.
The number of crashes at this location were more than double the statewide average.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. In the pursuit of audacious builds, engineers take on ever more unique challenges. Any mistake could lead to catastrophe. Like this tragedy in Missouri that left a nation reeling.
I was not ready for what I saw. It looked like a war zone.
Miscalculations combined with a change of plan had devastating consequences.
The Hyatt Skywalks disaster is one of the great disasters in American engineering history.
Kansas City, Missouri. Once famed for its cattle markets, the city became a major destination for work and play. Michael Mahoney is a local TV reporter.
Kansas City is a place where lots of people from the Midwest either come to work and try to develop careers here, or they come here for visiting because it's one of the nearest big cities.
One big draw has long been music.
In the 20s, during Prohibition, Kansas City was sort of like Las Vegas. Anything goes. We had lots of late after-hours nightclubs, and the sort of jazz that developed here was called the Kansas City Jazz, and it's based off blues, and it's very distinctive.
In the 70s, as Kansas City's popularity boomed, distinctive new architecture began to appear, including a new luxury hotel. When it opened in July 1980, its 45-story tower dominated the skyline.
At the time, the tower was the tallest building in Missouri. It even had a revolving restaurant perched at the top with views across the whole city. But the architectural ambition didn't stop with the exterior.
Attached to the tower was a vast atrium, 15 meters high, designed to draw the crowds.
They wanted some piece of architecture, some piece of that lobby, so that when somebody would walk into it, they would go, goodness. And what they had here were these suspended walkways, 3 of them.
The suspended walkways gave stunning views of the space below, which in music-mad Kansas City doubled as a dance floor.
The concept of floating floorways above the lobby wasn't just truly spectacular, it was a serious engineering challenge too.
Kathy Hagan is a structural engineer.
There were 3 walkways, one at the 4th floor, the 3rd floor, and the 2nd floor, that just connected so people could walk across and get back and forth between those 2 areas. The walkways were hung with rods that were placed at quarter points, and they were about 1 1/4 inch diameter steel rods.
The 3rd floor walkway hung alone, but the 4th and 2nd were suspended together.
The rod was supposed to start at the 4th floor and go down through the 4th floor walkway and then down to the 2nd floor, and it was supposed to be one continuous rod.
The plan was for 6 14-meter-long rods to hang from the ceiling. The top walkway would slide up the rods with steel box beams supporting the deck, all held in place by large steel nuts. The lower walkway would then be lifted onto the same rods and attached the same way.
The fact that these walkways had no support from the ground and seemed to hang in space made the impact even more impressive.
The trailblazing hotel was completed in 1980 and soon became the place to be.
The intent of it was to have people come down on a Friday night and have a couple of drinks after work and enjoy the music and dance. And the word got around that this was kind of a cool thing to be doing in Kansas City, a way to kick off your weekend.
July the 17th, 1981, the hotel's Friday night tea dance was in full swing. Michael was covering the event for local news.
They had a good crowd. They had well over 1,000 people, no doubt about that. There were people up on the walkways looking at the vista down underneath of all the people dancing.
Just after 7 p.m., Michael and his crew were taking a quick break.
What we were doing was changing the batteries of our camera gear so that we could do the interviews. And at that point, I heard this really sharp pop, pop. And it was not a sound that was coming from the band. It was just an alien sound to the environment. And I immediately looked up to where I saw or felt like I heard the source of the sound. And that put my eyes right on the second floor walkway as it began to break apart. And I could see the second floor walkway begin to sag and then break apart a little bit. And at the same time, that part of the collapse also drug the fourth floor walkway down on it, and it slammed into it. They both dropped suddenly to the ground.
The second and fourth floor skyways had completely collapsed.
Two things were really, really memorable. Number one was the dust. The lobby of the hotel, just filled with this pretty thick cloud of dust. And then the other thing that was striking was the silence.
Fire department.
Okay, would you please call me to the Hyatt Regency? Have you been called yet?
No, what's the problem?
Okay, 3 of our sky bridges have fallen. We have injured people. Can you come right away? We're on the corner of Pershing and McGee.
A police officer at the time, Joe Kern, was one of the first to be called.
I got paged and told me to get to the Hyatt immediately. They had a major disaster. There was officers outside trying to control the traffic, trying to keep people out of there. But I was probably the third or fourth that actually walked into the lobby, and I was not ready for what I saw. It looked like a war zone. It really did. It looked like somebody had just shot a big old bomb in there and just blew the place up.
216 people were injured in the catastrophe. Tragically, 114 lost their lives.
"42 years on Kansas City Police Department. It is the worst disaster that I have ever dealt with. I have never been back in that building.
It's difficult to comprehend the scale of this tragedy. This is the kind of disaster that every engineer dreads.
The Skyway collapse was the worst construction accident in US history.
The Hyatt Regency collapse at the time it occurred was the most devastating loss of life due to an engineering failure on record.
In the aftermath, state and city officials called for a thorough investigation. And the first clue was right above their heads.
The steel hanger rods were still attached to the roof, some with the nuts still in place. So if the supporting rods hadn't failed, the problem had to be with the walkways themselves.
After examining the walkways, investigators found unexpected damage. The box beams were splayed at the ends, where the hanger rods had once been connected.
The box beams were made of two halves known as channels, welded together top and bottom to make a box. But the welds were ripped and the boxes had split open.
Investigators believed the collapse initiated at the connection known as 9UE, which showed both buckling of the beam and torn welds.
So if you're looking like through the end of it, there was like these two channels that were back to back, and the bolt basically went through here and the legs of those channels just bent up. It pulled through that one, and then it pulled through this one.
Calculations from the design phase found that these beams could support the walkways, but clearly they weren't up to the job. The question was why?
It seems the calculations were flawed and the connections were weaker than expected, but that wasn't all. Further investigation revealed there had also been a crucial design change made during construction. As a result, each hanger was made from not one, but 2 rods.
So this is a schematic drawing of the change. So this would have been the original rod going through the 4th floor walkway and the 2nd floor walkway. And then each bolt would have basically had that level's weight on it.
In the designs, one 15-meter-long rod supported both decks at each connection. The new layout used 2 rods, one from the roof to the 4th floor, a second from the 4th to the 2nd floor.
When they changed it, they went to 2 rods. So they had the first rod that came down, and then they offset that. And so then this rod, this bolt basically carries the load of this floor, but then this bolt basically carries 2 times the load because it carries this floor and itself. And so that was the initiation point of the failure that evening.
A good analogy is 2 people holding onto a rope. If each only holds their own weight, like the original plan, everything's fine. But if one hangs from the other, like the change, unless the top person is super strong, they'll both fall.
Investigators later discovered, even with the original layout, the walkways were barely strong enough to support their own weight. The switch to 2 rods was catastrophic.
The design change was requested because they would have had to thread the 4th floor on completely onto the rod, and it would have been very time-consuming and difficult to construct. So it was requested so it was easier to construct.
This change to the design probably seemed like a relatively small and practical solution at the time, but the consequences couldn't have been any bigger.
As the connections failed, the girders slipped down over the nuts, rendering them useless, triggering a cascade effect, bringing down both skyways. After the disaster, the whole atrium required major repairs. But in time, the skywalks were replaced, although with lessons learned from the tragedy.
The 2nd and 4th floor walkways were completely redesigned and rebuilt, this time supported by columns from below instead of hanging from the sky.
For the people of Kansas City, the tragic event of 1981 will never be forgotten.
We're at the Skywalk Memorial. This is actually the first time I've been here since the night of the tragedy. On each side of the pillars, there's the names of the people that lost their lives.
It's a true reminder of the responsibility that everyone takes on when it comes to building big structures.
The Hyatt Skywalks disaster is one of the great disasters in not only Kansas City history, but American engineering history.
Catastrophe can strike long before construction crews leave the site. But some lie lurking, a disaster waiting to happen. Like this tragedy in Texas, which appeared out of nowhere.
If anybody was to fall into this hole, they were going to get sucked underground and they were going to get taken.
An engineering fail with huge consequences.
There was no warning. This road just dropped into the hole.
San Antonio, Texas, a city with a rich past and home to one of the most iconic standoffs in US history. Local radio producer Jan Ross Piedad remembers the Alamo.
The Alamo is a big, big thing, not just for Texans, but now for Americans. For a lot of folks, it's a symbol of freedom and kind of fighting for independence.
But this historic city has its sights set on the future too.
So San Antonio has been up and coming in recent years. We're actually the 2nd fastest growing city in the country and also 7th most populous. San Antonio is a really amazing city.
With population growth like this come engineering challenges. L. David Givler is a civil engineer.
When you consider the history of San Antonio, it was a mission outpost under the Spanish, then it was a cowboy town, and today it's a thriving city. So there's been a lot of growth, and the old infrastructure of the past is just inadequate to support the current demands.
One piece of city infrastructure has been undergoing a massive upgrade: the sewage system.
In this case, there was deteriorating infrastructure, and because of that, a consent decree was issued for San Antonio to repair the sewer system. There were thousands of feet in each phase needed to be repaired, so it was an ongoing multi-year process.
San Antonio has a vast network of buried pipelines for water and sewage. Digging it up piece by piece and replacing it would be a mammoth undertaking.
In 2016, the infrastructure upgrade was going according to plan, but trouble was lurking beneath the streets. December the 5th, heavy rain was rolling through San Antonio. Mark Moody was on duty at the fire department when a call came in.
We were at the station, and it comes in. We look at the computer, and it says there's a sinkhole. Well, that's strange. It's definitely not something we make every day.
Mark sped to the scene.
The weather was nasty. Visibility was tricky. The biggest thought was, man, if it's a sinkhole, how big is it and how much bigger is it going to be?
What the team found was shocking. A massive sinkhole had swallowed the road and was filling with water. When Mark arrived, the area was already being secured.
The police department has shut down all the roads coming in here to about right here.
Mark and the team had no idea how stable the ground was.
I walked up to approach the scene so we could determine how close we could actually get to the scene with the trucks without having any problems. We had a car on that side of the road that was right side up, and then on this side right here in front of me pretty much was a car that appeared to be upside down. All I could see was a single tire.
Darkness and poor visibility had made it impossible for these drivers to spot the sinkhole. Fortunately, 2 people climbed to safety, but rescuers weren't sure if everyone had made it out.
Obviously, something was allowing water to rush into this hole. The water was spinning, and it was sucking down and going out. If anybody was to fall into this hole, they were gonna get sucked underground and they were gonna get taken. Water's kind of a strange thing. It can look not violent, and it can be extremely violent. I think that the water is probably the most dangerous thing we have that we deal with because it is so deceptive. Nobody was gonna be able to fight against that power of that water to get out of there.
Overnight, word spread about the sinkhole. The next morning, Jan arrived to cover the story, as Mark and the team tried to recover the inverted car.
It was just a cold December morning. We were just waiting on bated breath to see how it would go. It was a somber moment to be witnessing.
We brought our ladder out over the back of our truck. So from there, we sent a couple guys down on rope down to the bottom of the car and assessed it for stability, for ways that we could connect to it. Our guys were able to connect the crane to the car, and then the crane was able to lift the car up and set it down over here on the side of the road.
And I remember the car kind of rise up with all that brown water. Later for us to realize that there was a person in there.
When the car fell and rolled over, its driver hadn't stood a chance. As the city mourned, drivers were fearful of hidden pitfalls under their roads and wanted to know why this one had collapsed. One possibility was the very ground upon which San Antonio sits, as geologist Matt Cannon explains.
If you know much about the geology of San Antonio, you know that we exist in a sea of limestone here. Limestones are very easily dissolved by weakly acidic water, which leads to the formation of karst and sinkholes.
The limestone around San Antonio dissolves very slowly, but it's riddled with caves. And when the roofs get too thin, they collapse without warning, forming sinkholes.
Matt quickly realized there was more to this catastrophe than geology.
As soon as I saw images of the sinkhole itself and the aftermath of it, it was clear that this was a human-induced sinkhole. This was a pipe that broke and suddenly released an enormous volume of water underground. When you suddenly unleash that volume of water, moving at those speeds underground, the rate of dissolution of material is going to be very rapid, especially in unconsolidated sediment like what we had in this particular case.
The problem appeared to stem from a sewage pipe that had been undergoing renovation. L. David Givler was called in to investigate.
Here we have the original 54-inch or 4.5-foot diameter sanitary sewer pipe that was installed in the 1960s. The old pipe was concrete. The new pipe was something called FRP, fiber reinforced polymer. And this is a new junction box 4, which was also installed as part of the Phase 2 work.
The junction box joined the old concrete pipe and the new, much wider reinforced polymer pipe, but the temporary fix was flawed.
Corrugated metal pipe was used for the temporary connection here, but that's not standard. Metal pipe is almost never used in sanitary sewer systems. And the reason is because sewerage has gas dissolved in it called hydrogen sulfide.
When hydrogen sulfide mixes with bacteria from the sewage, it creates sulfuric acid, which is highly corrosive to some metals, and it had been eating away at the corrugated pipe.
Instead of acid dissolving the limestone, in this case, it had dissolved the pipe.
This photo shows the corrosive nature of the environment that was in the pipe and gives some hints as to how it deteriorated. It was an 18-foot pipe, and there were only a few pieces of it left after the acid had done its work.
Delays in the project meant the makeshift pipe was in place for 21 months, slowly being dissolved. But the material wasn't the only problem.
There's another complicating factor here, and that's that this connection at junction box 4 was not a secure connection. There wasn't any structural aspect of this connection that prevented the pipe from sliding down. And then this wasn't watertight, so this was creating a flow path for any leaking water to erode soil out and into the junction box.
The choice of material, combined with a lack of support, meant that this connection was never up to the job.
As the connection failed, sewage began to leak from the pipe, silently washing away the ground beneath the road with tragic consequences. The solution here was straightforward. The temporary connection was replaced with a permanent section and the road rebuilt above it. But it was an important reminder of how vital functioning infrastructure is.
When you just consider how people think about sewer lines, I mean, they're boring, insignificant, and here's an example of what can happen when the chemistry and the physics of the situation take over and disaster results.
That's the problem with buried infrastructure. It's impossible to monitor every last piece, and if something goes wrong, you might not know it until it's too late.
This tragic case caught the city's attention and prompted significant changes.
Billions of dollars were allocated towards having better sewage infrastructure, but it's also possibly a cautionary tale of making sure that when those plans are set, that the job is done right.
In engineering, construction success always begins with solid foundations. But sometimes the unexpected can sink even the best laid plans. Like this disaster in the UK, a building demolished just weeks before its completion.
This is the first time that I've ever come across a story like this.
An engineering fail that came to light at the 11th hour.
I was shocked. I thought, how could they mess this up that badly?
And a trailblazing build goes back to the drawing board.
Sometimes there's just no option but to start over.
The ancient city of Sheffield, England, for centuries home to a world-famous cutlery industry and the birthplace of stainless steel. Alana Roberts is a local journalist.
Sheffield is actually very well known for its steel industry and its steel heritage. A lot of the buildings around Sheffield are actually quite old.
As well as forging steel, Sheffield has a reputation for forging great minds, with a university population of around 60,000.
Sheffield is a very kind of student-focused town. The University of Sheffield campus really kind of stretches across the city. It's very well known. Everything kind of centres around the universities.
In 2018, the University of Sheffield unveiled plans for a new state-of-the-art building, designed with sustainability at its core. Jake Loader was an undergrad at the time.
When the plans for this building were announced, there was so much excitement from the students. It was going to be this massive, sustainable, really advanced technological building. We just couldn't wait to get in there and start to use it.
The structure's curved steel frame echoed the city's industrial past, but its staggered glass facade was more than cosmetic, designed to allow light in while keeping heat out, boosting the building's eco-credentials.
The building that we're using at the moment, it's dark, it's dingy, it's depressing. This brand new building is going to be incredible.
Construction on the £65 million project began in May 2019 on the site of an old sports field. Like any structure, it would rely on solid foundations with deep footings known as piles. Geotechnical engineer Jeffrey Pereira specialises in pile foundations.
Piling is done mainly to support and give the stability to the building. Just imagine that you're trying to build a house on a bowl of jelly. If you put the house on the bowl, it will just sink through the jelly. So what piling does is holds the house up such that it doesn't sink down.
With many projects, piles are driven down into the bedrock, creating a solid base to build on. But this wasn't a normal construction site. The groundbreaking build was above a former reservoir.
The reservoir had been there since the 18th century, but in the 1950s, it wasn't needed anymore, and the hole was filled with rubble. The messy ground was a real challenge for engineers.
The entire footprint of the building was above the old Godfrey Reservoir. The rubble fill, said to be from buildings bombed in the World War II Blitz, was less than ideal for sinking pile foundations into. Despite the complexities, the build was scheduled to take about 2 years. Due for completion in the summer of 2021, just in time for the new academic year.
We walk past it every day. Each week there was a new development, and it's ridiculously exciting. First of all, you've got the foundations, then the next week you can walk past it, you can see the concrete, and it got to the point where you could really see the building starting to take shape. We were all absolutely buzzing to get in it.
This was to be a world-class construction for a world-class university. May 2020, and work on the new building was making good progress. But just as the main frame was nearing completion, the build hit the brakes.
I woke up to a text from my mate in the morning. He said, "Have you seen the news that half the building was going to be knocked down? The ground underneath it had actually started to move." We were absolutely shocked.
Worse was to follow. In August 2020, with partial demolition underway, contractors announced that the entire building would need to be torn down. For local journalist Alana Roberts, this was breaking news.
The university and the contractor actually announced that there would be a full demolition of the site. It really shocked me that something like this could go on. This is the first time that I've ever come across a story like this.
It's normal for construction projects to go over schedule, over budget, or both, but to have to knock something down and start over, something must have gone seriously wrong.
I thought, how could they mess this up that badly? How can you make a mistake that big?
What had gone so wrong with this state-of-the-art structure? The The developers discovered the problem lay with the pile foundations. Geotechnical engineer Jeffrey Pereira explains.
Piling is like our legs for the building. If you have very strong and steady legs, then you hold the building out really straight and well. But if you have wobbly legs, then the building will tend to sway and eventually crack. So the better the legs you have, the better the support is for the building. It is really important to get your piling right.
Here, it seems the problem stemmed from the very early stages of preparation.
Like any construction project, ground investigation was carried out to make sure the project could go ahead, but given that they were building above a rubble-filled reservoir, it was particularly important.
To get a really accurate picture of the ground, engineers drill a network of boreholes so they can see for themselves what's underground.
The ground inspection was thorough, but as the structure was nearing completion, unexpected levels of subsidence were recorded.
We designed the piles to settle to within an allowable limit. We know that the building can withstand certain movement in the pile and yet still be fit for use.
The initial plans allowed for up to 25 millimeters of movement, but here the settling exceeded that in multiple places. For a building this size, it's unacceptable.
Every building will settle to some degree, but here it was a lot more than expected, and there was no way to be sure it wouldn't get worse with time.
The exact reasons haven't been revealed, but it's possible the ground investigations didn't paint an accurate picture of the rubble beneath.
In this case, some boreholes might have been drilled in places that didn't give a true reflection of the ground around it.
Accurate data about the depth of the bedrock would be crucial.
What potentially may have happened is that because there was no data available between these boreholes, you could have got a very deep cavern within the former reservoir. And imagine you piling to this level, you've got a pile that is just hanging in poor soil. When these piles are loaded, it's just going to go down.
If placed too shallow in poor soil or over an undetected void, the piles simply wouldn't do their job.
Because the piles were not deep enough and were not built into the competent soil, they kind of gave way and caused excessive settlement, and the building was deemed to be not fit for purpose.
With lessons learned and more reliable foundations laid, by 2021 building was once again underway. But starting over had pushed completion back by more than a year.
The residents nearby were actually calling the contractors the neighbours from hell because of the noise, because of the dust. They just had enough.
Now when I walk past the building site, that excitement's gone. I'm never going to get to use it. The excitement's been replaced by loud noises and rubble and dust. And it's frustrating. It's just a constant reminder that we're never going to get to step foot inside this building.
Ultimately, this is a reminder that every project comes with its own unique problems. You just have to hope you don't miss any of them.
With big infrastructure, every calculation is vital. Get one wrong and the whole thing can grind to a halt. Like this highway holdup in Iowa on a major safety project.
The number of crashes at this location were more than double the statewide average.
Mistakes that stopped construction in its tracks.
You're going to have, jackhammer off the top of the concrete pier.
This fail had drivers asking what had happened. America. Few things have shaped the nation as much as the automobile. It's now home to more than 250 million vehicles. Todd Wessel is a travel journalist.
Americans love their cars and they love the open roads.
They love the wide open spaces. They love to go out west and go into the mountains, and it's all part of being an American.
At more than 6 million kilometers, America has the biggest and longest road network on the planet. It's also home to some of the world's longest highways.
US Route 30 is the third longest highway in the country and stretches nearly 5,000 kilometers from Oregon to New Jersey.
It was the first transcontinental road in the history of the United States. It was built in 1913, right at a time when cars were starting to become the preferred method of travel. Its importance is immeasurable for our country.
Like every major road on Earth, keeping Highway 30 maintained has been a constant battle.
US 30 from Marshalltown to Ogden is a 55-mile section of primary highway in Iowa that needs to be modernized.
Highway 30 originally passed through every small town along the route. In the 50s, as traffic volume increased, one major bottleneck was the town of Ames, Iowa. Luckily, road planners had come up with ways to ease the flow.
One key improvement in the late 1950s was the building of roads that went around towns instead of through, known as a bypass. Bigger roads, less traffic, faster journeys.
Faster flowing traffic needed faster flowing intersections with no traffic lights or hard turns to stop vehicles in their tracks. Like this cloverleaf interchange at Ames, connecting Highway 30 with the key north-south artery, I-35. Tony Gustafson is an engineer with the Iowa Department of Transportation.
A key thoroughfare for the whole country, Interstate 35, and especially in Iowa, it carries a tremendous amount of traffic to keep Iowa, the goods and people flowing across the state.
Highway 30 and the I-35 are major transcontinental transportation links, with more than 40,000 vehicles using the Ames intersection every day. This is one seriously busy junction.
But 5 decades after construction, the old cloverleaf design was struggling to cope with demand and had become a major accident hotspot.
You get that many vehicles mixing together at the same time, it's just the odds are more probable that you're going to have a type of collision between vehicles.
When built, the cloverleaf smoothed the transition between highways, but to safely make the 270-degree loop, drivers had to slow down to about 40 kilometers an hour. With more and faster traffic, the clash between high and low-speed vehicles was a major concern.
The number of crashes at this location, just in the northbound direction, were approximately 25 to 30 crashes a year, which is more than double the statewide average.
Engineers desperately needed a safer way to handle traffic. In 2016, work began outside Ames on this new exit ramp and overpass, carrying vehicles from the northbound I-35 to westbound Highway 30.
We're looking south right now at the flyover, the south end of the flyover. Northbound I-35 traffic is going underneath the flyover. So again, you can see the bridge span.
The flyover consists of 8 two-lane bridge spans supported by 6 piers, creating a long, smooth curve from I-35 up and over the main roadways, allowing vehicles to switch freeways without significantly slowing down.
It's a beautiful bridge. We're proud of it. You can see they have some aesthetic features on the piers. A weathered steel beam kind of fits into the natural environment here in Iowa.
This $23 million safety solution was initially scheduled to open to traffic in 2018, but months before its completion, construction had to be put on hold. The problem lay within the 6 concrete piers that were designed to support the roadway.
When the piers were completed, 2 problems were spotted. First, the anchor bolts for the bridge decks were in the wrong position. Secondly, all 6 piers were too high. There's no way the decks would fit.
One of Iowa's largest and most expensive construction projects, designed to make a safer intersection, had ground to a halt. Officials said the issue most likely stemmed from the initial survey. Like many projects, it relied on Global Positioning System, or GPS.
Global positioning systems have been around for years. Invented by the US military, today GPS is everywhere. Our vehicles, our phones, and even on a watch.
Assistant Professor of Engineering Roy Sturgill explains, with the help of his student Jay.
And the first thing that Jay's going to do is set up the equipment for the base station over top of a known point.
At any given moment, the base station can detect its position in 3 dimensions, relative to satellites orbiting the Earth.
We have 2 GPS antennas. One we're going to use as the base station. The second we're going to use as the rover. This antenna will not only communicate with the GPS satellites, but will also be communicating with the base station. Everything's controlled by our data collector here. Once the system's calibrated, from there we can start collecting data.
The fixed base station plots the exact location of the rover, allowing engineers to accurately plan out any new structure. With the exit ramp, getting the shape right, both in gradient and curvature, was vital to safe, smooth operations.
The initial layout tells the rest of your contracting crew where bits and pieces and parts of the project are going to go in. So it's critically important that your survey work is as accurate as it can possibly be, because it sets the stage for the rest of your project.
Today, GPS is an essential tool for all big engineering projects. But like any technology, it's how it's used that matters.
So GPS surveying is something that looks really easy, and the equipment makes it feel very easy, but there's a lot of opportunities for things to go wrong.
It seems something did indeed go wrong when plotting out the new Ames exit ramp, that resulted in the piers being too high.
With the pier heights being incorrect, the impacts that would have is that the vertical curvature, the horizontal curvature, and even the super elevation of that flyover would have been impacted by those varying heights.
This roadway was designed to make travel safer, but there was no way construction could continue.
Mistakes happen on every project. There's no perfect project. It's all in determining where those mistakes are and trying to figure out how to fix them.
Given the junction was an accident hotspot, engineers worked tirelessly to devise a solution to both problems.
Once you're dealing with in-place and cured concrete, you're left with no choice other than to chip off the tops of the pier to the point where you reach a sound point and then can reconstruct it without damaging anything else. So that is a very tedious process and does take time to do that appropriately.
The answer lay in brute force.
You're going to have, hydraulic or pneumatic hammers to come in there and jackhammer off the top of the concrete pier.
The solution might not have been elegant, but it was very simple.
When the piers were down to height, the concrete tops were re-poured, this time with the anchor bolts in the correct positions. The new ramp finally opened in 2019 with great success. Vehicle collisions at the junction have dropped significantly.
A bridge is going to be here for 100 years, we hope, and we're proud of the little extra time it took to build it. The citizens of Iowa and the DOT are very proud of.
And engineering lessons were learned along the way.
So in terms of lessons learned from this project, I think it is a good lesson to understand, the use of GPS technology, the use of importance of surveying.
Even with the most sophisticated technology around, mistakes still happen. Thankfully, the errors were found before it was too late, and traffic is flowing safely between the highways.
With proper foresight and modern engineering techniques, highways of today and tomorrow can be our best investment.
In Egypt, a shipping catastrophe sends shockwaves around the globe.
Her size and her scale fundamentally changed what this event was going to be. This event was going to have worldwide implications.
A devastating bridge collapse in Australia narrowly avoids tragedy.
It was an absolute miracle
that people didn't lose their lives. So this is a huge story.
In Pennsylvania, disaster strikes as a driver and his vehicle are swallowed whole.
Usually you'll see a tire or something that goes into a small hole. This actually encompassed the whole vehicle.
And in Louisiana, failure on a crucial crossing forces an urgent multi-million-dollar fix.
$30 million sounds like a lot of money, but compared to human life, you really just can't put a price tag on that.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers are constantly pushing the limits in both design and scale. But if things go wrong, a catastrophe like the structure itself can be monumental. Like this disaster in Egypt, a crisis on a global scale.
A blockage that was holding up billions of dollars of trade every day.
A supersized ship runs aground and a race against time to find a solution.
The front of the ship is now trapped, buried in the sand.
They needed to get this ship moved, and fast.
And the world economy is brought to its knees.
She's so large, so big, that when she careened out of control, she effectively blocked 12% of the world's trade in one motion.
Egypt, an ancient land full of epic feats of engineering.
When you say Egypt, you might think of the ancient pyramids, the Sphinx, but it's also home to one of the most vital trade routes on Earth, the Suez Canal.
Linking the Red Sea with the Mediterranean, this maritime shortcut dividing the continents of Africa and Asia is a true engineering marvel. Completed in 1869, it took more than 10 years to build. Associate Professor of History, Dr. Salvatore Macogliano, explains.
The Suez Canal was a massive undertaking. You had to dig 120 miles, 190 kilometers worth of sand and dirt, and it actually conjured up images of the pharaoh building the pyramids. They're building a new pyramid, but this pyramid links together two oceans.
In its more than 150-year history, the canal has become one of the world's most vital shipping lanes.
Previous to the Suez Canal, you had to circle around Africa an additional 15,000 miles in some cases. And it was seen as the bridging of two worlds, something that had never been accomplished before. What the Suez Canal provided was a shortcut.
Today, around 12% of world trade navigates the narrow channel.
In 2020, nearly 19,000 ships transited the Suez, carrying more than 1 billion tons of cargo.
As trade grew, so did the ships, on a mammoth scale. Like this, the Ever Given.
The Ever Given is a giant among ships and can carry 20,000 containers. It's known as Suez Max, the largest type of ship allowed through the canal.
Almost as big as the Empire State Building, these ships are pushing engineering to the very limit.
Ever Given is a quarter of a mile long, 200,000 tons. If you're standing on the lower deck and you look up at the container stack, you're seeing 24 8-foot containers stacked one on top of the other.
With such vast ships, navigating this narrow, shallow stretch of water is no cakewalk. Stephen Turnock is a professor of maritime fluid dynamics.
The Suez Canal, it's very narrow. There's not very much water between the bottom of the ship and the bottom of the canal. Sort of the flow underneath the ship is forced through faster than it would normally do, and that kind of sucks the ship down towards the canal bed.
Known as the squat effect, the faster the ship moves through the water, the greater the effect is on the vessel, and the deeper it's forced to sail in the already shallow canal.
Suddenly it matters a lot that you keep within quite narrow bounds, you don't deviate to the left or right by very much, and that makes it particularly challenging for mariners to navigate through and to maintain the course that you want to go through safely.
With only about 9 meters of clearance between the bottom of the ship and the canal bed, any deviation can be catastrophic. During the early morning of Tuesday, March the 23rd, 2021, the 400-meter Ever Given, en route to the Netherlands, was in a convoy of ships traveling north.
It was the 5th vessel in a 25-ship convoy heading up the Suez Canal from the Red Sea into the Mediterranean.
Loaded with 18,300 containers, as the ship approached the entrance to the canal, it encountered heavy winds and a sandstorm blowing from the west. Right from the outset, the ship was struggling to stay on course.
The vessel was never in the center of the canal. It actually maneuvered from bank to bank.
Moving side to side, getting really close on one side, close on the other side, having difficulty controlling its course.
It wasn't just weaving. The Ever Given was also accelerating.
It started to speed up, progressively getting faster and faster, sort of 7, 8, 9, 10 plus knots.
At 7:40 a.m., the 200,000-ton ship crashed head-on into the side of the canal, ploughing around 5 meters into the sandy bank. The Ever Given was stopped in its tracks.
And what the vessel essentially did was ram its bow into Asia. The stern kept swinging northward. It ran aground in Africa. She was traversing the canal at such a high rate of speed that when she careened out of control, she effectively blocked 12% of the world's trade in one motion.
The figures are staggering. It's estimated that the Ever Given was holding up 3.3 million tons of cargo an hour, or $6.7 million a minute.
The ship was completely wedged across one of the busiest trade routes on the planet.
Her size and her scale fundamentally changed what this event was going to be. This event was going to have worldwide implications.
And the world was definitely watching. With the Suez Canal completely blocked and ships and trade at a standstill, the entire planet was searching for answers.
On average, more than 50 ships a day navigate the Suez without incident, and crucially, without making headlines. So the big question was, why did this one get stuck?
Examining the ship's global tracking device revealed that something was wrong from the moment the ship entered the canal. Associate Professor of History Dr. Salvatore Mercogliano explains.
If you follow the track line of the vessel was never in the center of the canal. It seemed to have lost control. It actually maneuvered from bank to bank.
As the investigation began, early reports suggested high winds were to blame. Professor of Fluid Dynamics Stephen Turnock explains that even for a ship weighing over 200,000 tons, this can be a major problem.
With big container ships, they're sticking a long way up into the air. If the wind is strong, then you get quite large forces. A wind was coming from its stern. Naturally, that wants to turn the ship, actually makes it more difficult to control.
Not only were huge forces acting on the Ever Given from above, they were also at play from below.
The vessel is so large that it doesn't have a lot of water underneath it, and it doesn't have a lot of water next to it along the banks. And that creates forces that act on the vessel.
As well as the squat effect pulling the ship deeper, it was now being dragged towards the sides too by another phenomenon known as the bank effect. As the ship moves closer to the bank, water squeezing between the two surfaces speeds up, pulling the stern towards the canal side, effectively turning the ship.
What we saw happen was Ever Given got extremely close to the west bank, and she had to turn right. And unfortunately, she turned so hard right that it put her into the east bank.
The bank effect was too much of a challenge. You get away from that side, but you then get in trouble on the other side.
While there's little doubt this played a part in the wreck, another question remained. With the initial ships in the convoy making it through, why did this one speed up in the canal?
The Ever Given was reported to be doing 13.5 knots, almost 25 kilometers per hour. That's more than 50% over the speed limit for this size of ship.
The pilots may have actually gone faster to try to get better control of the vessel. The faster you go, the more maneuverable your vessel is. Drive a car down a highway, it takes only a small turn of the wheel to change lanes when you're going fast. The problem was when something goes wrong at that speed, there's very little margin for error.
With the rescue operation demanding help from across the globe, Plan A was to try and pull the ship free. Easier said than done, as geotechnical engineer Professor David White demonstrates. Wet sand is hard to escape.
So in civil and maritime engineering, we use physical models of systems a lot. They're quick and easy to make, and we can just get a feel for the problem. Put it in a tank, got some sand representing the sandbank, and when it comes and hits the bank, it pushes into the bank, and the bow is buried. Dragging the ship backwards, which is maybe the first thought you might have, is very difficult because you've got the friction from that enormous weight resting on the front. If you do a quick calculation, maybe you're going to need 60 or 100 tugs to pull the ship back.
The Egyptians scrambled very quickly. They dispatched tugboats to the area and attempted to pull her off. The problem was, Ever Given being solidly aground on the bow and stern posed too much of a challenge, and it wound up being that the Egyptians could not move the vessel at all.
With billions of dollars of cargo and more than 300 ships backed up on both sides, it was time to go to Plan B.
Twisting it around is easier. If you try to pull the stern of the ship to the side, then actually the force you need is less, maybe just a handful of tugs. And this was the strategy that they adopted.
With larger anchor tugs and a specialized suction dredger, salvage teams were finally making progress.
This specialist suction dredger could shift around 2,000 cubic meters of material every hour. That's almost enough sand and mud to fill an Olympic swimming pool.
So once it was stuck on the bank up here, the dredging here needed to remove the sand over at this side, in front of where the bow is going to push the sand out to allow it to then rotate.
Not only was this one of the most expensive delays in history, it was now also a race against time and the tide.
To free the Ever Given, they used all the resources at hand, even the moon. One thing that all mariners are aware of are tides. And in this case, a fortunate spring tide was happening at the end of the month.
Their best hope was on the Sunday, when water levels would be about half a metre higher than normal for just a few hours. That gave engineers a very real deadline to hit.
The combination of dredging and tugging with some help from the moon finally paid off. On Monday, March the 29th at 3:05 p.m, after 6 long days, the Ever Given was finally free. And while it may be some time before we know the full story behind this crisis, it firmly highlighted the world's reliance on these colossal containers.
We've experienced before hurricanes and disasters that temporarily shut down trade, but never before had we seen an accident shut down 12% of the world trade and all of a sudden impact the entire globe.
After dominating the world headlines for 6 days, finally, this cargo megaship, the length of 4 football fields, was dislodged from the banks and on its way again. Gone, but definitely not forgotten.
In big construction, careful planning and preparation are key to every project. Even a slight mistake and the results can be catastrophic. Like this disaster in Australia that brought down a vital crossing in the capital.
The amount of concrete, the amount of steel that was on the ground over such a large area, I was shocked.
A fundamental oversight that went unchecked.
This disaster could have been avoided.
And a catastrophe that barely escaped tragedy, rocking the nation.
There was shock and amazement, and then obviously it was everyone get to work.
Canberra, Australia's capital, is home to the nation's federal government, as well as national museums and monuments. Local journalist Emma MacDonald was born and bred in this central city.
In 1901, the search was on to find a place for the national capital. Now, there was a big fight between the two biggest cities in Australia at the time, and that was Sydney and Melbourne. They both wanted to be the national capital. So Canberra was in many ways considered a bit of a compromise. It was sort of halfway between the two.
Derived from an Aboriginal word meaning meeting place, every last detail of Canberra's sprawling metropolis was analysed by city planners, and it worked.
Canberra is one of Australia's fastest growing cities, with its suburbs driving much of the population boom.
But as the city grew, the roads were struggling to accommodate all the commuters, especially in the northern suburbs like Gungahlin.
One of the problems with Canberra being such a car-centric city is that the road infrastructure really needs to keep pace with the population booms that these areas have. And Gungahlin was a classic example where we had a lot of development, a lot of new housing, a lot of population wanting to move in straight away, and the roads just weren't equipped.
In 2009, to ease congestion, work began on this interchange. The 9-kilometre Gungahlin Drive extension running into the heart of the city.
Commuters frequently faced lengthy delays any time of day. The work to double the road from 2 to 4 lanes couldn't come fast enough.
In total, 9 new bridges would be constructed as part of the project, including this one, which would be built alongside the existing crossing. Michael Inman is a local reporter.
There was already an existing bridge and an existing drive. They decided to duplicate that so they could have a few different lanes going in each direction so people could actually get to work.
One of the proposed bridges crossed over Canberra's busiest and most important freeway, the Barton Highway. Civil engineer Mike Evans explains.
The road over the top is the Gungahlin Drive, which is the main traffic corridor going in the north-south direction on the west side of Canberra. The road beside me is the main highway through to Melbourne.
Closing this busy highway was not an option. So, like a lot of bridges across major roads, this crossing would be built in place, known as cast in situ.
Cast in situ would allow the busy Barton Highway to remain open. Wooden moulds, known as formwork, would be built in the shape of the bridge, on top of the temporary steel bracing or supports. The plan was to cast the entire deck in one pour, and once hardened, lower it into place alongside the existing bridge, creating a 4-lane crossing.
The extension was vital, not only to Canberra's transport network, but for the growth of the city as a whole.
Saturday, August the 14th, 2010, the concrete pour was underway. At around 1:50 p.m, workers were over 3/4 of the way through.
They heard a bit of a cracking sound, and about 2 or 3 seconds later, the bridge just gave out from underneath them.
A huge section of the bridge collapsed suddenly and without warning. Workers scrambled for their lives as hundreds of tons of wet concrete came crashing down onto the road below.
Some guys had time to run clear. Several guys went down with the bridge.
Incredibly, one worker managed to grab hold of a cement truck hose and clung onto it in mid-air for around 15 minutes until he was rescued.
With Canberra's main highway now blocked, details of the disaster quickly spread through every newsroom in the capital. Journalist Emma MacDonald was at work when word came through.
I remember all of us just being quite shaken because the people that were working on that project were people who lived in Canberra, and everyone knows everyone in this city. There was shock and amazement, and then obviously it was everyone get to work. This is a huge story.
As reporters and rescue workers rushed to the scene, the scale of the disaster became clear.
When I first saw it, I thought to myself, what a mess. I'd never seen anything of that size and scale to collapse like that. The amount of concrete, the amount of steel that was on the ground over such a large area, it blew my mind, to be totally honest. I just thought that these things don't happen in Australia.
while 15 workers were injured and 9 hospitalized. Incredibly, despite the devastation, no one was killed.
Those workers were just so lucky. It was an absolute miracle, given the catastrophic nature of that collapse, that people didn't lose their lives.
The disaster sent shockwaves around the country, and people wanted answers.
Well, everyone was interested. Everyone in Canberra was speaking about it. So it was obviously a big story around town and nationally at the time as well. The question then started to be, how did it happen? Why did it happen? And what was the fallout?
In a city famed for its planning and heavy reliance on its road network, how had such a seemingly routine build gone so disastrously wrong?
And we've got to figure out what happened, make sure it doesn't happen again. But at the same time, you know, there's a highway that's been blocked. There's a major road that's been blocked. So they've also got to get that moving so the rest of the town can get moving again.
An engineer's report commissioned by the Australian government quickly identified the source of the problem. The steel beams supporting the wooden mould or formwork were missing a key structural element. Civil engineer Mike Evans was asked by the government to analyse the findings.
The beams on the temporary bridge had no bracing and no stiffness, and that lack of bracing and the instability of the beam reduced the carrying capacity of the beam. This is a photograph of the temporary bridge, and you can see from this that these are the longitudinal steel beams with the timber resting on them. There is no cross bracing of any kind.
The investigation found that the steel girders supporting the formwork weren't braced to prevent lateral movement. But when you're pouring around 800 tonnes of wet concrete, one thing you're going to get is movement.
Engineers also discovered that the steel supports had been placed at a slight angle.
The beams had been placed at 3% to the vertical so that the rain could run off the surface of the road. Now, gravity acts vertically, so in effect the beams were carrying a sideways load at the top of about 3% of the vertical load, which, whilst a small proportion, was a very sizable load.
It was more than enough to make the temporary structure unstable.
A combination of the lateral instability because it wasn't braced, plus the fact it was carrying a sideways load, caused the beam to move over sideways and to bend sideways and then eventually to flip over.
Essentially, they didn't have the weight-bearing capacity underneath the bridge, and the whole thing just crumpled out from underneath them.
Further investigation also found that the welding of the top beam was insufficient.
What was critical in this case, they only did a partial weld rather than going through the full depth of the metal. But because of the sideways bending as well, there was a tension on the edge of the top of the beam, and that caused that to tear open. If you look at this close-up, you can see the rusted area where there was no weld. It's only that little edge there where there was any weld. Not a very good detail.
The report cited multiple structural and planning failures that ultimately caused the disaster.
In fact, engineers often talk about the Swiss cheese effect, where all the holes in the cheese have to line up to cause the accident. And I think this may have been one of those cases where so many things went wrong all at the same time. You had the end effect of the bridge collapsing during construction.
Following the catastrophe, engineers were quickly deployed across the city to check all other bridges under construction.
Fortunately, this flaw in the formwork was only found in this one bridge. The others being built around Canberra at the time were given the all clear.
In the aftermath, new regulations were put in place for formwork and the bridge demolished.
It took a month to clear all the debris away. I think it took another 4 months until they could even start trying to construct it properly again and get the project actually finished.
A new crossing was rebuilt, and the Gungahlin Drive 4-lane extension finally opened on October the 7th, 2011.
And it looks lovely now. You go up and around and off you go. Very, very few traffic jams, if ever.
With lessons learned and a new code of practice in place for formwork, hopefully disasters like this will be a thing of the past.
Australia has been nicknamed the lucky country. In this case, it's a miracle no one was killed.
From the tallest towers to our vast sprawling cities, engineers build to last. But there's no escaping the ravages of time. Like this disaster in Pennsylvania that struck without warning.
All of a sudden, the road opened up and swallowed his SUV.
A massive sinkhole in the middle of a suburban street.
Usually you'll see a tire or something that goes into a small hole. This actually encompassed the whole vehicle.
Leaving residents wondering, how did this neighborhood nightmare happen? Easton, a small city in Pennsylvania, owes its existence to the ground on which it sits. Brittany Sweeney is a local journalist.
Easton is a little town. It's really rich in natural resources like limestone, slate, and iron ore. The other great thing about Easton is it's located in a region that has a lot of highways, so it's easy to get products in and out of this area.
The city might be looking to the future, but it can't escape the past beneath its feet, which is far from solid. Geotechnical engineer Ward McMasters explains.
Easton is part of one of the limestone belts that basically run across Pennsylvania and then dip down into Maryland, known for sinkholes characterized by the limestone bedrock below. Limestone, just because of its geologic characteristics, is going to have fractures and cross fractures, and also what you're going to have is voids within the bedrock system.
Because the more people you have, the more water gets used, which dissolves more limestone.
When we exacerbate it by having larger developments, concentration of people piping below the ground surface, we cause increased levels of sinkholes.
Water dissolves the limestone, forming fractures and voids which grow into caves. As the roof gets thinner and collapses, the soil above is washed away, creating a sinkhole.
The ground can be riddled with holes, but from the street level, you'd have no idea. If you then build a city above them in time, it can be a recipe for trouble.
Monday, December the 30th, 2019, on a suburban street in Easton.
This is a quiet neighborhood where not a lot happens.
As residents were going about their daily business, all that was about to change.
From the footage, this looks like a regular rainy day on a regular street. Then, the SUV kind of bumps and drops into a hole. It's surreal.
Journalist Brittany Sweeney knew this big hole was big news.
Not a lot of people traveling through. It's not like it's a busy road, so the fact that a sinkhole would open up and just driving down the road and then all of a sudden your car gets swallowed by a sinkhole, that is an insane thought for a neighborhood like this.
It was more than that. A young girl was watching from her bedroom window.
I couldn't believe it that it was my dad's car. So I rushed downstairs. My mom was in a panic.
Her father was trapped. Easton Fire Chief Henry Hennings was on duty at the time.
When I pulled up to the intersection, I saw the front end of the SUV sticking up in the air, and the original sinkhole opened up right about this area here. And it was pretty large. It was probably 40 foot in diameter and at least as deep.
The hole was filling with water, with the driver fearing for his life.
And I see a lot of water is going through. That's time I'm scared, So I'm going to die right now.
Luckily, both the driver and passenger scrambled to safety.
It was a relief that it was a recovery and not a rescue. We didn't have anyone hurt, which is always fortunate.
But the danger wasn't over just yet.
Once the sinkhole opens, there's no way of knowing where it's going to go or any way to stop it.
Pretty much every built structure has foundations. And if the foundations have been washed away under part of the road, there's a risk the same is happening elsewhere, even under the buildings nearby.
When you have a sinkhole in a residential neighborhood, any of the housing in the area is at risk.
Houses on both sides of the street were evacuated, and more was to come.
That first sinkhole was not the last. A few days later, as they're working to fix the street, an excavator fell right into the street, into another sinkhole. It was scary for the neighbors. They said that it started to get to a point where they never knew when another sinkhole was going to open up under this street.
While this part of Pennsylvania may be famed for sinkholes, there were no known caves directly under the neighborhood. Engineers ruled out Mother Nature. Something else must be at fault.
Easton had a water main break, but the water main break wasn't in the actual location where this sinkhole occurred.
With no direct flooding causing the sinkhole, how had it opened up so dramatically?
When a water main breaks, the escaping water can blast a hole under the road surface. But sometimes, like here, the water tracks underground, causing erosion further down the road.
That fracture becomes very active, and 50 feet down the road, 100 feet down the road, all of a sudden we get a sinkhole that appears to have cropped out of nowhere. But a lot of times they are interconnected just at depth.
The broken water main explained the sinkhole. But the next question was why it had failed in the first place.
In the US, there's a water main break roughly every 2 minutes. The basic reason is simple: age.
Like many water pipes in America, this could have been a century old, and back then most were made from cast iron.
Cast iron piping can be susceptible to increased brittleness when we have cold water temperatures moving through it. It doesn't have to be freezing. Anything below 40 degrees will increase the brittleness of that piping.
The problem here isn't the water pressure bursting the pipes, but the cold temperatures of winter making the cast iron brittle. Multiply that by nearly 100 cold winters, and it's no surprise that they fail.
Once the water washes away the road's foundations, it's only a question of time before a sinkhole appears.
This is really a scary thought for the people who live in this neighborhood, and any neighborhood for that matter. It's not like it's a street that's heavily traveled, it's not a highway. This is just a neighborhood road that is in a suburban area, and for a sinkhole to open up when someone's just driving down the street is just scary to think about.
Across the US, there are more than 3 million kilometers of water pipes, much of them still cast iron. Yet since the 1960s, one new material of choice has been ductile iron. Although installing it is an expensive and disruptive process.
What we want to do is, when the budgets allow, let's go in and get rid of the cast iron piping and replace that with newer, more updated materials that would be stronger and more resistant to the weather.
The graphite in cast iron is flaky, and those sharp edges make it prone to cracking. In ductile iron, however, the graphite is rounded, and that acts as a crack preventer. So pipes made from ductile iron are stronger, more malleable, and more durable as well.
To make sure that we can maintain the stability of the roadways and the buildings to protect the health and safety of the people of those areas.
In a city built on soluble limestone, this sinkhole was a reminder of the risks of aging water systems.
The US has a massive problem with aging infrastructure. There's no silver bullet, but shocking events like this are a good reminder to everyone that one day, nearly all of it needs repairing or replacing.
With all bridges, gravity can be an engineer's biggest enemy. But when other forces come into play, the threat can be much greater. Like this near miss in Louisiana on a crucial river crossing.
This is an evacuation route. It's a route that needs to be kept open.
This fail had been brewing for decades and prompted a major rebuild.
$30 million sounds like a lot of money, but compared to human life, you really just can't put a price tag on that.
An oversight with the potential to bring this mighty bridge crashing down. New Orleans, Louisiana. More than 1 million people call the metropolitan area home. In this low-lying city, life is ruled by the water that surrounds it. Autumn Cafiero Giusti is an engineering journalist.
We're in southeast Louisiana. This is an area surrounded by large bodies of water, swampland, the Gulf of Mexico. We've got the Mississippi River.
With half the city below sea level, flooding is a very real risk, whether from the Mississippi or storm surges from the Gulf.
We're right in the path of hurricanes being right by the mouth of the Mississippi River. If there's a storm that's large enough that could overtop those levees, that's when we have the bowl effect where the city starts to fill up with water.
New Orleans floods most years, but when Hurricane Katrina hit, parts of the city were inundated for more than a month. More than 1,500 people died in one of the worst disasters in US history. But the toll could have been higher. More than 80% of residents had fled New Orleans in the city's first ever mandatory evacuation.
Evacuating can be a very dramatic response, but when you're in the direct path of a hurricane, moving can be the safest option.
And if the city starts to fill, for most, the only way out is by road.
When you have something like a Katrina where you've got an entire metro area trying to leave, all of your roads are going to be congested. So having reliable roadways that you can use to get out of the city, every possible artery is necessary.
With so much water to cross, bridges play a crucial role in the evacuation plan.
These bridges across the Mississippi, there are only a handful of them, so they're really vital because that is our way out of danger. That is how we escape the city.
This key Mississippi crossing, about 40 kilometers west of New Orleans, is the Hale Boggs Memorial Bridge.
Coming out of the city, you go from suburbs to just swamp all of a sudden. You turn onto 310, and then all of a sudden there's this big, beautiful bridge kind of out of nowhere. So impressive to look at.
Completed in 1983, with a main span of around 370 meters, this was the third major bridge of its type in the US. Norma Jean Mattei is a professor of engineering.
It was a very innovative bridge. Back in the 70s when it was designed, it was the first cable stay bridge to be used to cross the Mississippi River. There were cable stay bridges in place in Europe and in other parts of the United States, but a cable stay bridge crossing the Mississippi had never been done.
One main challenge was to build a bridge that wouldn't obstruct the busy shipping channel below.
You can see that the Mississippi River is a pretty wide river down here in Louisiana. So you want to not have the substructure too close to the navigation channel because you're going to have major ocean-going vessels pass it, and should one lose control, you do not want that vessel to collide with your bridge pier.
With Louisiana's famously swampy ground, a cable stay bridge was the best solution to keep the shipping lane as wide as possible. The main towers stand on bedrock, taking the strain of the 72 steel cables that support the road deck below.
Those cables are protected by a polyethylene or plastic sheathing, and you don't want water to get in between the sheathing and the steel cable because that would cause rust.
Back in the 80s during construction, the plastic covering the original cables started to crack before they were even erected. Engineers were able to patch up 21 of them, but it was too late to replace them completely.
The cables were already in tension, so all they could do was try to repair them for now. The plastic was heated to seal the cracks, but the real damage had already been done.
In 1983, with the cracks repaired, the Hale Boggs Bridge opened to traffic. 2 decades later, when Hurricane Katrina struck, the bridge stood firm. and played its part as a vital evacuation route.
When I evacuated for Katrina, I think we took the Hale Boggs Bridge out of town because it was less jammed with traffic. So it really is important to getting people out.
Just 2 years after Katrina, another catastrophe further up the Mississippi raised red flags.
In 2007, the Minneapolis I-35 bridge, also over the Mississippi River, collapsed. This was kind of a turning point for infrastructure in the United States.
Hale Boggs was newer and a completely different design, but no chances could be taken.
This is when people really started paying attention to the state of our infrastructure and the fact that things needed to be repaired.
In 2008, the original cables went under the microscope with concerning results. Although the bridge could survive the failure of individual cables, more than half were found to be corroding, reducing their ability to carry the weight of the road below.
The amount of tensile force that a cable can carry is a function of its ultimate tensile strength and its cross-sectional area. If you have corrosion, you have just removed some of that cross-sectional area, so you no longer have the same amount of area to hold that tensile force.
Although none of the cables failed, the corrosion was far worse than expected. If it hadn't been spotted, the results could have been catastrophic. Action needed to be taken, and fast.
As engineers investigated further, they discovered the problem was being made much worse by Louisiana's wet and windy weather.
The cables were very well monitored, and what was noticed that in rainstorms, the cables would vibrate. And that was not something that was foreseen.
As wind from the storms caused the cables to vibrate, it was creating stress and fatigue on the steel inside, as well as cracking the anti-corrosion sheathing meant to protect the steel. With more than 50,000 vehicles crossing the bridge daily on one of the city's main evacuation routes, it was crucial this vital bridge was fixed for good.
When they were repairing the bridge, they really had to take into account evacuation traffic and loads and figure out if the bridge could support that much weight, because when you have an evacuation, you're going to have a lot of cars on the bridge, and that puts a lot of stress and strain on the bridge.
In 2009, the decision was made to replace all 72 cables.
There was a lot of thought and design that went into how do we economically and safely replace the cables and not impact the ability to move traffic along the bridge. Now that's a challenge because this is an evacuation route. It's a route that needs to be kept open.
To keep the bridge operational, the cables were replaced individually, one side at a time. And to prevent wind-induced damage, the new protective sheathing has a ribbed exterior design.
This was an incredible fix. Every cable was successfully replaced one by one, allowing the bridge to remain open to traffic throughout.
Now the bridge was better than new, but the fix hadn't come cheap.
$30 million sounds like a lot of money, but compared to human life that could have been lost if it hadn't been repaired, I mean, you really just can't put a price tag on that.
Work was completed in 2012, and the new cables are set to last for 3/4 of a century.
Knowing that it's been repaired, that it's got, you know, a new lease on life and 75 years of lifespan is really reassuring, and I think it's going to be reassuring to the people who use this bridge all the time.
In Pennsylvania, a catastrophic landslide rocks a community.
The entire slope started to move, the roadway cracked at the top, all of that material is now pushing down slope.
Disaster strikes at the heart of a small town in Iowa.
It was a very scary moment. You just couldn't believe it. I mean, how can this happen?
In Indiana, a bridge build goes tragically wrong.
They was laying concrete
about 40 feet into the air when a disaster struck.
And in the UK, a state-of-the-art highway project threatens chaos.
There is a technological room for error, and there's also a human room for error.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When engineers take on gravity, strong foundations and perfect balance are everything. Just one slip-up can lead to catastrophe. Like this disaster in rural Iowa, a big day for a small town that went horribly wrong.
Everything looked to be fine. Then the crane just went down. And the whole crane fell on the structures and everything fell to the ground with it.
This engineering error came from nowhere and left residents reeling.
The steel girders, the crane itself were all laying across here.
The rolling green state of Iowa is home to thousands of farming towns like New Providence. Dennis Reese has lived here for more than 30 years.
Well, right now we are walking down Main Street of New Providence, Iowa. New Providence is a typical small Iowa town, originally settled by the Quakers back in the mid-1800s.
Like many rural communities, New Providence is proud of its water tower, which has carried the town's name for 2 decades.
There are water towers all over the world. They're not just for storing water. You can do that easily at ground level. The reason for putting it up high is all about pressure. Gravity pushing down on the water gives the whole town a nice, consistent flow.
Water towers are important because they provide better water pressure, but they also are a backup supply system in the event of an emergency.
For decades, Dennis and his neighbors relied on water that was pumped in from across the state. Then, in 2000, they received major news.
New Providence had always had a water system for a long time, but it did not have a water tower. When we first heard that a water tower was actually going to be installed, that was a big deal for the town because it felt like we were going to be a real town now.
On July the 19th, the wait was over as the construction team rolled into town.
Well, it looks like somebody's coming down the road right at me.
One of Dennis's neighbors filmed the project from the beginning.
That's where the water will all be.
The plan was for the 4-legged tower to stand almost 40 meters tall, topped with a near 230,000-liter tank. Storing water so high meant gravity would ensure each resident had plenty of pressure. Like every building project, this one would be unique. Based on the location and type of lifts required, contractors brought in a mobile tower crane nearly 200 feet tall. With a crane this size, preparation was vital. Professor Risto Rautiainen is an Iowa-based engineering safety expert.
Every lift is a little bit different, so it takes a lot of careful planning, and it is definitely very dangerous. You need several people, some up on the structure, and often this is done at a height of over 100 feet, 30 meters, and so it is definitely very dangerous, especially when the conditions and the situation changes every time with every lift.
As with every lift, stability was key to safety.
Weeks earlier, they dug and filled a huge pit with compacted earth to create a solid base to build on.
So the very basic thing with cranes is you have to have it on solid ground and you have to set it up so that it is not going to fall. Usually when you set up a crane, you have outriggers to provide a larger base for the crane and what the crane is lifting.
Outriggers are telescopic steel arms on each corner of the crane with feet on the end. To spread the load out more, these were placed on wooden beams called cribbing timbers.
The first job was to raise the tower legs into position.
The empty tank weighed 14 tons, but when full of water, it would top 200. So the tower and its foundation had to be strong.
Once the tower frame was complete, the team lowered the water pipe into place. All that remained was to lift the tank.
Construction took several days to build the base of the tower, but then when word got out that the actual tower was going to be lifted into place, that was a big deal, and a lot of people gathered to watch the tank actually being set on the legs.
For maximum stability, contractors maneuvered the giant crane right up against the tower legs. Once in place, the outriggers were deployed to spread the load as wide as possible. The crane was so close to the tower that the rear right outrigger and its cribbing timbers sat on the newly compacted foundation. Now that everything was in place, the team started to lift the tank.
Well, they say we're going to lift off.
With the tank 40 meters up in the air, the crane rotated to line it up in position.
Just as the tank was being set on the legs, that's when things started to shift and move. The water tower and tank fell that direction. There's a tree that's still standing and has a scar on it. That's where the tank came to a rest, and then all of the steel girders and the crane itself were all laying all across here.
Two of the three workers were injured, yet tragically, their colleague was killed.
It was a very scary moment. It was a tragedy for the town. You just couldn't believe it. I mean, how can this happen? The obvious tragedy is that there was a loss of life.
The town was in shock, and as word spread of the disaster, the state launched an investigation. Engineer Risto Rautiainen was part of Iowa's fatality assessment team.
The main purpose with our program is to find out what happens in these kinds of cases and how we can prevent it again. My role was looking at it from an engineering perspective with all of the evidence we could put together.
With some investigation, it could take years to unpick what caused the accident. Was it equipment failure? Was it an operator error? Was it the weather? But here, one potential suspect was right in front of them.
The cribbing timbers from the outrigger beneath the tower had sunk and separated.
This site had been prepared fairly well some months earlier, but the soil layers on top were not really very stable. When it was time to bring the crane to this site, the top layer of the soil was quite wet.
Before every lift, engineers calculate the pressure a crane will exert on the ground and the ground's ability to withstand that pressure.
But here, the calculations were based on a flawed understanding of the strength of the ground.
The basic issue was that the pressure handling capacity of the soil was not adequate for the very high pressure that was put on when the crane was lifting the water tank and swinging it to a position. So the pressure was probably 2 times more than what the soil can handle.
Based on this calculation, the cribbing beams supporting the outrigger needed almost double the footprint to withstand the pressure. And as Risto demonstrates, the situation was made much worse on the weak soil because the timbers weren't secured together.
Now we're going to test if this outrigger set up in a miniature size will actually hold the weight of a skid steer loader. Okay, let's go.
The post represents the outrigger foot, the skid steer, the weight from the crane. And here, just like the accident, the cribbing clearly fails.
So we could see that when we put some pressure on, this timber started to dig into the ground and the others started separating, and finally it all fell and went through the timbers, and we can see how the soil behaves when it's wet. It really has no support if the pressure is put on a very narrow, small area.
As the crane turned to position the water tank, its weight shifted to the outrigger on softer ground. Then gravity took over.
All of the weight was put on just one outrigger, and that outrigger was not supported properly, and it sank into the ground, and the whole crane fell on the structures, and everything fell to the ground with it.
This fell quickly snowballed out of control. Once the crane started to tilt, the outrigger failed, and there was nothing to stop it from toppling.
Now, Risto shows how bolting the beams together and giving them a larger footprint could have made all the difference. The same ground conditions, the same weight from above, but a very different result.
So we have it on pretty wet ground here, and it is sinking just a little bit, but it is holding the weight because it is spread on the fairly wide surface here. Yeah, this is basically working now the way we would expect a well-designed cribbing to work.
Back in New Providence, with the tower and tank destroyed, the only option was to start over.
After a disaster like this, lessons would have been learned. And when the new tower was built, everything would have been checked and double-checked to make sure nothing was missed.
Today, the new tower still stands as a reminder of the tragic events of 2000.
The fellows that were working on the tower actually were here quite a while in the area, and people got to know them. They were just doing their job.
This really was a tragic case that I think everybody in the area remembers for as long as they live, and we would really want to make sure that this kind of a thing does not happen again.
In big construction, engineering and the environment have to work together in perfect harmony. Get that balance wrong and the results can be catastrophic. Like this disaster in Pennsylvania, a vital hillside highway destroyed in just minutes.
The entire slope started to move, the roadway cracked at the top, and all of that material is now pushing down slope.
A race against time to avert disaster.
We need to do something immediate to get the local community out of harm's way.
And the ongoing battle to hold back the might of Mother Nature.
There was that much force. It took down the entire hillside, most of the road, all the apartment complexes below, totally destroyed.
Pittsburgh, Pennsylvania, home to US Steel, with a rich history as an American industrial powerhouse. Thanks in part to the landscape surrounding it.
Pittsburgh is famous as the Steel City. The slopes around it provided natural resources, including wood and coal, for the foundries that made this the nation's steel capital.
Nestled in the Allegheny Mountains and at the junction of 3 major rivers, the city's growth was complicated. District Executive of the Pennsylvania Department of Transportation, Cheryl Moon Siriani, explains.
Pittsburgh was not an engineered city. It was not a planned city. It was a city that just developed from the industry. The industry grew along the river. Over time, if you wanted to work or live in Pittsburgh, you had to move outward.
As industry and infrastructure boomed along the valley floor, residents took to the hills. Local geologist Matthew Morris explains.
As the city expanded, Residential development started to take place up higher on the slopes, and what that left was building roads to get people from the bottoms of the hills to the tops of the hills.
One of the most important is this, Route 30, a vital link between the city and the suburbs.
It's about 30,000 vehicles a day that utilize this route. So this is a major connector or collector that collects folks from the suburbs of Pittsburgh into the cities.
First opened in 1928, this stretch of road high above the city proved to be a challenge for engineers.
If you want to build a road on a hillside, you have various options. You can tunnel, you can blast into the rock, build a ledge for the road, or a combination. But if you do build out, one thing is crucial, a solid retaining wall.
Without a retaining wall, the slope could simply collapse or slip onto the land below. Geotechnical engineer Brian Heinzel explains.
The original wall was concrete cantilever structure. It has a shallow foundation footing, and then the soil on top of that footing helps resist lateral forces just by the weight of the soil over top of the footing, so it does not rotate.
Incredibly, this seemingly insignificant wall was the strength and last line of defense holding back this stretch of Route 30 in an area that is well known for landslides.
In our district, we have about 100 active landslides at any one time. There's some warning signs. You may see trees leaning, rock falls, excessive flooding, but honestly, unless you have a crystal ball, it's very hard to tell which road is going to go first.
With all of these steep slopes around here, you do have a lot of landslides occurring where you run into weak rocks, and over time the development encroaches more into those slopes, and as that happens, things start to destabilize a little bit more. I don't know that it's a great place to build a city, but it was the only place at that time.
In early April 2018, reports surfaced that Route 30 was starting to slip. Even for someone with 25 years experience, what Chief Engineer Brian Heinzel discovered was shocking.
We noticed that the guide rail was starting to move laterally. There was a retaining wall that had separated in one area. We also observed movements actually above and below the wall that were indicative of a landslide.
Cheryl Moon Siriani received an emergency call that something was very wrong.
It was Friday, April 6th. I was in the office, was notified by the assistant district executive that they felt there was an imminent failure. Time was definitely of the essence. It was most important for all of us that the traveling public who traveled along Route 30 and the folks that lived below were evacuated, and the road was closed immediately.
This situation was accelerating rapidly, so it was, best to try to get everybody out of harm's way. And in this case, it was lucky that we did.
At around 6 a.m. on the morning of Saturday, April the 7th, a 90-meter section of Route 30 dramatically collapsed. 2 apartment buildings and 1 residential home were completely destroyed.
And honestly, the slide occurred within hours after moving the people out.
More than 25,000 cubic meters of debris came crashing down in minutes, and the scale of the disaster became clear.
The whole roadway had collapsed. It fell about 20 feet. The slide mass had pushed the retaining wall and debris into the building, basically demolishing the building where we're standing right now.
This whole entire hillside was laying on top of the 2 apartment buildings down below. That is the first thing I saw when I got here.
While the quick thinking of engineers wasn't able to avert the disaster, it almost certainly prevented tragedy.
The damage was catastrophic. You could tell right away that, if anybody was still in those buildings, they would have been hurt seriously.
Some of them watched their entire world collapse in a couple of minutes, so that was tough.
The team had been monitoring the road for months and knew the ground was shifting. but they hadn't expected such a catastrophic fail.
We have quite a few roads around the area that are settling. It's sometimes due to pipe failure, sometimes due to bad soil underneath. So we kept adding asphalt to the road, thinking maybe it was just a settlement issue, not realizing there was a bigger problem underneath.
Engineers suspected the bigger problem might be due to local geology, specifically stony shale and clay rock. Geologist Matthew Morris explains.
Those areas where the shales and the claystones come out onto the slopes, they weather faster than the sandstones. And then that becomes problematic because those weaker rocks and weaker soils, you're now interacting with them as you cross over them with your roadways, railways, any sort of a transportation corridor, really.
But it turned out geology alone wasn't to blame. The seeds of this disaster may have been sown decades earlier.
A lot of these roads were not engineered roads. They were roads that grew up from horse trails and farm field roads. The roads can't handle the additional traffic, the heavier weight trucks, and they fail.
Not only was the increased traffic load a problem, it appears the already unstable conditions were made worse by unusually bad weather.
Typically, we have around 38 inches of rain a year. 2018, we had about almost 58 inches of rain, and we did see landslides occurring much more frequently than what we had seen in the several previous years.
The weather in the months before the disaster added to that risk. There was a wet and cold winter and a big April snowstorm. All of this made the ground much more likely to slip.
So the weather triggered more landslides. But why did this one road fail so catastrophically?
Some of the catalysts were the weak claystone, the excessive amount of rainfall contributing to additional load and weight on the existing retaining wall.
After decades of increasing load from above, the old wall simply couldn't withstand the pressure any longer.
We believe that the final straw was the wall that was below, that was right behind the apartment complexes, did finally fail. That was kind of the last thing that was holding up this hillside, and then the whole entire hillside fell right after that started to move.
Gravity had been working away at the hillside for nearly a century, putting more and more weight on the retaining wall. The wet and cold weather just gave it that final devastating shove.
With Route 30 out of action and traffic diverted, authorities immediately went to work rebuilding this vital artery.
We were here basically 24/7 to help guide some of the emergency response.
Once the debris was cleared, work began on this, a new 120-meter long, 6-meter high retaining wall. Brian Heinzel was the project manager on this nearly $7 million build.
The wall was constructed by drilling 25 feet into durable sandstone bedrock and then filled back to the surface with high-strength concrete to support the beams. These panels here are reinforced concrete, and the anchors consist of steel cables there to provide additional support for the retaining wall against bending.
For added strength, the entire wall was backfilled with a rock embankment to ensure nothing was sliding anywhere again.
This wall is new and improved over the old concrete cantilever wall, and it should last more than the next 100 years.
While this area will always be prone to landslides, with a new, robust and rock-steady retaining wall, the only thing that's moving on this road is the traffic.
This disaster was a clear reminder of the constant battle between big engineering and Mother Nature.
We closed the road on April 6th, and we opened it back to traffic on June 27th, which is literally a miracle. That is his testament to the great people of Western Pennsylvania, having everybody working together. That's how fast this road opened back up.
Engineers have been working with concrete since Roman times, but even with the best known materials, just one mistake can have devastating consequences. Like this disaster in Indiana, a catastrophic collapse on a new highway ramp.
It was one of the biggest industrial accidents in history.
A seemingly simple oversight with disastrous results.
It's a very unfortunate sequence and an incident, losing life. What a tragedy for us.
The obvious question, what had gone so fatally wrong? East Chicago, Indiana, sits at the southern tip of Lake Michigan. Once swampland, the city grew into an engineering powerhouse, nicknamed the Workshop of America. Michael Puente is a local reporter.
East Chicago is a very industrial city. You are not going to find too many cities in the country that is this industrial. But it's also comprised of a lot of great people, a lot of down-to-earth, blue-collar families.
East Chicago is known for one thing, heavy industry, particularly steel. More than 100 years ago, the Indiana Harbor and Ship Channel was built to help move it all around.
A lot of the products that are made here are shipped to all parts of the country and even world. It's a very important cog to America's industrial might.
In 2020, this elevated freeway, known as Klein Avenue, was completed to streamline the flow of industrial traffic through East Chicago. But this isn't the first Klein Avenue viaduct here. Although its predecessor was built 4 decades ago, it worked the same way.
The Klein Avenue Expressway was a long section of elevated road, basically a long line of bridges up to 100 feet high, including a main span over the ship channel.
I was in junior high school at the time. The construction was underway to build the original expansion bridge. It was deemed one of the largest construction projects in the history of Indiana.
Back then, engineers chose a tried-and-true technique to build the more than 5-kilometer-long viaduct, with concrete for the decks poured in their final position, called cast-in-place. Gongkang Fu is a professor of civil engineering.
Casting place meaning we cast that bridge right here, not in a shop, and then move the parts to here to assemble.
With cast-in-place bridges, molds are built between the piers in the shape of the bridge decks, with extra support coming from temporary structures called falsework. After the concrete has been poured and fully cured, the falsework is taken away, leaving the bridge section behind.
When the concrete was cast first, it's wet. There's no strength. We have to wait for 28 days for the concrete strength to build.
In 1982, this cast-in-place construction was in full swing, both on the main roadway and access ramps that would carry traffic up from the industries below. April 15th, about 75 workers were on site, some more than 20 meters up in the air, preparing to pour the concrete for a new span.
One of the most dangerous moments for cast-in-place construction is when the concrete is being poured. Suddenly, the structure has to carry all that extra weight.
At 10:40 a.m., the concrete pour was underway.
As it was going up and they was laying concrete about 40 feet into the air when a disaster struck.
Suddenly, the falsework crashed to the ground.
These sections, when it collapsed 400 feet, it crushed several people.
Just minutes later, the adjacent spans fell too.
Unfortunately, there was no warning. That was very devastating. Co-workers watching their colleagues standing there without any help, but they couldn't help either.
There has been big tragedies, big industrial accidents in this area with the steel mills, but nothing to that extent.
17 workers were injured in the collapse. Despite rescue workers' best efforts, sadly 13 lost their lives.
That tragic day will always be remembered in the city of East Chicago, because a lot of them saw friends and family or co-workers die as a result of that large collapse.
The city of East Chicago needed answers. What exactly had triggered the tragedy? The first clue was the timing of the collapse.
Concrete was being poured for the deck when the structure collapsed. The additional weight seems to have triggered the disaster, but the structure was designed to be built this way. So the big question was, why did it fail?
Investigators shifted their focus to the temporary steel support towers, the falsework.
Key bolts were missing from the steel frame, as well as wedges that would help align the falsework under the sloping ramp above. There were also issues with the concrete base the tower was standing on.
After the incident, they concluded that the entire sequence of failures started from the supporting pad of one of the shoring towers.
Each leg of the steel tower rested on a 1.5 meter square solid concrete pad, 30 centimeters deep. Dennis McCann is a forensic engineer.
A concrete pad foundation is intended to transfer the loads that are collected in the structure above down into the ground below.
Where the ramp had collapsed, investigators found a pad that was cracked.
If that pad or that footing is too thin or not dimensioned correctly, then it can deflect and deform, which can lead to cracking or performance problems or catastrophic failures.
The problem comes down to concrete's brittle nature.
Concrete failure can be very sudden. In our profession, we call that brittle failure, meaning there's no sign of failure. Just like this, it happened. It's like an explosion.
So here we have a compression testing apparatus, and we're going to conduct a compression test on a concrete cylinder that came from a construction site. It's going to take and apply a force pushing down on that cylinder, and we do that to determine the compressive strength. It's going to eventually begin to crack and will rupture when it reaches its full compressive strength.
The risk of brittle failure is much greater if, instead of being squashed, the concrete is being stretched.
Concrete is strong in compression when it's being squeezed on itself. But unless it's reinforced, concrete can't cope with tension, being stretched or flexed.
With Klein Avenue, it seems the supporting pads were too thin, and when concrete was poured above, they were trying to bend under the extra weight, and one failed.
When the pad fails, the leg being supported by the pad had no support. So it dropped, and of course, the shoring tower tilted. And the support between the shoring tower and the bridge slipped. Now this shoring tower cannot function as it was designed.
That small movement was enough to bring down the falsework, triggering a domino effect along the ramp.
With the investigation complete, construction resumed, and the original Klein Avenue eventually opened to traffic in 1986.
This really emphasizes why testing is critical to making sure that we validate our structural designs and that we make sure we have the correct materials in the field that get built.
Civil engineers learn from these accidents, and structural engineers, in this particular case, have learned a lot.
But this wasn't the end of the story. The first Klein Avenue carried traffic over the ship channel for more than 2 decades. Then, in 2007, the tragic I-35 collapse in Minneapolis triggered nationwide safety inspections, and Klein Avenue didn't fare well.
Inspections revealed it was corroding and becoming dangerously weak. So, in 2009, it was closed to traffic and scheduled for demolition.
But with this major link gone, the area suffered years of congestion. Finally, in 2017, construction began on its replacement, which opened just before Christmas 2020.
This is a new state-of-the-art bridge that will connect Indiana with the city of Chicago. It's going to be primarily used by semi-trucks and companies hauling steel, hauling other products, but it's actually a very much faster and efficient way to get from this area up to Chicago.
With big engineering, safety must always take a front seat. Even the smallest oversight can lead to catastrophe. Like this story in the UK, where a massive highways project sparked a public backlash.
There is a technological room for error, and there's also a human room for error.
A smart solution that may not be so smart after all.
I am absolutely amazed that the biggest safety feature has been removed.
And a state-of-the-art project that risks chaos and catastrophe on the nation's roads. The United Kingdom, a small country that relies heavily on its extensive road network, with more than 38 million vehicles on the move. Former traffic cop Mike Rawson has spent a lifetime keeping drivers out of harm's way.
I'm a retired Metropolitan Police Traffic Patrol Sergeant. The safety of people is an absolute priority in my book.
And statistically, the safest of all Britain's roads are these, high-speed freeways known as motorways. Initially only a 13-kilometre stretch in 1958, Britain now boasts more than 3,000 kilometres in its network, all built with safety in mind.
Britain's motorways traditionally have 4 lanes in each direction, 3 for driving, and the 4th at one side for emergencies called the hard shoulder. They've been that way for decades.
First introduced in the 1980s, these 3.3-metre wide lanes are a safe refuge for broken down vehicles, as well as allowing access for emergency services.
The hard shoulder provides you the opportunity throughout the length of the motorway. If you are unfortunate enough to break down, you can get across to the hard shoulder, and that's the safest place to be.
Hard shoulders have been compared to lifeboats on a ship. You hope you never need them, but if something does go wrong, they're ready.
But with vehicles driving more than 100 billion kilometres on motorways every year, Britain's fastest roads were becoming clogged.
2 main ways to cut congestion are to reduce the number of vehicles with ideas like carpool lanes, tolls, or better public transportation. Alternatively, you could make your roads wider, but that's hugely expensive and disruptive, and in built-up areas, nearly impossible.
In 2006, engineers came up with an alternative. In the biggest change to Britain's roads in decades, the hard shoulder would be turned into a 4th lane of traffic, with computers helping control these so-called smart motorways. The challenge, how to keep drivers safe in case of an emergency.
You can never completely remove the risk of an accident, but if you get rid of an emergency lane, you have to replace it with something that does the job just as well.
Emergency refuge areas were installed at regular intervals along the road. But as head of policy at one of Britain's largest roadside assistance companies, Nicholas Lays explains, it wasn't a perfect solution.
Those refuge areas are spaced at every 1.6 miles. So there may be scenarios where if a vehicle breaks down, it might not be able to reach one of those refuge areas. If you get into a breakdown and you can't reach a refuge area, you might stop on a live lane, which is quite a terrifying experience.
If a vehicle does become stranded, then technology takes over, using the Motorway Incident Detection and Automatic Signalling System, or MIDAS for short. Sensors are embedded in the centre of each lane about every half a kilometre. If they detect slowing traffic, the system triggers a change in speed limit on the overhead signs.
By altering speed limits where things are getting congested, the aim is to keep everyone moving as smoothly as possible. It's like air traffic control for the roads.
But although MIDAS can spot slowing traffic, it can't detect stopped vehicles.
A MIDAS system detects slowing traffic, And that can automatically change the speed limit on the variable message signs. But in terms of actually closing the lane physically, that's got to be done by people in the Highways England Control Centre.
For this, operators constantly monitor CCTV cameras, with traffic patrol officers also playing a key role. Friday morning, June the 7th, 2019. Two vehicles were involved in a minor collision on the M1, one of Britain's busiest motorways. They needed to stop, but were too far from an emergency refuge area. Claire Mercer's husband, Jason, was one of the drivers.
They didn't know where to pull over. There was no hard shoulder. The only sign they could see said no hard shoulder for 4 miles. So they pulled over where they could.
The two drivers pulled up against the safety barrier and stepped out of their vehicles. While oncoming traffic moved over to avoid them, critically, the lane remained open.
They couldn't get right out of the left lane because of the crash barrier, and they couldn't stand over the barrier because there was a 30-foot drop onto the road below. So they stood by their vehicles, exchanging details.
6 minutes later, a truck was approaching in the live lane. At 8:15 a.m., still travelling at 90 kilometres an hour, it collided with one of the stopped vehicles. Tragically, Claire's husband and the other driver were both killed.
He was stood there 1 minute and gone the next. Your brain just doesn't work. I couldn't function for 2 weeks, but especially immediately.
Research shows that smart motorways play a role in preventing accidents due to speeding and rear-end collisions. But in this case, the coroner's inquest suggested that the existing system played a role in the tragedy.
This is the coroner's Regulation 28 report to prevent future deaths. The inquest heard unaccepted evidence that the lack of hard shoulder due to the road being a smart motorway contributed to their deaths.
The MIDA system had neither registered the original accident nor closed the left lane.
The lane should have been closed as soon as Jason stopped, but it wasn't, so the lane was left open.
The MIDA system, in effect, detected slowing vehicles, but it didn't detect stranded vehicles.
Once the vehicles were stopped in the live lane, it became a race against time to warn traffic of the obstruction ahead.
Part of the problem with these smart motorways is that we've discovered that actually, on average, it takes almost 20 minutes between when the vehicle stops and when that lane is completely closed.
With vehicles travelling on Britain's motorways at speeds over 100 kilometres an hour, sometimes this can be too little, too late.
The risks for drivers increases substantially because if they can't make it to the refuge area, then they're 200% more likely to be involved in a collision than if a hard shoulder were present.
In 2021, the UK government ruled that within 2 years, all smart motorways must include radar systems to more quickly spot stopped vehicles. But many believe that there is only one real solution.
The only answer is to restore emergency hard shoulders, and therefore the moment somebody feels their car is going to fail, they have the opportunity to get straight onto the emergency hard shoulder.
You can say that it's scrapping smart motorways, or you can say that you're adapting smart motorways, but we need a hard shoulder in every single instance.
This is a powerful reminder of the challenges involved with massive infrastructure, particularly when it impacts so many people every single day. The hope is that lessons learned from tragedies like this will make the system safer for everyone in the future.